Okay, well, thank you everybody for having me here today. It's nice and early in the UK, which is where I'm talking to you from. And in my talk over the next half an hour or so we've got time for questions at the end, I know it's kind of preaching to the choir here. We're geoscientists, we work within the industry, we know how important it is, but I want to talk about why mining is so important, why it's so important that we act as kind of stewards of the earth without that sounding too lofty. And then I'll talk about the work that we're doing in Cornwall with Cornish Lithium, so trying to approach mineral exploration and extraction as responsibly as we possibly can do. So my background is that I'm a geologist by training. I did a master's in mining geology at the Camborne School of Mines down here in the southwest of the UK. And then I got a job working for a junior exploration company and spent quite a lot of time doing fieldwork in Morocco and Ethiopia for a few years, which was awesome experience. I then moved back down to Cornwall in 2017, actually, 3.5 years ago, which has gone very, very quickly, and joined Cornish Lithium. I actually drove down to move back down to the southwest and drove straight to an interview with Cornish Lithium and started the next day. So I was the first technical team member back then, and the company has grown exponentially since then. I think since when we went into lockdown in the UK in March last year, we had 12 members of staff, and I think we've now got 26. So we're growing really quickly, and our projects are progressing really quickly as well. So it's a really exciting thing, and it's going to be great to talk to you about that in more detail. So as part of our role about mining, and I'm imagining we're all attending an event on the Clean and Green Day because it's something we're really passionate about. We know how important raw materials are going to be for this energy transition. If we want to produce solar panels, if we want to produce low carbon technologies, if we want to facilitate this move away from fossil fuels and burning lots of carbon and causing climate change, then actually this is going to take a lot of raw materials. And I think that's something that many members of the general public, particularly here in the UK and Europe, don't necessarily actually appreciate how crucial raw materials are to our daily lives. In South Africa, you've got a really thriving mining industry. In the UK, we haven't had any metal mining for well over 20 years. And we've actually not had any coal mining for, well, I think it's still a tiny bit, but, mining is not something that happens in the UK in people's psyche. And so when you go and talk to the public about mining, you quite often get questions when we go into schools, for example, to do outreach and say, oh, so, what do you think of the mining industry? And people are like, do we even do that anymore? Do we need mining? Like, yes, just because it's not happening where you can see it. Absolutely. We use the products of mining every day. And it really kind of surprises people. So I think a big part of our role in facilitating this clean, green energy transition is actually going to be making sure that we've got the public on side and people start to understand and appreciate where all of the things that they're using in their daily lives come from, whether that's a metal water bottle or, 2/3 of the periodic table in their mobile phone. People don't necessarily have an appreciation for that. And that means they don't have an appreciation for the impacts of what they're consuming. And if they don't have an appreciation for the impacts of what they're consuming, then it's very easy to say, mining, bad, give it a blanket, no. Something I've found really interesting is doing outreach events in the public. And we've done some quite high profile ones at some of, the Science Museum in London, for example. And at a few of them, we've literally just taken along these big pieces of paper, written mining on one of them and renewable energy on the others. And we've asked people to come up and just write what comes into their mind, word association. What is the first thing that they think of when somebody says the word mining to them? And you can see the kind of answers that we've got. We've got things such as people telling us it's dangerous, it's wasteful. People immediately link it to coal and fossil fuels. And pretty much everybody talks about how bad it is for the environment. So overwhelmingly, a pretty negative connotations that people have with the mining industry. You then ask people the same question about renewable energy, and they mention wind turbines and they mention solar panels, and everybody realizes how important these technologies are for if we want to combat climate change. Everybody talks about how green they are as well. That's all great. And, you know, I said here, I'm already preaching to the choir. If we aren't able to grow a material, then it's likely we've got to mine it. We've got to extract it from the earth somehow. So everything we use in our daily lives has either been grown or it has been extracted from the ground. It's been mined. I give the example here, you know, a smartphone contains nearly 2/3 of the elements from the periodic table within it now. And they've all come from different mines all around the world. Think of the supply chains associated with that, the impacts associated with these supply chains, not just the extraction and refining of these materials. And so it really is a huge global industry. And if we want to make sure that we're going to be able to extract all the raw materials that we need for this energy transition, then we really need to look at these whole supply chains, and we need to make sure we're doing them as responsibly as possible. Because if we're extracting lithium, for example, because we want to help fuel this energy transition, that's all great. People who are buying electric cars that these lithium ion batteries go into, they're buying these electric cars because, you know, they want to feel good about themselves. They want to feel like they're doing something positive for the planet. But actually, if the impact of producing all the raw materials that have gone into that electric car are really significant, then that really does kind of mitigate why they're buying that electric car in the first place. And so these conversations are starting to take place more. In the UK, for example, at the moment, you know, fuel, diesel, petrol is taxed. So there's a lot of thought going on in government as to, well, if we no longer have diesel and petrol cars in, you know, 10, 15 years time, where's all of that revenue going to come from? So they're looking at actually potentially taxing cars on the carbon impact of actually producing that car. So if one car is being produced with a localized supply chain in a much more responsible low carbon manner than another, then the tax on that car might actually be lower than the tax on one that's been produced in a different manner. So people are starting to think about this whole supply chain, this life cycle assessment of products, but you know, it's still in its really early stages. And then there's the whole argument that, okay, in the West, especially, you know, Europe and North America, we're really lucky that we are developed economies. That's fantastic. So it's quite easy for us to say we need to ban all combustion engine vehicles by 2030, which is what the UK has said. You know, no new cars sold, no new vehicles sold after 2030 can have a typical, you know, a classic combustion engine. But we're already a wealthy society. We went through the first industrial revolution in the mid-19th century, caused a hell of a lot of pollution. And now we're turning around to countries that are in the developing world and saying, oh, actually, you know, you can't burn those fossil fuels. You can't cause that environmental degradation as part of your development. It's a very difficult conversation to have, and it's not necessarily something that we have the right to. So there's a lot to think about. In addition, in places such as China and India, we've got such massive growing populations and across swathes of Africa as well. And a lot of these populations are becoming wealthier. And we're getting a lot more middle class people around the world who all of a sudden are aspiring to having their own car in their family and living in, you know, much more brick built houses and consuming a lot more. So the argument that simply recycling everything that we've currently got in circulation simply cannot meet this future demand for materials. There's this amazing statistic by the World Bank that in the last 5,000 years, humanity has produced about 550 million tons of copper. And the World Bank estimate that the world will need that same amount of copper in the next 25 years to meet global demand. So when people turn around and say, oh, why don't we just recycle everything that we've got in the urban environment? Absolutely, we need to think about this circular economy and build these supply chains. But that's not going to be enough. And so let's look at lithium now, because, you know, I work for a lithium company and it's something I know a bit more about. The World Bank estimate that we need 965% more lithium by 2050 than we produced a couple of years ago. And if you take into account that in the mining industry, it can take, what, 10 years from finding something to actually producing it, then that's a hell of a lot of work for the industry to do over the next few decades. So it also, so as well as meaning that, we need to expand production at the current places producing lithium around the world, we also need to look for mines that are probably going to be in slightly more remote locations. The logistics might be more difficult. But perversely, I think we also need to look slightly closer to home. Europe and North America in particular are only just starting to think about, actually, could we produce some of these raw materials ourselves? In the UK, we've got prospective geology. We've had a really, globally significant mining industry in the past, but we haven't produced anything for the last couple of decades at least, but on a big scale for the last 40, 50 years. And that's very much because people have been much happier to kind of outsource extraction to other parts of the world. It's been cheaper to do it in other parts of the world. And, that's the only consideration that people have had previously. So there's some statistics out there that say the lithium in an electric car battery that's, if I was to buy an electric car in the UK now, there is a serious chance that the lithium in that battery could have traveled over 50,000 kilometers around the world before that car has driven a single mile. So let's look at why. So at the moment, most of the world's lithium is either produced from hard rock in West Australia from a mineral called spodumene, or it's produced from these salar deposits, these salty brines in South America. Sorry. That's great. So at these mine sites, more often than not, a mineral concentrate will be produced. If we're producing it from a salar deposit in South America, these salars form in really arid environments, such as the Atacama Desert, which, are really high altitude. They're very, very dry. And you get these really salty liquids that form just below the surface. Lots of us have seen photos of the Bolivian salt flats, for example. And so in places such as Chile, Bolivia, and Argentina, they have these big, high altiplanos, and these salty solutions form just beneath the surface. People will drill down, pump them up to the top, and put them into these huge evaporation ponds. So these are fairly expensive to set up because they've got to be lined with an impermeable membrane. And to give a sense of scale, I think that's about apparently 5 kilometers from the front of this photo to the pond at the end. So these are big, big structures. And what they do is they pump the water up to the surface, put them into a pond, and then just rely on solar evaporation. So over about 18 months or 2 years, the water will evaporate off and you get this really, really salty solution left. It's that really salty solution that they then process and form a mineral concentrate. So the lithium is probably present as lithium chloride in those waters, a lithium salt, and they'll produce it, potentially turn it into a lithium carbonate on site. The things to note are you need a lot of space for producing lithium in this way. And also, I think over 90% of the water can be evaporated off and lost to the atmosphere, which is cheap, but also in these really water sensitive areas is having a really big impact on the local water tables, which is then affecting local communities, their ability to farm, and it's having really negative connotations. So yes, it's an old technology. Yes, it uses solar evaporation, so renewable energy, but actually how sustainable is it? So once you've produced your mineral concentrate on site, for the last few years anyway, these mineral concentrates have been shipped over to China. And that's because the Chinese have been really smart at, developing the ability to refine these mineral concentrates into a battery quality product. And that's key because the impurities are really important. You want very few impurities and they've got to meet certain standards. And certain elements such as sodium, for example, can actually really screw up a battery. So the Chinese have been very clever at developing the ability to actually refine stuff into battery quality chemicals. So things have been shipped over to China, which is a fairly significant way. And then actually maybe there'll be these battery quality chemicals might be then shipped to Korea or somewhere like that to be made into a battery cell and then assembled into a battery pack. That might then be shipped back to Europe, where it might be then assembled into an electric vehicle. And there's your 50,000 kilometers. So that's just one element. And that's just the journey of one element within an electric vehicle battery. So when you start to add together everything else, so cobalt that's maybe being produced in the DRC or or Australia, you know, these are big, big supply chains. So why are we interested in lithium? Well, lithium, as I said, is a key component of lithium-ion batteries. The first lithium-ion battery was commercialized in 1991. So before that, lithium had been used as a glaze in pottery. I think it's used as a drug in pharmaceuticals to treat depression. But you know, there wasn't a huge market for it. And so it's really because of the advent of the lithium-ion battery and the need for lightweight portable batteries that's driven this huge increase in demand for lithium. So lithium-ion batteries are found in your mobile phone, they're found in your laptop, but actually, if you also want a car to be lightweight and portable and charged by a battery, then a lithium-ion battery is pretty key. So I know that this map is now slightly out of date, but it's probably still pretty much true. It shows that most of the world's lithium is either produced in Australia from hard rock or in South America from these salar brine deposits. What's really noticeable about this map is actually the lack of any significant production from Africa, from North America, from Europe, or even from Asia. It's not because we don't have lithium deposits in those parts of the world. It's just that previously, you know, the market hasn't necessarily been there to justify looking for lithium deposits. It's only really in the last few years that people are starting to bring things. So if we were to have a map of where exploration projects are, projects in development for lithium, then that would look very different. This is also important because if we look at this chart on the right-hand side, we can see that although China was only producing about 7% of the world's lithium from primary sources back in 2017, it was actually producing over 50% of the world's lithium chemicals. So that just shows how much of that supply has been shipped to that part of the world to actually be refined into battery quality chemicals. What's also notable from a European point of view is the lack of any significant production of lithium chemicals in Europe, despite us being the second biggest market for it. And actually, if you look at that as well, there's nothing in Africa, nothing significant there. And these are huge growing markets. So we need to look for lithium deposits in these parts of the world. And you know, we are, but the work that we're doing, especially in Cornish Lithium, is actually looking at deposits of lithium that have been previously considered, you know, unconventional. The hard rock mineral that you have in Australia is a mineral called spodumene. And to extract the lithium from that, you have to roast it to really high temperatures, I think nearly 1,000 degrees Celsius. And so to get to nearly 1,000 degrees Celsius, you need to use fossil fuels, really. So the carbon impact of roasting to high temperatures can be quite significant if you're producing lithium in that way. Take a drink. So what are we doing? We're looking for lithium here in Cornwall. And this is a photo of some iconic engine houses that we have down here. And you've probably seen similar ones around the world because the Cornish mining industry, you know, has been globally significant in the past. We've produced over $50 billion worth of tin in today's money, produced over $12 billion worth of copper in today's money. And that's all over the last few hundred years. But we've got evidence of mining going back here for at least 5,000 years. And the mining industry is, as we all know, very cyclical. And when it's been at its high, it's been booming. But when it's been at its low, the Cornish miners have spread out all across the world, to South America, to Africa, to Australia. And actually, they've taken their engine house design with them in a lot of places. So why are we looking for lithium down here? It's because the whole of Cornwall, the whole of the southwest of England, so this little peninsula here, if you can picture it, is with the far southwest part of the UK, with a bit that sticks out on the end. And we're underlain by this big mass of lithium-enriched granite. So the granite was intruded about 290 million years ago, over a 20 million year period. And it's actually those final pockets of granite that were intruded that are the most enriched in lithium. So this central granite, I don't know if you can see my mouse, but the central granite around St Austell, pockets of that, this G5 topaz granite, these are the ones that are most enriched in lithium. So you can see we've got a pocket in central Cornwall here, and then out to the west, down to the southwest, there's also another pocket there. In addition, the granite in the UK the granite that underlies the southwest of the UK, sorry, is also much hotter than the other rocks in the UK. So this is a map here of the UK, and you can see that the southwest really is this pokey out bit in the corner at the bottom left. And the heat flow that we have down here is much higher than other rocks in the UK. And that's why we've got the potential for also producing geothermal energy. I mentioned that we've got this mining industry that spans the last 5,000 years. I think we've got over 3,000 named mines in Cornwall. You know, we're only a small part of the UK, really. So it's a really heavily mineralized part of the UK. And traditionally, you can see these, if you squint and look closely at your screens, you can see these east-west trending green structures on this map clustered around the granite margins. It's typically these east-northeast trending structures that contain the tin and the copper mineralization. Obviously, they're associated with the margins of the granites. And then you can see there's this orthogonal, there's this perpendicular 90-degree angle set of longer structures which cut these mineral lodes. And these have typically been called cross courses because they cut across the course of the lodes that have been mined. And it's these northwest trending structures that tend to have the highest permeability. They've been the most recently reactivated. That is important if you're looking for lithium in geothermal waters, which is what we're doing here. So across Cornwall, I mentioned that there are these engine houses dotted everywhere. I've just shown you a photo of them. These are here because they needed to dewater the mine. And dewatering the mine meant that they could mine to deeper and deeper depths, as we all know. So a lot of the water that they were pumping out were these meteoric waters coming from surface, but actually in a lot of the deep mines, they had these upwelling warm waters coming from depth. And these geothermal waters are actually where lithium was first discovered in the UK, not where lithium was first discovered in the world, but in the UK. And in 1864, a guy called Professor Miller from King's College in London came to Cornwall, took some samples of these upwelling hot springs, as they used to call them, in one of the deep mines, took it back to London and analysed it in his lab. And he wrote an academic paper. There's a quote from it just in the bottom left here. And it says, these hot waters could be a potential source of lithium. It's a shame that we don't have a use for it. So fast forward to 2020, 2021, as it is now. And that's exactly what we're looking for down here. Lithium contained within these geothermal waters that we know circulate naturally at depth. And they circulate within these permeable geological fault structures. And then we're also looking at potential for producing lithium from the granite. So Cornish Lithium was founded in 2016 by Jeremy Rathall. He's a mining engineer by training, but he's been working as an investment banker for the last 25 years up until this point. And so in that capacity, he's financed mines all around the world, seen trends in commodities, and realized that actually lithium was going to play a really significant role as we go forward, because we need to move away from fossil fuels. There's probably going to be battery power that helps us do this, and lithium's a really key constituent of many of those batteries. He also remembered that Cornwall has the potential for lithium, and that led him to found the company. And the core ethos is really around, can we extract this lithium in Cornwall, but can we do it in the most responsible manner possible? So we've now got mineral rights agreements in place over, I think it's more than 500 square kilometres actually. But that's about 15 to 20% of the 15 to 20% of the southwest of England, which is pretty cool. And we've also actually just been awarded some exploration rights from the Crown Estate to explore for lithium in geothermal waters in 4 areas offshore of Cornwall as well, which has significantly expanded our mineral rights package. We're a private company at the moment, but I imagine we'll probably list at some point in the future. And so, yeah, and I said, we're growing rapidly. We've gone from 12 people last year to 26 now. So we've got 4 major exploration streams. One is looking at the potential for producing lithium from the granite itself. And we don't have spodumene in Cornwall, but rather we've got lithium-enriched mica minerals within the granite. It's the kind of polylithionite series, so they're somewhere between lepidolite and zimwaldite. I'll talk about that in more detail in a moment. And then we're looking at producing lithium from geothermal waters as well. And we've got 2 different scenarios for that. One is what we're calling shallow, where we will drill down to anywhere between 1 and 2 kilometers depth. You'll have temperatures of 40 to 70 degrees Celsius for those waters, and a certain amount of lithium in solution within those waters. And then we're also looking at potential for producing lithium from deep geothermal. So if you drill down to over 5 kilometers or around 5 kilometers depth, you have water temperatures of 185, 190 degrees Celsius. So if you can pump them back to the surface, you can actually flash those off, turn turbines and actually generate geothermal power. So once you've then generated your geothermal power, if you can then put that water through a lithium extraction plant, then you can actually use that geothermal power to power your lithium extraction plant. So that's using green, zero carbon energy to power your lithium extraction plant. Then you can actually produce lithium in potentially a net zero carbon manner, which is pretty neat. So we're also looking at potential for that. What we also find is that the deeper you go, the hotter it gets. The hotter it gets, the more stuff there is dissolved in the water. So the higher the total dissolved solids, but also the higher the lithium content. But you can drill down to about 2 kilometers with a mineral exploration rig, a decent diamond rig. To get down to 5 kilometers, that's where you kind of need oil and gas style technology. And so the cost of drilling goes exponentially up. So somewhere there's a sweet spot, the depth that you can drill to, the higher lithium grades and higher water temperatures, but also it's more affordable. So we'll see what that is. And then finally, we're also looking for other battery metals down here as well, whether that's copper, whether that's tin, zinc. There's even been historically a couple of pure cobalt mines in Cornwall. Probably nothing that's going to be significant enough to open up as a mine on its own, but there's high grade ore down here. Typically, tin and copper were mined between 5 and 8% back in the 19th century here, when mining was at its peak. So there's actually a lot of waste piles sitting around as well with, potentially quite high grade ore in. And it's worth mentioning that, responsible mining actually has the potential to contribute positively to all 17 of the UN Sustainable Development Goals. And obviously in different parts of the world, you can have different impacts as to which ones you can most impact. But affordable and clean energy is a really important one. Industry, innovation, infrastructure, responsible consumption and production. We can contribute positively through improving the local environment, but also through socioeconomic factors as well. So it's always worth bearing that in mind. So that's great, but how are we actually exploring for these things down here? So I keep mentioning that Cornwall's got this amazing mining heritage, and we've been mining stuff for thousands of years, but we've been mining stuff professionally for the last 250 years, I'd say. And so that means that we've got a whole wealth of information about the subsurface. There's over 3,000 named mines in Cornwall, and there are just thousands and thousands of kilometers of, it's like a rabbit warren under certain parts of Cornwall. And so that means there's a lot of information about the subsurface as well, but most of that information is written, it's on paper. So we actually have 2 digital archivists who work with us full time, and we go and we have access to archives that some of them haven't seen the light of day for 100 years or more. And so our archivists will go in, will take photos of these maps. Some of them, they're hand painted or they're on vellum, and they could be 2 meters by 2 meters in size. And so there's no way that we can just put that through the scanner. So they have to take photos of it, digitally stitch it together, and then they hand it over to our GIS mapping team, who will bring that in, will georeference it and start to capture information in 2 dimensions using ArcGIS. And then we use a program called Leapfrog for our 3D modeling. And so we'll bring in these maps and sections, we'll hang them in virtual 3D space, we'll trace off the information that's contained within them. And we've got information for whole swathes of the subsurface. So it's allowing us to build these really accurate 3D digital models of the subsurface, which allows us to build up a picture of the geology, the mineralization and the structures without actually having to spend much money on drilling. So we can do all of this to target where we actually want to drill. So in this image here, the colorful images, the colorful things kind of trending northwest on your screen, these are mineral lodes, and then the gray structures are these orthogonal cross-course faults. We're also bringing in things such as satellite imagery. We've been doing 3D drone surveys that allow us to build 3D digital models of where these geological structures outcrop. And that means that we can then take measurements of them while sitting in the office. So joy of joys, less time spent in the field, but it's a much more efficient way of doing field work. It means we can constantly go back and remeasure things and take more measurements off these same outcrops without actually having to go back into the field and scramble over cliffs. So it's much more efficient. So we're looking for lithium in hard rock. Just checking the time, I'm not talking for too much longer. We are looking for lithium in hard rock, but Cornwall is a very beautiful place. And, the main part of its economy is actually now tourism. Since the mining industry collapsed in the 1980s, limped on until the 1990s, tourism has really taken over as the main part of the economy. It's a beautiful place. So when you mention that you want to potentially open a hard rock mine, some people are like, "Oh, is that going to be possible?" And the answer is yes, we think so, but with a caveat. In the centre of Cornwall, in that, if you can cast your mind back to when I showed you the outcrops of granite, that central outcrop of granite has actually been producing China clay, kaolin, for the last 250 years. So if you ever look at it on Google Earth, it looks like a moonscape. You've got these huge open pits that are bright white because they've been extracting kaolin. And it's actually in some of these old China clay pits that there is the most potential for producing lithium, because that's where we've got the most enriched lithium micas. So we don't want to open a new open pit, but actually if we can go and repurpose an existing China clay pit to produce lithium, then that's quite neat. So again, tying into trying to minimize our impact of mineral extraction here in the UK. We completed our initial drill program on this project last year, had really promising results, and so we're now doing our second campaign. And this is going to try and give us a JORC compliant resource by the summer, which is very exciting. It's allowing us to, build up our 3D model of where this lithium mineralization is. But excitingly, it's through embracing technology that we're really unlocking these mineral deposits here in Cornwall. So mica deposits, no one's producing lithium on a commercial scale from them yet, anywhere in the world. There's a few projects in development. And we have actually acquired a license from Lepidico to allow us to extract the lithium from these micas without having to roast to really high temperatures. So we've got an exclusive license to use in this part of Cornwall. It's not exclusive for the rest of the world, but in this part of Cornwall, it is for us. And it's using a hydrometallurgical technique to produce the lithium rather than having to roast it to really high temperatures. And this is really exciting because you can actually directly produce a battery quality lithium hydroxide product using this technology. So that means we won't have to ship it elsewhere to refine it. We'll be able to produce that battery quality product here in the UK, which is pretty neat. And then we're looking for geothermal. So we've got shallow geothermal down to about 2 kilometers. We've done our first couple of R&D holes where we drilled down to about 1,000 meters each. We used diamond drilling, so we've got lots of nice core. And as we drilled down, we intercepted a number of these permeable geological structures. So, if you think of a granite work surface or something like that, granite isn't particularly permeable. So that's why these geological faults are so important, because that's where we have this natural permeability that allows these geothermal waters to circulate at depth. We believe that as they've been circulating for thousands of years through the lithium-enriched granite rock, they've been heating up because the granites are hot, and they've also been effectively leaching the lithium out of the mica minerals and into solution. So if we can drill down into these permeable horizons, pump the waters from these permeable horizons up to the top, then we can put them into an extraction plant, use new direct lithium extraction technology to allow us to selectively remove just those lithium compounds. So we've done our first couple of R&D holes. We knew that there are upwelling warm waters that contained lithium. Historically, when they've been mining in this part of Cornwall, the mines have obviously all now flooded because they've stopped. But anyway, we've managed to drill down, intersect these structures and produce fluids from them that have been warm and enriched in lithium. So that's pretty cool. So we're now setting up this site as an R&D site to allow us to test some different facilities, some different extraction technologies. We are also collaborating with a deep geothermal project in central Cornwall. So they drilled down to just over 5 kilometers depth last year, the year before, and they're in the process of building their power plant. So we managed to take some samples of their deep water when they first produced it back at the end of the summer last year. And we sent it off to the lab, and we found that these were, actually pretty remarkable waters. So this little chart on the bottom here shows the lithium grade on the y-axis, and on the x-axis, the total dissolved solids. So you can see that salar brines, the stuff you get in South America, you get high lithium grades, orders of magnitude more than certain other deposit types, such as geothermal waters or oil field brines, but also they're a lot saltier. So if you're trying to selectively remove just lithium compounds, can make it quite difficult. If you look at the typical range that you can get for geothermal waters, you can see that they cluster from about 150 up to about 200 parts per million lithium, 200 milligrams a litre lithium. The United Downs Deep Geothermal Project, which is this big red blob, that is the project here. So actually we found that these are the lithium grades that we've got in Cornwall from the Deep Geothermal Project are higher than any other published grades from any geothermal waters worldwide, which is pretty exciting. But what's remarkable about them is how low the total dissolved solids are. So that little black cross in the bottom left, that's seawater. So actually the waters that we've got in Cornwall, although they're more enriched in lithium, they're actually 1,400 times more enriched in lithium than seawater. But actually we're also less salty. So if you're trying to selectively remove just the lithium compounds, it really is remarkable that we've got kind of lithium enrichment in Cornwall, but very little else in that water. So if you're trying to then extract just the lithium compounds, that makes it, much more amenable to processing. And, if we can co-produce geothermal power from these waters and then extract the lithium, that's pretty exciting. And we've received some government funding to allow us to look at this. So we're building a pilot lithium extraction plant on this site as we speak. So I've talked about how you generally produce lithium from salar brines. You wait for the evaporation, then process it into a lithium carbonate product in most cases. We are looking at using something different. It rains far too much in Cornwall for us ever to be able to rely on it just evaporating off. But also that's not very efficient. You lose a lot of water and it takes a long, long time. We're looking at using a suite of technologies called direct lithium extraction, DLE, and this could be ion exchange resins. It could be an absorbent that you have. Sometimes it's really highly selective membranes. So DLE kind of is a catch-all phrase for selectively removing just the lithium compounds from the water, but there's different mechanisms by which you can do it. We are going to be trialing a number of these different technologies at our sites in Cornwall to see which is most suitable for the Cornish context. And this is just a schematic showing that, pump up hot waters from depth. They're going to geothermal plant, will produce geothermal power. We'll then have heat as a significant byproduct as well. So maybe we can use that excess heat to heat greenhouses, for example, and grow horticulture. Then we'll go into a lithium extraction plant. We'll extract the lithium compounds from the water. Those waters will then be re-injected back to depth to allow them to recharge, reheat, absorb more lithium, etc. So just to summarize then, this energy transition is going to be hugely mineral intensive. We need these minerals to enable the change from fossil fuels to low carbon technologies and combat climate change. But a really key part of that is going to be making sure that we have the public on side with us and people understand where all of these technologies are coming from, the impacts that it has. And so as geoscientists and people who work in georesources, we really are going to play a really vital role in this energy transition. And I think responsible stewardship is a great phrase to kind of catch this all. But it's really through embracing new technologies to allow us to explore more efficiently, using satellite imagery and remote sensing to come up with targets in the field efficiently, using new technologies to extract things as responsibly as possible and in the most low carbon manner as possible. And, this will all help us to gain this social license to operate and maintain it. So I think new technologies are really going to be key in helping us to embrace this and be able to deliver the materials that we need for our clean, green future. So thank you very much for listening. And if anybody does have any questions, I'd be happy to answer them.
Thank you very much, Lucy, for that really interesting look at the relationships between mining and the green economy, and also what it is that you folks are doing out there in Cornwall. We have got a question in the chat box from Xavier regarding your exploration program. Are you looking potentially at anything in Southern Africa somewhere down the line?
I mean, never say never, but at the moment our focus is very much on the UK. We've got a lot of exploration licenses in the UK. And at the moment, the government are being very supportive of what we're doing. I think just in the last 12 to 18 months, actually, they've kind of woken up to the fact that we need to think about where we're going to source these raw materials. I think it's something that the UK government's just previously, he said, okay, great that we want to build so many electric cars here, but where are we going to get the raw materials from? To give an example of that, there's a thing called the Faraday Battery Challenge in the UK. And so the government have invested, I think, £274 million in developing lithium ion battery technologies and developing capability for us to produce lithium ion batteries in the UK. And, research organizations and industry could apply to this pot of money to say, look, we want to develop this part of the supply chain. We, Cornish Lithium, along with the Natural History Museum and some mining consultants called Wardell Armstrong, we applied for just £500,000, so £500,000, to look at the potential of producing lithium in the UK from a UK source. And we were the only project out of that 275 million that was looking at sourcing these raw materials. Everything else was looking at, okay, it's fine, we'll just, you're like, well, where do you get the lithium from? They're like, well, we just buy it. It hadn't occurred to anybody that we have to think about where it comes from. So just in the last 12 months, we're starting to see a big change in the UK as to where, actually thinking about where raw materials come from. But so I think for the time being, our focus is very much going to be on developing these projects in Cornwall. But no, there are some fantastic lithium deposits in parts of Southern Africa, absolutely.
Thank you. Judith, I see you've unmuted yourself. Do you have a question there?
Yes, I just wanted to say to Lucy that Bakita in Zimbabwe has been producing lithium for many, many years. And I think it's regarded as one of the 3 biggest lithium resources in the world. So I'm sure Michael Cronwright will be telling us a little bit more about that. I just felt that Lucy kind of dismissed lithium in Africa, but fantastic.
No, please don't think I was. Thanks, Judith. No, please don't think I was dismissing lithium production in Africa. It's just from, that map, which I do admit was, it's 2017 now, so I do need to find a newer version of it. But, this, on a global scale, the significance of the amount that's currently being produced compared to what's being produced in West Australia and South America wasn't up there, but I will absolutely relook at that. So thank you.
I think the issue is that Bakita has been producing lithium for the ceramics industry for the last 40, 50 years or so. And I think it's happy to chug along doing that. But I'm sure Michael Cronwright is going to tell us more, so I'll end there.
Yes. Yeah, and there's so many projects that are in the development stage now and coming into production, that map is totally out of date. I do accept that, but I think this general sentiment that at the moment the vast majority of production does still come from Australia and South America, I think that's possibly still true, but especially when we're thinking about battery grade lithium, perhaps.
In Africa, exploration plays in nowadays, and we're getting quite far down the development pipeline. So just a disclosure, read it at your leisure. And so why lithium? What is lithium? Discovered in the 1800s, and its initial uses in the 1940s were some of the first hydrogen bombs. Its applications today are largely now still energy related, but on the greener side of things. Its main applications are ceramics and glass, greases, catalysts in the polymer production, fluxes, air treatment, pharmaceuticals, and I suppose the 2 most relevant here, although I won't really touch on the aluminium aspect, but aluminium with green energy and EVs is a big input into the EVs, and lithium decreases the density, increases the strength, and obviously then lithium ion batteries. If we just look at how the market's changed over the last 15 years, we've gone from 125,000 tons lithium carbonate equivalent through to last year 437,000 tons lithium carbonate equivalent. And you can see that the lithium ion segment of that market's tripled. Incidentally, last year saw a decrease from 2019, just as a result of COVID and a bit of a surplus that entered the market. So if we look at the demand, it's been growing at about 10% a year. It's set to accelerate to 20 to 25% a year, and largely taken up by battery demand. And this is the same slide, really, just a bit more granularity. And in terms of the battery demand, it's largely EV driven, electric vehicle driven, which is the green bars. The blue bars are from energy storage and electronics. And this really, on the right, is really just taken from a Bushveld Minerals presentation. And obviously it's a competing technology with a whole lot of other technologies. And it's more horses for courses in terms of energy storage. But for electric vehicles, your lithium ion battery at the moment is your what's a charge of choice. If we look at what's forecast for the lithium market, as you can see, 2019 there was a bit of a surplus, and they forecast a surplus again for this year, and then going into a deficit going forward. This is work done by Benchmark Minerals. So why lithium ion? Well, it's a known proven technology. The prices have been coming down, and you've got various chemistries for various applications in the electronics and electric vehicle space. And you can see here, just bang for your buck, I suppose, lithium ion has a high specific power and energy density. Obviously, there are a few cons that everyone knows about: vehicles catching fire, batteries tend to degrade over time, and they have a limited temperature operating range, so they do require some sort of heating and that in colder countries. So why this demand? Well, it's the rise of the EV and energy storage, obviously as a result of efforts made to curb CO2, increasing CO2 and pollution levels. Many countries have also have put policies in place to mitigate CO2 emissions. And a lot of that has revolved more recently, and it's been quite well publicized, on electric internal combustion engine restrictions. And largely in Europe, North America, but countries like China, although they haven't necessarily formalized that they have got policies in place to look at reducing their carbon footprint through the transport sector and public transport. And if we look at global CO2 emissions, transport probably makes up about 16%, between 16 and 25%, depending on your source of your CO2 emissions. And obviously that varies from country to country. As you can see, South Africa, no surprise, electricity generation, when they're generating it, is 42% of our CO2 emissions. A country like Norway, only 3% from electricity generation. But you can see why transport and generation sector have been targeted to try and curb CO2 emissions. If we just look at an internal combustion engine versus an EV, this is just sort of a generic example, but you can see it, you can sort of drop it to about 40 grams per kilometer on a battery electric vehicle, depending on the energy mix. Obviously, if you go to a zero emissions energy charging, you drop it down to 1 gram a ton. 1 gram CO2 per kilometer, but obviously that's probably quite a long way off for many countries. COVID last year, well, it obviously had a big impact on the transport sector, and it provided us a bit of a glimpse into what is possible by curbing CO2 emissions from vehicles. And there was about 2 gigatons reduction in CO2 emissions compared to 2019, of which 1 gigaton of that carbon dioxide came from the transport sector. And if you look at the makeup of that 1 gigaton, 265 million tons was from the aviation sector. But it translates into, I think, 100 million conventional cars being taken off the road. Obviously, by the end of the year, with lockdowns coming to an end, CO2 levels got back to normal very quickly and on the increase. So I suppose the question, where to from here? Well, with a sustainable recovery, we can probably look at dropping CO2 emissions. Without a sustainable recovery, we'd look at on the trajectory of increased CO2. But I think what COVID's allowed a lot of countries to do is to sort of expedite their policies around electric vehicles and changing the energy mix to more renewable sources. And this one just shows the rise in EV sales over the last couple of years, and it's been quite meteoric. China's always been sort of the big market there. However, recent years, we've seen the rest of the world catching up quite quickly. So if we look at where South Africa sits with this, companies like, I think it's BMW and Jaguar have put quite a lot of charging infrastructure along some of the major routes to Cape Town, Durban and the Windy City. If we look at EV sales in South Africa, they've been pretty dismal, and it's really just, this is just looking at pure electric vehicles. We're not looking at hybrids here. So the two companies really that dominated at the moment are Jaguar and BMW. Nissan used to sell the Leaf. I don't think they sell the current generation, but I think there are plans to bring it back. If we just look at total sales up to December 2019, this is looking at hybrids. So obviously your Toyota Prius has led the way, along with a couple of other hybrid vehicles offered by various other manufacturers. If you look at plug-in hybrids, you've got the likes of BMW, Volvo with their offerings, and then just pure battery electrics. The sales up to December 2019 were only 545. So South Africa makes a very small segment of that market, largely because EVs, I suppose, are seen as a luxury item at this point. The study by Green Cape basically looked at what South Africa has in terms of a EV infrastructure and building a supply chain around that. Our vehicle component and production in South Africa accounted for about 30% of the country's manufacturing output in 2018 and more than 14% of South Africa's total exports. So there's definitely a need for South Africa's auto industry to get with the program, I suppose, and actually modernize, because otherwise we're going to be found left out in the cold very quickly if we don't, I suppose, develop with the rest of the world in that sector. But we do have the makings of something that with potential to sort of start producing electric vehicles. I just thought this was quite an interesting picture of reserved for green vehicles, and probably a dirty diesel buggy, looks like an Isuzu park there. I suppose the big thing that's happened now as well is greenwashing, where people sort of paint a picture that they are environmentally friendly but don't really walk the talk. That's changing quite rapidly, and companies need to change their supply chains, regionalize them to reduce the carbon and CO2 impacts. Supply chains need to be sustainable. Your products need to be sustainable. You need to look at end-of-life impacts of your products. And obviously this all goes hand in hand with the ability to raise funds and just actually participate in this low carbon economy. Yeah, and I suppose it's no use producing lithium-ion batteries in electric vehicles if your supply chain's dirty. And really that just goes around sort of performance, your ability to make money, and sustainability, and just that whole supply chain. and that's a whole talk on its own. So if we look at what's happening in the battery space, in 2015, there were only about three or four companies looking at producing these bigger factories where they produce these lithium-ion batteries for electric vehicles and electronics and that. Come back to 2020, you've got 186 planned plants. I see Volkswagen yesterday announced they were looking at building, I think, 6 factories and basically going the Tesla way. And you've gone from 57 gigawatt hours to 103.1 terawatt hours. So it's quite a big shift. So if we look at what it's done, this whole hype has done to the lithium price. Lithium's priced according to lithium carbonate or lithium hydroxide. And you'll also see reference to ST6, which is spodumene concentrate, 6% lithium oxide. And they also track each other, but basically what you had leading up to 2016 was a bit of a panic buying and a boom in the price, largely because your supply was so constrained. The first to respond to the supply were your hard rock lithium producers, which are your pegmatite miners, just because they're generally smaller and less capital intensive to develop. Your big brine deposits in South America are a lot more expensive, and usually it takes about, I think it's about 12 to 18 months to get material just through your process. So when they expand, there's quite a large lag time between getting the evaporation ponds out and actually being able to produce a product. Obviously then, around 2018, you had a lot of mines entering the market and a bit of an oversupply, and your chemical converters that produce the lithium carbonate from the spodumene couldn't actually keep up with the supply. So it ended up with a bit of a glut in the market and prices dropped, and obviously that sort of had quite a big impact on some of the junior miners that fell by the wayside, and even some of the producers, junior explorers and producers. And then COVID hit, didn't help things. So if we look at where we are now, prices are on the uptick in China at least. And I suppose you look at share prices on the juniors and even some of the producers in Australia are sort of up 100% plus over the last 6 months. And I suppose prices do need to stabilize at a point where it is sustainable for mines to actually start producing material. So if we just look at what the lithium-ion battery comprises, just to simply break it up, you've got an anode that's usually made of graphite. You've got a cathode that's got varying formulae. It contains lithium, and then you've got an electrolyte, which is your charge carrier, and your lithium is your charge carrier, and then a membrane separator between the two. Obviously, lithium forms a small component of these lithium-ion batteries, depending on the chemistry. But like Robert Friedland likes to say, they should be called nickel batteries, although lithium's your key component in these things. But nickel's a large component of these. And then you've got cobalt, manganese, or you've got the lithium iron phosphate batteries. Obviously, some batteries charge quicker than others. Others have better energy density. So really, it's not a one-size-fits-all situation. And obviously, that's going to have an impact on a couple of other markets as well. The components that go into these batteries is very chemical specific. So it's not just any nickel that you can be putting into these batteries. It is quite a refined product. Similarly for cobalt and things like your manganese. And all of these markets are forecasting a bit of a deficit leading up to sort of in the next 5 to 10 years. We look at what lithium-ion battery prices have been doing. They've generally been dropping, and quite dramatically. I mean, $300. Obviously, these prices vary a bit, but this is just sort of the general trend. $300 a kilowatt hour, 2014. Today we're sitting at around $100. And obviously you're getting sort of efficiencies in your manufacturing and that, but it is going to reach a point where it plateaus based on your commodity prices. And that volatility is something that a lot of these producers see as a risk. And we've seen a lot of OEMs and your chemical producers actually trying to take interest or stakes in mines to ensure that they've got a supply. And obviously there's a lot of geopolitical risk associated with this as well, for countries to meet their CO2 agendas. If we just look at where the resources sit globally, a lot of them sit in South America and Australia. But if you look where the production's coming from, 5 years ago, most of it would have been coming from South America. Today, most of it's coming from Australia. And it's due to sort of shift back to about a 50-50 split between Chile and South America and Australia in the next couple of years. Obviously, there are other countries that have significant lithium resources. Incidentally, Zimbabwe is the 5th largest producer of lithium globally, all out of Pegmatite, and it's mainly petalite for some of the technical, for non-battery applications. So if you just look at what I was saying here, Australia is the largest supply at the moment, but that's bound to change as the rest of the world comes online. And you're going to probably start seeing production coming out of Africa, Europe, and America who do produce, but they don't disclose what they're producing. But the likes of Pegmatite Lithium are supplying or due to supply Tesla in the near future. And again, that's just on a trend of increasing demand, and hard rock is going to probably be the biggest winner out of this. If we just look at the supply chains where the flows of materials go, it's largely mined in Australia and Chile. Your refining all happens in China, a bit in Chile, and then your chemical production, again, China, Japan, South Korea. Your cell productions, again, China and South Korea, Japan, and your battery assembly, Japan, South Korea. So obviously, this comes with a huge geopolitical risk, and what you are seeing now is all these gigafactories going up, and they're not going up necessarily in the Chinas and South Koreas, but in Europe and America. So I think companies have seen the need to firstly sort of de-risk it geopolitically and also just shorten supply chains. And obviously they cost it to reduce costs in addition to the carbon dioxide impacts. This is a bit of a big slide to take in, but the takeaway from this is your ores refers to your pegmatite derived minerals, and your spodumene and your brines are from the South American brines. And they produce very different chemicals. So lithium carbonate's generally your input into the batteries. Historically, that was the case with your spodumene as well. But with the chemistries of some of these batteries preferring lithium hydroxide as an input, your spodumene materials or precursors can go directly to hydroxide and then into your batteries. And there's quite a big cost saving there. And it was always a case of your brines being sort of a cheaper, lower cost compared to a pegmatite derived material. With this circumventing the carbonate step, you actually bring costs pretty much in line. There's parity between the two. So there's not much benefit going one or the other. And obviously your pegmatites are a lot easier to mine, quicker to market as well. And just in terms of the companies that dominate this market, 75% of your lithium supply comes from 5 companies, namely Albemarle, SQM, Ganfeng, and Tianqi and Livent. So they generally dominate the market, and I think it is sort of a topic of another discussion as to sort of how they control prices. So let's get to the geology. I've been talking about brines and pegmatites. Well, lithium deposits, you've got actually four, I suppose, potential sources of lithium. You've got your traditional brines, your lithium pegmatites, usually spodumene and petalite are your minerals that are mined in these. And then you've also got your sedimentary deposits like your jadar deposit and your lithium clays that you're seeing a lot of juniors exploring for. You've got Rhyolite Ridge and Sonora in New Mexico. And then you've seen companies like, I think it's Vulcan in Germany, looking at the geothermal waters, recovering lithium from there in your oil field brines. To date, none of these have actually produced any lithium. And your pegmatites tend to have quite a wide grade range, but they're generally quite high grade in terms of lithium oxide and relatively small, where your brines are massive low grade deposits. You just look at the global distribution. Your brines sit in South America. You've got some, I think, in North America. Your pegmatites are generally distributed quite all over the world. And then you've got some of these unconventional deposits like Clayton Valley, which is your clay deposits. You've got Jadar and a couple of other deposits in this Vardar zone that stretches from Turkey. And that's also a massive boron producer. And if you just look at where the global resources sit, it's largely in your salars, your brines, your hard rock deposits, and then you've got this sort of mix of various other deposits. If you had looked at this a couple of years ago, it was really just dominated by your pegmatites and your brines, and not much consideration for other lithium sources had been given. So if we look at, I'm going to sort of focus on the pegmatites because Africa, we don't have the brines. And there have been a few salt pans that have been tested, but really with no success. So that's just Frank Hesse's take on pegmatites. And I suppose the reason why I got involved in pegmatites was really just an excuse to go and pick up gemstones when we were doing some work in Mozambique in 2000. So what is a pegmatite? Well, this is a definition by London: extremely coarse grain, systematically variable grain size. That grains vary in size by a factor of 100 from the margins to the center. You've got skeletal or graphic crystal textures, unidirectional growth habits, prominent spatial zonation in mineral assemblages and textures, or any one of the above, but usually you get a combination. And this picture here on the right is just a picture of a pegmatite. So if we look at pegmatite classification, your pegmatites are subdivided into two broad families, NYF, which is niobium yttrium fluorine family, or lithium cesium tantalum family. And that's really just based on the mineral chemistries that you find in these pegmatites. The ones that are the focus of the lithium industry are your complex type pegmatites and your albite spodumene pegmatites. Generally, these complex types are quite well zoned. You tend to find they're a little bit smaller than some of these albite spodumene pegmatites. And the albite spodumene pegmatites generally tend to be quite big, massive deposits with sort of grade, quite a variability in grades, but quite generally on the high side. And high side, I mean usually sort of north of 1.2, 1.3% Li2O. Whereas, and usually the mineralization is distributed quite evenly through the pegmatite, whereas these complex pegmatites have quite well-defined monomineralic zones. If we look at a PT diagram as to the formation of where these pegmatites form, you're looking at this area here where you see petalite spodumene, and I'll come back to the significance of this sort of phase diagram between petalites and spodumene as well, because that has quite important implications when it comes to looking at pegmatites and mining them. And it's just quickly pegmatite 101. Everyone sort of probably knows the general model. You've got a S-type granite, fertile granite, that as it crystallizes, evolves off sort of incompatible elements that migrate, form pegmatites away from the main granite body. And generally, your last pegmatites to form are your lithium-bearing pegmatites. And again, this just picture here looks at your complex pegmatites, generally quite well zoned. Not always concentrically zoned. As you see here, they may be asymmetrically zoned and sometimes very poorly zoned, where you've really got sort of quite coarse-grained material with some aplytic zones in between. The main lithium minerals that you find in these pegmatites are spodumene petalite, eucryptite, amblygonite, lepidolite, lithiophyllite, and zinwaldite. I suppose the most important two are spodumene, which is generally the one that everyone's looking for at the moment for inputs into your battery sort of supply chain. It's got the highest, well, not the highest, but one of the higher lithium grades. Your petalite often has more technical applications in the glass and ceramics industry. And spodumene is also used in the glass and ceramics as well, but I think most supply now is destined for batteries. Then you've got lepidolite, which has a lot of nasties in it, like fluorine, which when it comes to processing can be quite corrosive on the plants. And obviously your chemistry to clean that up and get a decent lithium carbonate would be quite difficult. But there are technologies around that can produce or can process things like amblygonite, lepidolite, and lithiophyllates and all that. This is what some of these minerals look like. They can be quite gemmy, in which case you get kunzite, or quite well bladed crystals here in a matrix of K-feldspar. Your petalite, quite grey. This is altered petalite from Rubicon, or quite sort of sparry and looks quite a lot like feldspar. Incidentally, this sample here, the little white lines that you see is actually spodumene within the crystal, and I'll show you a thin section of that shortly. This is what your lepidolite looks like, usually quite purple. You get some quite pretty textures within the pegmatites, and it can vary all the way through to sort of a grayish color. And then you get some other funnies where your lithium reacts with your host rocks and you get lithium amphiboles. And this is sort of just, it'll give you a kick when you're looking at core. You'll get a bit of a lithium kick, but it's not something that would be of any significance in terms of mining. And then obviously you've got a couple of other minerals that can contain a bit of lithium. In terms of why the PT conditions under which these form is important, your petalite generally forms at higher temperatures, and as these pegmatites cool, they tend to exsolve spodumene. Whereas if you've got a pegmatite crystallizing within this sort of spodumene area, you'll get primary spodumene forming. So obviously you do get pegmatites where you've got a mix of these two, and it makes processing quite difficult because your spodumene is quite a dense mineral, and the processing is quite different from petalite, which has quite a low density of about 2.4 tons per cubic meter. Spodumene is 3.2. And yeah, these are just some notes as to what how your melt chemistry impacts what crystallizes out. I'm not going to delve too deeply into that right now. These are just some photomicrographs from Highbury pegmatite by Thomas et al. We've had petalite crystallize and exsolve spodumene, and this is quartz here. So if you assay that sample, you'd get probably a lithium oxide grade of about 4.5%, which is petalite. Individual crystals of spodumene would be 8%. And obviously this sort of material would need to be milled quite fine to actually get your spodumene liberated. Similarly for petalite, this is that same sample again, a thin section of it. You can see there's quite a bit of spodumene in here, in amongst the petalite. And again, that's going to be a bit of a processing challenge. And yeah, you'd end up with two product streams, potentially with this. So, and then you've got very fine-grained squeezed spodumene quartz into growth. So this is very fine-grained. And there's probably a bit of eucryptite in there as well, just to make things interesting. And petalite as well, you get this incipient weathering. And again, what you'd have here is that when you start crushing a material or blasting it, your petalite's probably going to fall apart and produce quite a bit of fines. So it really just does talk to the need to understand your mineralogy, and it's on a sort of a microscopic scale as well. And this sort of early stage test work is quite important in any project. So if we come to Africa, Africa is quite well endowed with pegmatites. Currently, we produce about 70% of the global tantalite, 9% of global tin, with less than 2% of lithium supply. The significance of the tantalite and tin is that lithium forms in the same deposits as these tantalite and tin deposits. So obviously, the lithium remains quite an untapped resource. If we look at exploration, we've had quite a bit of work in West Africa, work in Namibia, you've got Zimbabwe, and then I suppose the big one in the DRC, where you've got Manono, which is, I think, the largest lithium resource reported to a code compliant standard globally. It's 400 million tons, 1.65% Li2O. And then you've got places like South Africa and Angola, which have pegmatites and potentially have lithium-bearing pegmatites, but haven't really been explored to any significance. If we look over time, if we look at the African context, these brown circles, we've got these, I suppose, geological terrains that host pegmatites well within these periods where pegmatites were generated. And so again, it really just speaks to the potential that we know Africa has. If we look at South Africa, I suppose the three areas that you would look at, you've got the Namaqua Natal belt, where there has been some exploration and a history of mining pegmatites in the past. You've got the Carpal Craton, where you've got these greenstones, and often you do find these lithium-bearing pegmatites in greenstone belts in Australia. All the gold mining jurisdictions, pegmatites were quite a pest. When they were exploring, they just found pegmatites in the core, and it was really something that was sort of logged and never looked at again. With this recent boom, all that old core has been hauled out, and they've been looking at that core from the gold mining exploration. So you've got the likes of Barberton, and you've got some of the greenstone belts up here that do have records of spodumene-bearing pegmatites. And then there's this Highbury pegmatite down in the south coast. If we look at the Namaqua Province, you do have quite a lot of lithium-bearing pegmatites out in the west, and a bit of a trend in the east. And this is really from Woolard. And there's quite a variation in the lithium-bearing pegmatites, from quite homogeneous, unzoned, to quite well-zoned pegmatites. The one that I looked at a couple of years ago was this Blesberg pegmatite that had been mined in the past for its beryl. It has quite spectacular spodumene crystals. They were found to be quite altered and not really carrying much lithium, and the exploration was stopped quite early on. But the work they did manage to find extensions to the west of the pegmatite, and it just shows that a lot of what we know about these pegmatites isn't what, so what you see is not what you get. There's a lot more to them, usually extensions to these pegmatites. You just look on the Carpal Craton, you've got this Green Hills pegmatite out in the Vredefort that does look, I know someone was exploring or looking to explore, I'm not sure where that got to, but it does look like quite a nice pegmatite, quite big spodumene crystals. You've got spodumene occurrences out near Swaziland border. and then a couple out here. But again, a lot of these were exploited for, I think, beryl and tantalite in the past. But really just like a side note that they contain spodumene. And then obviously just going back a couple to Highbury, I think there was some work done quite recently where they looked at where there was some drilling, but I don't think the results were too great, and I think exploration there has stopped. Then you've got the Damara origin in Namibia, it's Pan-African belt, and you've had exploration here at Rubicon and Helicon by Desert Lion, now Lepidico, and they were looking at mining the lepidolite from that pegmatite. I'm not sure where that project is at the moment, but I think not much is happening there. You've got the Oist belt. I see some of the African guys are here, and at Oist they're targeting the tin mainly, but there is a lithium resource that has been published along with their tin resource quite recently. And obviously there are a lot of other pegmatites within this belt that potentially could be mined for lithium, but haven't really been explored in too much detail. So, yeah, all these tin pegmatites would potentially contain lithium as well. We look at Rubicon, quite a well-zoned pegmatite. The resource was 8.8 million tons at 0.5% lithium oxide at a 0.2% cutoff, and the mineralization was largely lipidolite, petalite, and some alteration materials in the form of cookiite. Its surface expression was quite prominent and quite an easy thing to find. And a lot of these pegmatites with quartz cores do stand proud and often quite easy to find. If we look at the Oist Tin project up in the Northern Tin Belt, these are pictures from African's website and from MSc Ashworth in 2014. While these pegmatites can be well exposed, they can be blind. So again, it goes to this need to explore these belts in quite a bit of detail, and not just, if there's one pegmatite, there's usually more. And understanding the structural regime of these areas is also quite important, because they often come in as in echelon structures, and you can see some of the mapping that was done by African. You've got these pegmatite veins along a sort of quite a well-defined trend. In the south, some of the older pegmatites in Namibia, you've got Tantalite Valley, and that's around a mafic body on the edge of it in the Strange Shadow. You've got the Homestead Tantalite mine down here. And there are a couple of other pegmatites around there as well that they're looking at. But on the back of it, you can see, if you zoom in, you've got all these pegmatites here, and it's quite an unexplored area, but I'd suspect that there is a fair amount of lithium mineralization associated with those as well. Madagascan pegmatites, Madagascar is generally quite well known for its gemstones, but there is some lithium potential. Generally, these pegmatites are quite odd in terms of mineralogy, and the exploration to date, well, one or two juniors hasn't really yielded anything too newsworthy. We look at Zimbabwe, fifth largest lithium producer in the world. You've got Prospect Resources, who are probably one of the earlier guys to the market with their resource at Arcadia, and one of the biggest resources globally, 72 million tons at just over 1%. Their mineralogy is quite complex in that it contains petalite and spodumene, and they would end up generating two product streams. And obviously that has quite a big impact on the type of plant they need to put in. And yeah, and it's a series of stacked sills varying between 4 and 10 meters thick. We look at what these pegmatites look like. You've got this banded aplite that to the untrained eye could just pass as a lice. And then you've got your sort of more homogeneous pegmatite, coarse-grained petalite, spodumene bearing. And that's hosted in these Archean volcanics basalts. And then just, it's quite a simple zonation. You can see the grades sort of vary generally from 1 to 2% through the pegmatite with a bit of a higher grade core. And like I said, it's a series of stacked sill-like bodies. And this is just what some of their core looks like. You've got these apatite zones that generally developed in the footwall of the pegmatite, but you do find them sort of randomly through the rest of the pegmatite body as well. And then your sort of coarser grained petalite, spodumene mineralization within the main pegmatite body. So what you learn or see in the textbooks and what you see in the field, they can be two vastly different things. If we look at Monono, that's a Cabaran age pegmatite. And like all things, I think someone had a sense of humor by putting it in the DRC because DRC is a challenging country to work in, and they do have some of the largest copper, cobalt, and now lithium deposits in the world. You've got about 13 kilometers of strike in a series of pegmatite bodies. Exploration to date is only focused on this bottom sector, and this pegmatite was mined for tin historically. And basically mining stopped when they got to the fresh rock interface. So yeah, the exploration focused down in the southwest. Resource drilled is 400 million tons, 1.65% Li2O. And obviously there are some tin credits that go with this, about 800 ppm tin. If we just look at the thicknesses, you've got 260 meters in some intersections at 1.74% Li2O. So essentially the approach for mining this would be a bit like an iron ore mine because it's just so big. And pegmatites that you would sort of normally I suppose a junior company would explore 10 to 20 meters thick, sort of look quite insignificant when you're looking at the size of this thing. And these again are some of the textures. You've got these apatite zones, quite coarse-grained zones of spodumene and feldspar and quartz. And this pegmatite would be a spodumene albite type pegmatite. The spodumene, like I said, is quite coarse-grained. Quite big blades of spodumene here in the core. You can see quite long laths. You do get finer-grained portions. So it does look like you may have initially have had some petalite starting to form and then the sort of quartz exolved out and spodumene crystallized. But most of your spodumene is primary. Then you've got the Alta Ligonia pegmatite belt, which hasn't really been the focus of much exploration recently. Pan-African belt, also mainly known for its gemstones, but you do have quite a few lithium-bearing pegmatites, and these, I think it's the greens are your blues are your lithium-bearing pegmatites within this belt, and it's a metasedimentary belt. Your lithium pegmatites tend to be preferentially hosted within the amphibolites. And if you just look at the era mag, you can see these purple stars are your lithium-bearing pegmatites, and they do tend to focus themselves around the magnetic heights, which are your amphibolites. And that's a trend that you see throughout Africa. Most of these pegmatites have some sort of mafic association in terms of host rocks. The significance of that, I'm not too sure whether it's just a rheological thing or if there's anything more to it, I don't know. And Iron Ridge, just a bit of a West Africa, bring a bit of West Africa in. They've got quite a small resource at the moment, but again, you can see there are a lot of pegmatites around here. And I think more recently, some of their sterilization drilling for their plant, they discovered a whole swarm of pegmatites. So again, it's sort of a case of if there's an account of one or lithium-bearing pegmatite, there are often others around. And it's just understanding that structural regime into which they intruded, being able to target these quite effectively. It helps. And then obviously the dumps, like I said, Manona was mined for its tin. Obviously it was all weathered material, but there was a bit of fresh rock. And this is a photo from some of those dumps. And there is potentially some spodumene to be recovered there. And this is what these dumps look like. They sort of form little mountains. Kamativi, I think I did some work there a couple of years ago on those dumps, and that resource was about 25 million tons at 0.6% Li2O, and it's largely spodumene hosted. And then obviously there are the dumps at Uys, which I think the company a couple of years ago declared a resource on, but haven't heard much since. So yeah, I think, as you can see, Africa does stack up quite well globally. Places like West Africa are quite well located to supply into Europe and to America. You've got the DRC, where you could potentially get material through to Tanzania. And Namibia also very well situated, with transport infrastructure, and getting things to port is quite easy. And I suppose it just begs the question, what about South Africa? And these are just some of the guys operating in South Africa in terms of exploration. AVZ are the guys at Manono, Afriton are Uys, Zimbabwe Lithium are the Kamativi dumps, Iron Ridge are West Africa, Codal and Firefinch are also West Africa, Prospect Resources, Zim, Premier are Zim, Force Commodities, DRC, Lupidico, and Namibia. And then obviously there are quite a few smaller private guys exploring. So if you just look at how the resources stack up, you've got the grade, sort of a grade tonnage plot here. Size of the bubbles is the amount of contained lithium oxide. Roche sits out here. I suppose the closest comparison is Greenbushes in Australia, which is originally a tantalite mine, but also a big lithium producer there. And then all these pink bubbles are African pegmatites. Your grey blue are the rest of the world. And these green bubbles are just your unconventional, your sedimentary hosted deposits, just as a comparison. And Jadar also is quite a massive deposit. So I think, you've got quite a range from quite small to massive. So I suppose just the challenges in the lithium industry at the moment is, at the moment you've got quite complex supply chains that are quite geographically constrained. Quite a bit of price volatility over the last couple of years. The supply deficits forecast, and then it's just managing the ESG risks so that you can sort of attract the investment you need and just not irritate the people whose back doors you're mining on. The general trends, I suppose, in the industry and mining industry in general are slow carbon economic transition, which is driving, I suppose, this move to electric vehicles. Auto manufacturers securing supply chains and regionalizing them. There's potential change in the source of lithium. So I suppose if we start seeing these lithium clays coming online and the technologies to extract the lithium gets to a point where they can do it economically, those will be a major player. Obviously, your battery chemistries and that are also sort of have quite an impact as to what inputs go into them in terms of the likes of nickel and copper, nickel and cobalt, or whether it's lithium iron phosphate batteries. Your costs are dropping and your energy density increasing, and the lithium ion battery technology changes constantly. A few years ago, it took ages to charge a battery. Now you can charge these batteries pretty quickly. So you don't have to sit and sort of spend the night to charge the battery if you're traveling somewhere. And the range anxiety issue then sort of falls away. And then obviously just how public transport and how going green and how vehicles are used. And then I suppose it just comes with, you need that government support, I suppose, just to kickstart the industry. I suppose this lithium craze initially was based on anticipated demand. We're seeing that starting to be realized quite quickly. And there's, like, this growth is set to continue. Obviously, Africa is quite well endowed with pegmatites, well positioned globally. You've got a country like South Africa where a lot of the, I think, cobalt comes through to our ports, and it won't be a big step if you had a sort of battery plant that started processing, or chemical production plant that started producing some of these precursors in South Africa. So I suppose if you just look at some of the news, you have got this mega million company down in the Windy City, looking at producing batteries, well situated in terms of the auto industry in South Africa. South Africa produces a lot of the high purity manganese. So it comes to that earlier slide where we do have the infrastructure, we just need to develop it. And I think guys like NAMSA are starting to see the risk to South Africa's auto industry in terms of not keeping up with the rest of the world. At the moment, 3 out of every 4 cars manufactured here are destined for Europe. So if internal combustion engines do become a thing of the past, so will South Africa. And yeah, these are just some exploration notes. I'm not really going to dwell on those, but really that's my talk.
Good to go.
Okay, and hello from Perth, where it's 3:30 almost in the afternoon on a Friday. And I'd just like to thank Natalie, Lully and Nolene for inviting me back to the GSSA again to give a talk. I think the last one I gave was in November last year, but I do appreciate it. I'm Dave Lawley. You actually got the pronunciation of the name just right, actually, Tanya. That doesn't happen very often. I'm the Chief Geoscientist at IMDEX, but also have one of my colleagues from IMDEX on the line as well, Nolene, our Principal Geoscientist, and most of you would know Nolene already, I would assume. She's based in South Africa, so if you have any questions or want to follow up on any of the information that you see today, then please just get in contact with Nolene. So what is the mining industry's role in a decarbonised future? I hope at least that by the end of this talk, you'd agree that the mining industry actually has a very, very critical role to play in this. And just to pick up on a couple of the points that Lucy and Michael made in their talks, Lucy was talking about some of the problems that the industry has reputational-wise in the UK, especially with young people. Well, I can tell you, even living in Perth, a place like Perth, which is absolutely dominated by mining, the situation really isn't much better. So it means it really is a global problem for the industry. And then another thing that Lucy was talking about was just the sheer amount of things that are going on in the industry now. I've been following this sort of story for, I don't know, a couple of decades, I suppose, when it wasn't that politically attractive. But now, these days, it's almost impossible to keep up with it. There'd be a dozen new data points appear every day. And to Michael's talk, he made a couple of really good points. And one of them was that, apart from the technical aspects of lithium exploration, but one of them was that with ESG considerations, environmental being green, if you want to put it in inverted commas, really we're getting to the point where glossy brochures and statements on company websites are not good enough. Really, it'll have to be demonstrable and auditable. And the other thing that Michael talked on quite a lot, especially with respect to lithium, was geopolitical risk and supply chain risk. And I think there are a couple of things which I'm going to pick up on and expand upon in a sort of a more of a helicopter type view. I'll just skip over and keep going. So really in the short term, most of us are geoscientists. I take it on this call. That's just a plot there. And I'm really looking at battery metals as too limiting. I think I use the other term that gets bandied about, which is forward-looking metals. So if we consider 4 forward-looking metals, they're copper, aluminium, nickel, and zinc. The prices of those commodities normalized back to 100 in January 20, where everything dipped during the COVID crisis, which is still ongoing, of course. But just from an industry point of view, the prices really since then have gone gangbusters. They may have cooled off a little bit just in the very recent past, but I think we can expect them to keep hitting in that trajectory and be quite volatile. But it's interesting to just have a look at some of the reasons behind that. And this slide here, this quote, this is really, with this quote, I'm really cutting to the end of the talk. Sorry, I just need to move the video screen out. There we go. This is really cutting to the end point, but I just want to bring it up at the start because Tony O'Neill just riffed this off when he was giving a talk at IMARC, a virtual talk at IMARC late last year. And he made the point, just when someone asked him a question in a forum, just like this one actually, where he said, we need to get to the point where society views mining as necessary for the well-being of its own existence. And I thought that that was just a terrific quote and really summarises where we need to be as an industry and how we need to be perceived. For those of us who have been in the industry for a long time, it almost seems that that could ever be the case. But I've got another quote down below there from Data, who's a futurist, and he makes the point that any credible idea about the future must at first seem ridiculous. So the conclusion from that might be that maybe we will get there. And just to add, I suppose, to what Tony O'Neill was saying about the industry, but from Anglo-Americans' point of view, just while I was waiting for this conference to start, I was looking at the Mining Journal, and just today, just an hour ago, there's a story in there about Anglo being powered 100% by renewables in South America. So it's a very, it's a really lively topic that just changes daily at the moment. I think another really important aspect of this whole discussion is that 3, 4, 2 years ago even, the debate and the arguments were taking place at a political level or at a governmental level. I think you could say now that the train has left the station in a way, and that what's happening now will be driven by the industry itself, society without government intervention, and with the funds that provide funding into our industry to get on with the job. So that's been quite a dramatic change. Now, just some context around decarbonisation, a lot of written words there, but I just want to pick on a few of them. Just sets up what comes after this. If you look at the 120 countries, an increasing number of companies globally have committed to achieving net zero by 2050. That really has an amazing set of knock-on effects. And in fact, the International Energy Agency are saying that if we're going to get anywhere near that by 2050, then things need to start happening now in the next decade. And we're already starting to see some of this roll out with the change of presidency, for example, in the United States. Joe Biden and his presidency is going to put an unbelievable amount of money into trying to get to some sort of carbon neutrality. And we have consultants like Wood Mackenzie throwing numbers around like $1 trillion of investment will be needed in key energy transmission metals. There's a list at the bottom there over the next 15 years to meet the growing demands. You look at numbers like $1 trillion, $1 billion, $1 trillion. What is $1 trillion? I've got some quotes later on that have numbers even higher than that. So it's an unbelievable challenge. Bringing it back a little bit, there is this huge global story going on. But just directly in our own industry, here's a quote that was taken just last month out of a newspaper, the Australian newspaper, where they did a survey of global mining executives, and most of them think that mine sites will be fully electric within 20 years, and 60% think that the next generation of any new mines that built will be fully electric from the start. Now, that has a decarbonisation aspect to it. Especially if you go back to the previous story about Anglo going carbon neutral in South America. But it also has other knock-on effects here. And Graham Stanaway, who's based here in Perth, was saying apart from the energy, but apart from cutting energy costs, the fact you don't have vehicles generating heat and diesel fumes underground could actually slash the cost of ventilating underground mines by 40%. But you could push that even further, because if we're doing this, it would actually change the mine design and may allow us to get at resources which previously would be unable to get at and mine economically. So that has all of these knock-on effects, which are all beneficial. And by the end of this talk, I think you understand why being able to get at resources that we can't mine at the moment is really a very important problem for the industry. A couple of my favourite people to get up in the media and talk about mining and resources. One of them is Robert Friedland. You may not agree with everything he says, but he always gets you thinking. Sort of not in our industry, but getting into our industry. There's another one, Elon Musk. You know, people diss this pair quite a lot over the years, but they're not to be mucked around with every time they get underestimated. They come through. But we've got Friedland here making a few comments. He doesn't call it a super cycle, he's just calling it the start of an unprecedented and revolutionary cycle. And really the key thing there is but the rise of green energy and the electrification of everything goes way beyond batteries and cars. But when you start to think about that, and the previous speakers have hit on this, is where are the materials going to come from? And I have some more and more of these sobering type numbers coming up. Another quote here from Friedland saying the 620 million tonnes of copper that the world has already consumed in the last 100 years will be needed in the next 15 years alone. And that rate of copper consumption will keep going up. So this is driving some strange behaviours in the industry, including the balkanisation of the supply chains, as Friedland calls it. But at the same time, we've got Friedland wanting to head down the supply chain route, so to get from mining down into the manufacture of batteries, electric vehicles, etc. And you've got Musk worrying about the same thing, but from the other end of the spectrum, manufacturing electric vehicles, but trying to secure supplies of nickel and lithium for his batteries. So these are moves in the industry which would have been unheard of, really, or not thought about even just 5 years ago. If we zero in a little on electric vehicles, and there's a graph there really, but the reason I put that in there, that just goes to 2020. It's really just showing the start of the start, or barely up to the starting line there for what's going to happen. But again, there are some numbers there to the left in the PowerPoint. Things like by 2040, apart from the number of electric vehicles, there will need to be 12 million charging points to charge the electric vehicles, and each of those consumes about 10 kilograms of copper. Now, there's only about 1 million charging points in existence. They're talking about having 12 million. As was mentioned before, the UK government setting a target replacing all of its 31 million internal combustion engine cars with electric vehicles by 2050. And there's another little quote there that each electric vehicle requires 4 times as much copper compared to the conventional or an internal combustion powered vehicle. So we've got things like that going on just with batteries and vehicles alone. This is another graph which I just took out of The Economist earlier this year. And this graph is, if you look at it and think about it for long enough, is truly astonishing. It's representing a scenario, high electrification scenario in the United States looking forward to 2050. And if you look at the relative balance of contribution in gigawatts of power from the different sources there, you can see that solar and wind are picked, at least in one scenario, to be contributing an enormous amount of the power that the United States requires. They are truly mind-boggling numbers. And how are we going to get there? How on earth are we going to be able to supply the materials to enable that to happen? The electrification of everything, as Friedland would call it. Even just today, we've been talking about lithium and copper, but it's important to realise that these forward-facing or future-facing metals is quite a broad basket of elements that we're looking at, and there's a list of them on the left-hand side there. This is a really good table, actually, because it gives you that full list, and then it gives you the applications across the things that people typically think about when we're talking about these problems, so electric motors, electric vehicles, but of course there's solar photovoltaics, battery, wind generation, so the generators and the wind turbines, perhaps even carbon capture and storage. LEDs even gets a Guernsey, light emitting diodes gets a Guernsey there. This alone represents an enormous requirement for all of those elements that are over on the left there. But then we also need to not forget about infrastructure. So at the same time as we're talking about the electrification of everything, most of the world is also talking about upgrading their infrastructure. And so infrastructure alone places an enormous requirement on the resources industry to deliver all of those sorts of things that are listed there over on the left-hand side. So iron, of course, which is obviously left off, but more aluminium, more zinc, more copper, more nickel, etc., etc. On top of that, when the industry is faced with the requirement to deliver all of these, and again, remember we're talking about non-gold here, but all of these other future-facing metals, we have the rise of the ESG considerations, environmental, social, and governance at the same time. So the graph there on the left there shows inflows into ESG and sustainability-themed trading funds. And I'll put a note there at the bottom there, look at the scale that's really, so the scale, the dollar scale is in billions, and the time scale there when things are taken off only just late last year. This is only getting rolling now. So we have the dual problems of needing to be able to, well, as we say, find, define, and mine to obtain the various elements that we need to enable all of this to happen. But at the same time, we need to be addressing all of these ESG concerns. So we need to be looking perhaps at the ability of things to be recycled, social problems, ability to rehabilitate sites, what waste is being generated, what sort of tailings and disposal you require, etc. Because if you don't have a lot of those things sorted out at the start, then you're not going to attract the funding that you need. You could say that exploration has a lot more dimensions, and mining is going to have a lot more dimensions attached to the economic of a program, much more than, say, just stripping ratio and head grades and disposal facilities. So just really driving along on this theme for a little bit longer, and I couldn't resist quoting Friedland again after he published this article called Geologists are the Gods of Mining. It's always a good wind up for our mining engineering comrades. But look, he makes some really interesting observations in this article. And one of them is he links the ability of blockchain technology to track the supply chain of the various components that get used. So right through from where they've come from, where they got processed, where the end destination is. But what that means is that eventually, and I think we're going to see this sooner rather than later, that there will be a price put on carbon, a global price put on carbon. And even countries, even where I am here in Australia, tend to ignore that or will get penalised by it by entities like the European Union, for example. So I think it will be a reality before too long. But it means that the existing situation of having a single price, for example, for copper, will no longer be the case. The copper will be priced by the ESG components that go into producing it. So we'll end up with a situation where we have you could call it a carbon modified price per unit of whatever it is you're trying to sell, which in a way, and I think the big base metal companies are onto this, and this is one reason why they're looking to go carbon neutral in a lot of their mining operations, because they'll be able to offset a lot of these costs when the copper, for example, starts to get priced with respect to that. This is going to be a really revolutionary thing that happens in the industry. You just can imagine an Apple, for example, just to use Apple, because they're likely to do this. If they're going to go and source the nickel and copper, for example, then they would most likely want to buy the greenest nickel and copper they can get their hands on and pay a premium for it. So if you're able to generate copper and nickel, just to use those two as an example of the low carbon input cost, then you'll get a better price for it and be well worth it. But what it does mean for our industry, and I think, is we'll have a whole new measurement system to deal with when we're optimizing our mining operations. And in fact, as if our job wasn't hard enough, we'll be needing to look for deposits and resources that we know that we can extract with the lowest possible carbon footprint, as though it's not hard enough as it is to find and mine anything at the moment. To touch on a little bit more about a topic that Michael brought up when he was speaking as well, just about lithium. That's just a really quick summary of the geopolitical influence on the supply chain for a lot of these really important elements. So it's not just about the ESG considerations and being able to find the things in the first place. A lot of the supply chains are concentrated in various parts of the world, which really, especially during COVID, where people are really looking at supply chains now, doesn't make the world feel very comfortable. So this will be another driver in the development of some of these resources in places where they're not typically mined or refined at the moment. The other thing is when we look at a lot of these metals is that where they're mined and where they're refined into a useful product, as Lucy was touching on lithium early on, it's not necessarily the same thing, but they still creates a supply chain issue. Now the red ones, or the pink, purple, apricot coloured ones there, are components where really there's a very strong geographic concentration on where the metal is mined and or where it is refined. Some of them are one and the same thing. So for example, rare earths are both mined and refined, dominated by China. Cobalt, something you'd be well familiar with, mined dominantly in the DRC, but refined into a product that can go to batteries in China. Lithium, which was touched on, Australia, it's the largest source of lithium in the world, but really most of it gets turned into lithium carbonate and batteries in China. And some of the other components, they're the same thing. For your part of the world, they're platinum, which has some platinum, palladium, of course, but platinum, which has some other uses. When we look at forward-looking metals, of course, is concentrated, but that's mining and refining in South Africa. Things that probably are of less of a concern are probably zinc and nickel. But the odd one there is Chile to have in a table like that. I gave it a slightly different colour because, Chile supplies 30% of the world's copper, and the supply-demand situation is so tight that if they're continuing off the political problems that were starting up in Chile near the end of the year before last, just prior to COVID, where there was a lot of political unrest in Chile, if that was to break out in Chile again, given what's going on with the tightness in the copper market, that can have quite a catastrophic effect on the copper supply chain because it is so tight. So there were some comments about the supply chain, but what about now? That was the here and now. But looking forward here to just four of these metals: copper, nickel, cobalt, and zinc. And these are Glencore's estimates of what would be required on an annual basis in 2050 compared with 2019. They're estimates, of course. But the quick summary there is nickel and cobalt. We're going to need 4 times as much nickel and cobalt per annum in 2050, and twice as much copper and zinc. Sometimes the numbers get quoted on graphs like this can be a bit confusing. The copper there in 2019 would include recycled input, but you could call mined output about 20 million tonnes a year at the moment, heading up towards requiring at least 40 million tonnes per annum in 2050. I'd argue, being a geologist myself, that it's easier to turn up the wick and generate more nickel and even cobalt, even at those levels, than it would be to generate more zinc and especially more copper. There are lots of reasons behind that, which I won't go into today, but I'm going to expand on the copper story as we move on. We can look at where investment's going now. So what is the industry doing around this at the moment? Well, one of the things that's seen play out right now is a lack of capital investment in mining existing mines. It's gone on for the last 5 or 6 years, and that was the discipline that was brought into the industry after the last crash. People have been very, very conservative with the deployment of capital. Now we're in a bit of a bind because of that starvation of capital in our existing mining infrastructure. It's quite difficult to pick up the production quickly to meet demand now. But if we look at not so much on the mining side, if we come back to the exploration side, this is some data that was published by S&P just yesterday, I think. So like I said, just the number of data points coming to the market is just amazing every day. So on the left is a report from S&P about existing projects and the way that looks in the rearview mirror. On the right there, that graph is a reflection of the number and the quantum in dollars of raisings that occurred last month, right, in March. So a couple of comments on that, just over back on the left. So we were working on 364 projects around the world in March, which was up on its peak from January in 2020, so that's pre-COVID, which is a good thing. But that number was really dominated by gold projects. 250 of them were gold projects and only 47 copper. So the industry was going really well. But if you look at the raisings there, that raisings plot, the gold financings are in orange. But if you look at the size of the specialty commodities, lithium, etc., and base and other metals, the size of that, the amount of money going into non-gold metals, and that number there, if you look at it, would be something like about $3 billion, something that raised in a month, is absolutely extraordinary. It's showing that the industry, the exploration industry at least, is rapidly pivoting around to try and provide more supply of these metals. What would be the outcome of that is an interesting thing to think about. So copper, let's come back to copper, and we'll look at those raises, and people all of a sudden massively interested in copper, as well as cobalt, zinc, nickel, etc. John Steen at the Bradshaw Research Initiative in Minerals and Mining at the UBC, he has a good quote there. It says, copper is the canary in the coal mine because it's the carrier of electricity. But he goes on there to make the point that the world's miners are struggling to replace the copper that we produce now, right? And this is a really important point. This is a bit wordy, but again, I'm just going to pull out a couple of comments here. This was published last month. So, yeah, if we did nothing and we just had a look at the graph that showed the capital investment going industry, we've been undercapitalized the last 5 or 6 years. If we look at our current 20 million tonnes, let's just round it off. If we do not much, then with mines closing, we'll be down to 12 million tonnes by 2034, which would be an absolutely disastrous situation. If we just look at the EV market and assume that by 2040, 30% of the world's passenger cars are electric, that's actually 500 million electric vehicles. These numbers are just absolutely mind-boggling. And if you take each electric vehicle contains, or if you accept it contains 85 kilograms of copper, that's 42 million tonnes of copper. So just to electrify 30% of the world's EV fleet in 20 years would take twice our current annual production of copper. Just unbelievable. If you further look at that, and then we had the prediction from Glencore and other people saying that by the time we get out to 2040 or 2050, we'll be needing another 20 million tonnes of production on top of the existing 20. So not only do we need to maintain the 20 we're doing, we need to add another 20 million tonnes. So you round out all the numbers, that's another 1 million tonnes of production added on per year for the next 20 years. So we need 2 Kamoas a year to come online. We need 2 Colorasis to come online a year. That is a very, very sobering thought. Just some more numbers here, people projecting around copper demand. And that's a graph there that's just showing just this is only going out to 2030 this time, but it's just showing, and I think it's quite conservative, but the point it's making is that the green electrification related to copper demand by region, showing it going up by 5 million tonnes of copper per year going out to 2030, but it's accelerating by the time it gets to that point. But it's saying that last time around, there was this sort of a massive capital investment globally. It was driven by China, but we're heading into a situation where the EU, US, China, and ROW, which is the rest of the world, will all synchronously be trying to go green and build up their infrastructure. Infrastructure is actually not included on that graph. And then here's these laws of big numbers, if you like. We estimate that nearly $16 trillion would have to go into green-focused infrastructure to achieve decarbonisation targets. You know, I look at that and go, what is $16 trillion? I mean, we should be looking at this and think this is an excellent thing, an opportunity for our industry, but man, we've got to step up to the plate if we're going to get anywhere near being able to do this. And this is just another quote from Friedland, just came out just this week. I couldn't resist putting it in. He always says things which get people going, but it's related to this requirement for this immense expenditure to improve the electrification infrastructure. And he makes the point here that if everyone gets home in a Tesla at 5 o'clock and plugs it in, it would fry the grid. Further making the point there that even with Biden talking about investing $100 billion in US electricity, it's a drop in the ocean, really, compared with what's actually required to be able to move electricity, move energy around in that form efficiently to where you need it. Now, we've got some challenges, and I've just stolen a few slides from some other people here. So here's something we know as exploration geologists, that why does all this matter? Well, copper deposits are hard to find. You know, and the rule of thumb that we've learned over the years that you need to test 1,000 prospects to get one tier 1 discovery. So that's a sobering number. More familiar with that. Here's a graph that links the price, the commodity price, with production. And this is a really interesting graph because the time period there is over the same. The red bar illustrates the same period of time. So there's the price of copper going back from about now to 2006, and that's the total mine production. The amount of time it takes to find and get a largish copper mine into production takes so long that's actually disconnected from the price. So a lot of the analysts here talk about the increase in the copper price, which is going on at the moment, and maybe over the next 3 or 4 years, will drive production. I don't think it will. Right? It needs some other type of thinking to fix this supply gap. You cannot rely on price alone. And then if we do find something and want to bring it in and mine it, then we have, again, the ESG considerations. And this is just a plot I adapted from Anglo. And I'll just talk about it. It's talking about what's required to generate 40 kilograms of copper today, in 1900 and some point in the future. And that's, again, it's another sobering plot about what we're going to do to bridge this supply gap. Again, just talking about copper. So to generate 40 kilograms of copper in 1900, you have to generate a ton of waste. 1 ton of ore to get 40 kilograms of a ton of waste, 3 cubic meters of water and 10 kilowatt hours of energy. The situation today is because of the drop off in grade is you need 8 tons of ore to get you 40 kilograms at the same time. You need to move an enormous amount of waste, 24 tons. You consume twice as much water and 16 times as much energy. So this is obviously a zero-sum game. We can't keep relying on just making everything bigger to be able to supply the copper the world needs, especially taking into account ESG considerations. So we need to do something different. We just have to do something different going into the future. Now, this is a bit of work that Rick Valenta and his cohort did as part of the Complex Ore Deposits initiative at the Sustainable Minerals Institute at the University of Queensland. And on that table, what they did is they looked at the top 40 undeveloped copper resources in the world. And there's the list down the left-hand side there. You'll be familiar with a lot of them, I have no doubt. But there's actually 500 million tons of contained copper on that list. So enough to meet 20 years supply of copper at our current consumption, more or less 20 years if we assume we're going to use 20 million tons of it a year, our current rate. But on the coloration in the graph there illustrates what are the problems, what's stopping these things being brought into production, because we are going to need things like this as time goes on. And they're color coded, so the dark colors represent a high risk and the light colors are low risk. So the interesting thing about this when I looked at it was if you look at grade is not the problem. It's a whole lot of things apart from grade. So water availability, tailings management and the ability to store tailings, variability, so geotechnical type risk, geosensing type risks, legal issues, local communities, etc., arsenic content, and the infrastructure, so the infrastructure intensity that's required to bring these things into production. So we have them, but we just can't get the things into production because we haven't quite know how to crack this one to get them going. Another way to sort of think about that problem is when you think about reserve conversion, so converting resources to reserves. Even when we do find something and it doesn't suffer, if that's the right word, from some of the problems in that previous table, and even then only 50% of resources make it to reserve status. So something we know we can mine economically. And that's just that's a rule of thumb suck average taken over time. But one thing that's happening now with the global mining codes is that there's a movement in JORC, but also the global umbrella organisation looks at all of the mining codes to start incorporating into resource estimation additional modifying factors. So we've always had the modifying factors going from resources to reserves, so economic marketing, things like that. But now now there's a drive to actually publicly list modifying factors on the resource calculations as well, like, for example, carbon intensity. So if we're not collecting the right information at the right time, we really run the risk of actually stranding more resources because we haven't properly taken those factors into account. This is a whole topic on its own, and it's something that I'm going to give a talk about in the future in conjunction with someone I know that's working very closely with these committees. But it's something we need to be very, very aware of, because it will be upfront. It will be an upfront consideration, additional consideration. So if we think about these stranded copper deposits, just looking at copper alone at the moment is a bit of a surrogate for the other resources that we need as well, the other elements that we need. So, you know, we know that finding new deposits, finding new resources is unbelievably difficult. So one thing maybe we can think about is really trying to unlock some of these stranded copper deposits. So deposits that we can't develop a resource on, resources we know about that we want to turn into reserves. What can we do about that? So perhaps one thing that we could do is going back to some of these and investing quite a bit of time and money to reacquire data. So look at the existing measurements, start to collect more data, more important data, which address some of these non-grade issues, but at a much higher spatial fidelity, which then could allow us to look at optionality around mine design. We might be able to get some of these things into production. What that would open up for us is some low capital precision mining strategies, and really take account of some of the new technologies which will be coming down in the mine design. I suppose, going back to the start of the talk, a small example of that would be the electrification of equipment underground and the lack of requirements for ventilation to cope with diesel particulates, etc., and even removing humans from harm's way underground possibly starts to open up these precision mining strategies. But if you're going to do that, it means that the amount of data you need and the spatial density you require from that data probably doesn't exist with whatever the deposit is that you're looking at right now. It will take a lot of additional work. But I still think it's something that we really need to be getting on with. Again, keeping up with that theme, and this is just a quote or some comments from Rick Valenta again, who was the prime author on that paper. And he's making the point that just making things bigger and bigger and bigger just doesn't work. And the quote that I've put there in bold, if you're going to take our existing approach to get copper production to 45 million tonnes a year by 2050, but with reducing grades, you would have to produce 9 times the tonnage of copper tailings that we produced in the 20th century. So clearly, that is not going to happen, even if we could find these large, low-grade deposits. So we really need to refresh our mindset and think our way through it. I'm going to finish up soon. I don't want to take too much of your afternoon tea, but some things that are going on in the industry, the way people are thinking. So this is just a slide from Sally Goodman, the Chief Geoscientist at Newmont. People now start to try and think, well, how can we get more efficient at these things? And she made a really good thing, a really good point, thinking about exploration and exploring in near mine environments. That perhaps the people best equipped in that are sitting under, well, if you're a certain age, are sitting under our noses, playing games, collaborating online, being competitive, consuming multiple spatial, three-dimensional data sets in real time and working their way through a problem. Maybe they're our next generation of explorers. I thought that was very insightful. And some other slides here. This is from Vanessa Ligford at BHP, I think also Chief Geoscientist, maybe Nine Business. But this requirement for more information and a high spatial fidelity in that information related to ore body knowledge to unlock, again, optionalities and efficiencies in the mine feed. And I think, you know, these things hand in hand are a little bit of the solution, a little bit of the way to change the path to get some of those resources either into production or to find more of them. I'm just going to skip over a couple of slides now because we're near the end.
5 minutes.
Yeah. So look, if you want to talk to us, what is IMDEX cannot fix the world. It's not our job to do it, but we can certainly help the industry. And we separate it into 3 things there. We're working on technologies to help people test more targets more quickly and more cost effectively, which means that you can drill out a resource in a lot more timely fashion rather than a 5-year drill program. Maybe it's 2, so you get your resource into production much earlier, and also tools to increase mine productivity. I'm just going to skip over some of these. You can always ask them about this and just come back to some takeaways. So we've all heard this before. We've been in the industry long enough. This time it's different. Is it? I don't know. I can't answer that. As soon as you make a prediction, it's bound to trip you up. But the third comment there, that maybe it is different because this super cycle, as Friedland calls it, may be immune from other sector downturns, because the requirement to decarbonise in the world, I think, would probably get underwritten no matter what's going on in other industrial sectors in the global economy. But that being said, who knows? Carbon pricing built into the relative pricing of metals, I think, is an amazing development in the industry. I think something that the industry will need to work its way through. Precision mining, I really think, and technologies which we don't even have operating in the field yet, are really the only way we're going to start to unlock enough of these metals that the world is going to need to decarbonise. But there are some things we still need to keep in mind. I mean, if you look at that $3 billion of raisings in 1 month to support largely non-gold focused programs, are going to straight away run into constraints around us having drillers, drill rigs, targets to actually test and go and drill, and geologists to prosecute. And that's purely from an exploration side. I think looking at the global situation, I think one red herring, apart from pure economics, is resource nationalisation, and lots of nations looking at their supply chains, maybe balkanisation of supply chains, the world splitting into trading camps when the desperation to get hold of some of these commodities starts to increase, could have quite unpredictable outcomes. I don't know what could happen there, but it could be good, it could be bad. And then the last thing I've got there is, can our own industry rise to the challenge? Typically, our behaviour in the past has been, when a lot of money has been raised to encourage greenfields exploration, then a lot of money typically gets wasted and everyone gets disillusioned and walks away and goes and put their money into Bitcoin and dope stocks instead. So there you are. It's up to us, actually. Our role as a mining industry in the decarbonisation of our world comes back on us as an industry. And I've just repeated Tony O'Neill's quote there because I think it sums it up beautifully. And then I've just quoted Friedland down there again, who sort of makes the same point, that really the transformation of all of this relies on miners, period. And that's it. Thank you.
I think some of the things that have been said already today are something that I want to build on, because we need to evaluate how clean is green as we go forward. And Dave Lowry has given us a lot of food for thought, and I hope that this adds to it. So I want to point out that materials have been important to man even before Homo sapiens. So early tools found around Lake Turkana actually date back to 3.3 million years old, and that's actually older than Homo sapiens by about 1 million years. And early trade actually in Europe was based on such material that was suitable for cutting tools and stone axes. And for example, in Northern Ireland, porcelainite, a tough hornfels, was sought after for material for Neolithic axes and tools. And production of this is thought to have started about 4 millennia ago. And it's likely that these rough artifacts were produced on site, but then importantly, they were also exported to the UK and Northern Europe. So there has been quite significant trade in materials for a very long time. Now, from about 3.3 million years ago, and for millennia afterwards, the mineral extraction industry was essentially limited to the manual collection of specific rocks that were selected for their particular physical properties and general hardness, generally with an ability to form blades, points, and edges. And the process that was used to turn those rocks into fit-for-purpose goods was simply physical processes such as percussion, grinding, and polishing. The earliest mining in Southern Africa seems to be for a slightly different purpose and comes from the Lion Cavern in Swaziland, where about 4,300 years ago, long before the days of Cleopatra and Helen of Troy, hematite for cosmetics was being mined to beautify men and women who even then recognized that nature needed a little bit of help. So moving from the Stone Age to the Bronze Age, tin was literally responsible for changing civilization. Some enterprising metal workers at the end of the Stone Age discovered that the addition of a small amount of tin into molten copper resulted in a new alloy. It was harder than copper and also much easier to shape. And the discovery was so revolutionary that the Bronze Age was born, a name given to any civilization which made tools and weapons from this alloy of copper and tin. So important was tin in that era that the secrets of its trade were actually quite closely guarded. And the ancient Greeks spoke of the Cassiterides, or the Tin Islands, which were believed to lie off northwestern coast of Europe. These mysterious islands have never been identified and actually probably never existed. All the Greeks knew was that the tin came to them by sea. It's likely to have come from northern Spain or from Cornwall that Lucy Crane was talking about in the first talk. Sorry, I'm having difficulties getting the next slide. So in Nigeria, we have exquisite bronze artifacts that come from 3 sites, and they've been dated to the 9th century AD, and these predate the more famous Benin bronzes, with early sculptures dating from the 13th century. Then we get to the Iron Age, which may have started at a very small scale, about 3,000 years before present, progressively developing its regional widespread use about 1,000 to 1,200 years before present. The duration of the Iron Age varies depending on the region under consideration, and it extended from Europe to the Near East as the Bronze Age collapsed in the 12th century BC. Then we move to the steam and industrial revolution age. By the 18th century, there was the advent of water power that enabled mills to drive machinery, followed by the use of fossil fuels, and steam power that not only caused an industrial revolution in manufacturing, but also with the coming of the railways, facilitated movement of goods that was distributed to a wider customer base than had previously been possible. So we started in the 1760s with James Watt's steam engine, through to the power loom in 1785, and then to the Stephenson's rocket, which was our first a time when we could add to shipping the ability to move material around by trains and also by canals. And then we come to the modern age, the age of petroleum, that refers to the increased use of petroleum in products and fuel. And clearly, the bottom picture shows traffic in India, and it clearly illustrates that we are causing a lot of pollution in the current age, and we're all very well aware of the fact that we need to do something about climate change, and we need to do something to contribute and act now. And the global community agreed in 2015 with the Paris Accord to try and limit climate change to no more than 2 degrees, or ideally 1.5 degrees centigrade temperature increases. And this sets targets for the world to meet in order to reduce greenhouse gas emissions. So clearly, over time, there are changes in uses with our requirements for energy generation from the elements that we used in wind power generation through steam to the petroleum age, and now as we go into what would it be called, the technological age, I'm not quite sure, but you can see that there's a vast increase, as has already been mentioned, in the elements that we use. So the point is that metals and materials have been important to man through the ages, whether porcelainite in the Stone Age, tin and copper in the Bronze Age, iron in the Iron Age, or coal that fired the first industrial revolution. These were all critical materials of our time. Now, in the modern era, as we try to develop a low carbon economy, the critical metals for our economy have changed. And these aren't fixed, but they vary in time, and they vary from place to place as well. For example, if we look at a criticality list that the British Geological Survey compiled in 2011, we see that those elements in red, such as antimony, platinum group, mercury, tungsten, rare earths, etc., these was regarded as critical metals, critical to our high-tech industries in the UK, whereas down at the bottom of the list in green, with no shortages, were things like vanadium, lead, etc. If we just go back to that a moment, at the top of their critical list in 2011 was antimony, platinum, and mercury. And then as we go to 2012, it had changed to rare earths, tungsten, and antimony. And then on the right-hand side, by 2015, it had changed to rare earths, antimony, and bismuth. And if we look at a compilation put together by Roger Skirrow in Australia, albeit in 2013, what it illustrates is that it depends where you are, whether you're in the UK, the United States, Japan, or Australia. What you regard as critical is dependent on what is important for your economy. And so criticality varies from time to time and from place to place. Now, if we look at the changes through time, 50 years ago, as shown sort of in the periodic table at the top there, perhaps only 20 to 30 elements were vital for everyday life. Whereas nowadays, half the periodic table of elements, as Lucy Crane mentioned, is vital to a smartphone that many people worldwide carry every day. So the number of elements in routine use grew through the 20th century from 12 elements at the beginning of the century to almost every element being used by the end of the century. So what is criticality? It's important to assess what that is. And I'm using some graphs here of the platinum group metals, platinum, palladium, and rhodium. because a commodity is critical if it is both economically important and has a high risk of supply disruption. So the scarcity of the commodity is illustrated here, because more than 90% of platinum group elements come from 3 countries, South Africa, Russia, and Zimbabwe. And looked at from a North American point of view, South Africa might not seem to be the most stable of countries. So where's the next best source of the PGEs? Oh my goodness, it's Russia, even worse news. And where's the next best? Well, Zimbabwe, and I don't need to go into the details there. So there is a scarcity of the commodity in terms of a world supply, because 90% of the PGE come from these 3 countries. But what is important is that very little of this platinum is used in the country of origin. And that if that were to change, the rest of the world could face a supply shortage. Now, that happened with the rare earth elements. Prior to the 1990s, as has been mentioned already, rare earths were produced from several countries, including the United States and Australia. And then increased production from China in the 1990s undercut world prices and resulted in the previous producers closing their operations, leaving China as the dominant world producer. Then in 2010, China announced that it would cut its export of rare earths as they plan to use more in their domestic market. And that drove up the prices and raised concerns worldwide about the future supply. You see from this slide how dominant China is in resource richness, but in spite of the huge metal resources in China, it's not self-sufficient, and it imports crude petroleum, iron ore, coal, copper ore, cobalt concentrate, and other things, not necessarily because it doesn't produce in its own country, but it's just the major growth in the Chinese economy that is driving the need for imports. So criticality can also depend on the fact that many of our elements needed for technology are critical because they occur in ores of other elements, making their availability somewhat sporadic. And I use the example here of germanium, which is vital in the making of semiconductors. There's only 2 mines, Kipushi and Sumab, where really germanium occurs as its own mineral. Otherwise, it's mainly produced as a byproduct of mining zinc from salarite. And if zinc is in low demand, then germanium output might also be compromised. So here you see a picture. Sorry, they're grass cutting outside. I hope that doesn't compromise the quality of the sound. Here you can see a picture taken from one of my students, MSc, Caitlin Stewart, where we're looking at the mineral rhenurite together with some copper ores in polished sections. So criticality, sorry, I need to stop this noise. Sorry, I don't know if that will work. So criticality depends on technology. And as I've explained, critical metals vary from place to place and time to time. And they depend on new technological developments. And new technology might require new metals, or it might, a frenzy of exploration for that particular metal might produce an oversupply. So critical raw materials are shown here. And I think, as Lucy said, we're preaching to the converted here, and virtually everybody has a concept of what we need. So having looked at all those previous tables, what are the current critical materials that everybody agrees are critical? And that includes the rare earth elements, the platinum group elements, and indium. And most of the people who compile these tables also include a range of other elements such as tungsten, germanium, cobalt, niobium, etc. So everybody is aware of the rare earths, but what I want to focus on now is how green is the mining of some of these commodities, which Dave Lowy has already mentioned earlier, because the president of South Africa, Jacob Zuma, has been known to say that we should go to solar energy because the energy is completely free. And I think Lucy touched on this as well, in that there's no understanding of what goes into producing the components that go into our green materials. So as everybody knows, the rare earths are a group of 15 elements which are used across an enormous range of modern applications, including in strong magnets for wind turbines, in batteries in hybrid vehicles, and as phosphors in energy efficient light bulbs and televisions, etc. But the thing is about the rare earths, is that a lot of processing is required for these rare earths, because of these 15 elements, many of them occur in the same mineral. So it's not like zinc sulfide, where you've got a simple sort of zinc plus a little bit of something else that it's easy to process. You've got to go through a whole series of stages to produce these rare earths. And it's a very complex series of processes. And that's only really done in 1 or 2 places around the world. It says it's done in China, and it's done in Malaysia. Now, the picture on the top right there of rare earth production in China caused an article and news by the British Broadcasting Association in the UK, saying what a mess this huge toxic lake was as a byproduct of rare earth production. But what they didn't point out was that in Bay and Obo here, where you have this 11 square kilometer waste pond with sludge that contains elevated concentrations of thorium, what they didn't realize was that it was also producing iron. But this is an issue, the fact that rare earths often come with some thorium or uranium bearing minerals, and Linus, who are mining in Australia, decided to process their rare earths in Malaysia rather than Australia, where they would be mined, because it received tax incentives. But Linus is now locked in a dispute with the Malaysian government over its advanced materials processing lamp plant, because of the slightly radioactive bearing waste that is a consequence of this processing. And this has also received quite a lot of negative news, and is also a cause for protest by the local people. So there are issues in producing these metals for the green technology. Let's go to the PGE now and consider some of the issues there as well. Platinum is a vital component, as you all know, in catalytic converters for cars, and in catalysts for the chemical industry. Also, platinum and cobalt are used to produce strong magnets for various applications as well. So you can see that the platinum palladium and rhodium contribution is quite significant in autocatalysts. As we look at the platinum value chain, we see that 5 grams of platinum is typical in something like the Morensky Reef here, which means that if you're taking 5 grams of platinum to make, that's a small metal bar, which is 22 millimeters long by 13 millimeters with a thickness of only 8 millimeters. That is what 5 grams from a ton of rock makes. So literally for every ton of rock that is mined, you get a ton of waste. And the issue is that all of this processing shown here, the mining, the concentrating, the smelting, the refining, everything through to the process of manufacturing requires energy to be used. And the South African mining industry uses 15% of the supply of electricity and 10% of the diesel. And the platinum sector uses a third of that electricity through its mining, concentration, smelting, refining, etc. Now, we are all aware of the increasing population. So from Roman times to 1900, the world population increased by about 1.4 billion people. So in 2 millennia, the population increased by about 1.4 billion people. Whereas in the 120-year period from 1900 to 2020, the world population grew by about 6 billion people. Now, a large proportion of this population is in the lowest of income brackets, and they all want to improve their standards of living. They want nice housing, they want water, they want food, they want transport, they want household appliances, smartphones, internet access, and all of these things require more metals and materials, and even food requires us the use of phosphorus and potassium containing fertilizers for agriculture. These all have a mined component. So this population increase is contributing to our changing climate. And if we go back and consider what has been happening since the Roman Empire, we see that in the period, the recent period sort of through 2018, the world economy is using much more copper, gold, iron, lead, but perhaps not quite such a large increase in silver. So the average growth rate of the copper production, mainly because of the massive development of this global electricity production, explains the nearly 18 times higher average annual production since 1900 compared to the average annual production rate over the period from 0 to 1899. So as we move forward, we are needing more and more energy for more and more mining to keep pace with technology and man's needs. Now, coming to South Africa, it's the 14th largest emitter of greenhouse gases, and those are largely being contributed from coal at the moment. And there's a plan within the country to shift away from coal in the electricity sector and aims to decommission 34 gigawatts of coal-fired capacity by 2050. And it aims to go much more to renewable power generation. Now, therein lies some of the issues as to how green or how clean is green. Wind turbines are largely made of steel, and it takes somewhere in the range of 200 to 230 tons of steel to make a single wind turbine. And it's even worse if the wind turbines are offshore. Now, the point is that for every ton of steel produced, 2 tons of CO2 are emitted. That's a huge amount of CO2 that's being emitted just in the construction of the wind turbines. Now, that's just mentioning what I was mentioning there was steel, but also on average, the wind turbines also require a mass of concrete. And for each ton of concrete produced, 1 ton of CO2 is emitted. And so what we're not taking into account when we talk about wind energy and solar energy being green is how much CO2 is being emitted during the mining, the processing, and the building of this green technology. And a good quality modern wind turbine will generally last for about 20 years. This can be extended a little bit longer, but what are we going to do when these are not functioning in 2 or 3 decades time? Only about 80% of the commodity is recyclable. And we need to be doing the energy maths. How much energy does the wind turbine produce, and how much energy and CO2 was produced in the creation of these wind turbines? When it comes to solar energy, a range of elements are needed for the solar panels as shown there. And I don't have time to go into the supply of all of these, and some has already been done on things like copper and such. But silver supplies could become problematic beyond 2030. And it's not just the supply of all these elements that is an issue. Currently, about 3,000 solar panels are needed for 1 megawatt of capacity of solar power generation. This means that for 200 megawatt project, it could be as big as 550 American football fields that are covered simply to provide that energy. So the London Array wind farm will provide approximately 0.6% of Britain's electricity demand. And that will be achieved by covering 100 square kilometers of the English coast with 175 skyscraper-sized turbines, which will require huge amounts of concrete and steel. But if Britain was to upscale its wind power to meet the actual demand, getting close to 100% electricity from wind would require an area the size of Wales to be covered in turbines. Now, as I come from Wales, I have take great exception to that. Now, the other thing is that energy generation by solar or wind may not necessarily occur at the times that we want for peak demand. For example, in America, wind capacity peaks in winter and spring at over 40%, whereas actually the peak demand is in midsummer, at the time of year when the wind farm output is at its lowest. And similar things have been found from the UK and Korea. So if we look at carbon dioxide emissions in terms of tons from the various processing of commodities and their uses, we can see the enormous amount of CO2 produced by manufacturing aluminium. And so each of these commodities for our green technology comes with its own baggage of all the bad things that are resulting during the preparation. So as we look at mining in the current age, the OECD estimates that in 2015, 16% of the global greenhouse gases were produced by mining, and it's estimated that this could reach 24% of the total emissions by 2060. So the current mining emissions from mining minerals and metals are comparable to the emissions from the global transport sector. So as Dave was mentioning in the previous talk, it's clear that the mining community has a significant contribution to make to reducing greenhouse gases. Now, going back to China, production of minerals and metals from 2000 onwards is quite a salutary thought. Remember how much CO2 was emitted, I showed earlier, during the production of aluminium. Well, in China, since 2000, aluminium production has increased by 1,300%. Steel production, also another major contribution to CO2, has increased by 600%. Cement production by nearly 300%. And the point is that fossil fuels are providing the energy for this. And in 2018, China's energy production was based on a mix of 87% from fossil fuels, 58% of that being coal. So this is a considerable concern. So as we think about mining and the environment, we are always aware that there are environmental issues, and we tend to perhaps think of that as something of a recent phenomenon. But mining of materials, whether from surface or underground, has had an impact on the environment for quite a long period of time. Going back to the Roman mining of gold in Las Medulas in Spain, the massive scale of this alluvial mining 2000 years ago had considerable mining impacts. And we know from ice core data here in Greenland that air pollution peaked during the Roman period when they were mining gold in Spain, and levels of atmospheric lead from this period were not reached again until the Industrial Revolution, 1700 years later. Waste material is an inevitable consequence of mining. Where the waste material is held by a dam at high elevation, considerable damage can occur if the dam collapses. And this occurs at Oktedi in Papua New Guinea in 1984. And I'm sure we all know of many examples of other disasters which have occurred more recently. But I just used this example because I thought perhaps other people wouldn't. And what happened when the dam broke, the chemicals in the water affected fish stocks and agriculture downstream. In addition, during heavy rains, the tailings overflowed the riverbanks into the surrounding rainforest, leaving behind 30 square kilometers of dead trees. And further, the waste muds raised the riverbed by 10 meters, resulting in a relatively deep and slow river, which disrupted indigenous transportation routes. So the overall result of this was that the population perceived that the damage to their livelihoods far outweighed any of the benefits that they received from the mine. We also, in our social and environmental awareness, need to be aware of other consequences. And I'm just going to take the DRC as a rich example, as an example of a rich resource state. It supplies over 60% of the copper needed for the EV batteries, and it is expected to increase supply to more than 73% of global needs by 2023. However, the point is that only a very small proportion of the revenue accrued actually goes to the mining communities around the mines, and they fail to capitalize on its assets in a sustainable manner. And currently the country ranks 179 out of 189 countries scored on the Human Development Index, and is regarded as one of the 5 most top fragile states in the world. And there are issues that get reported that child laborers as young as 6 dig for cobalt, and that the mining boom for cobalt is actually causing lots of issues. So it's a salutary point that while cobalt production might contribute to clean energy elsewhere, it might result in local negative impacts. And I think we do really, as a geological and mining community, need to take that on board. And continuing with an example from Guinea in West Africa, it's one of the world's most poverty-stricken and unequal countries. And it contains an estimated 26% of the world's known bauxite reserves, but accounts for only 6.5% of global production. Now, what is to me worrying is that the Chinese are moving in there. And so while Guinea's development prospects are potentially positive, what we have to avoid is that we don't have a resource curse where we benefit in Western communities, but the country of origin doesn't benefit. And the World Bank is aware of this and is trying to help with legislation, because it realizes that the economies of 81 countries that collectively account for 1/4 of the world's GDP and half the world's population, of those, nearly 70% live in extreme poverty. We need to consider, as we go forward, something more about a circular economy where we use waste from some materials into another process. And we need to think more about recycling. An United Nations report in 2011 suggested that only 18 elements, those shown in this dark blue here, only 18 elements had recycling rates of more than 50%. A further 3, magnesium, molybdenum, and iridium, had 25 to 50%, whereas 20 elements had recycling rates of less than 1%. And we can understand that discrepancy perhaps by looking at niobium and tantalum. Niobium has a very good recycling rate here, whereas tantalum, which is often in the same minerals, has a very poor recycling rate. That's because niobium goes into very large things like steels used in car and truck bodies, oil pipelines, steels for ship hulls and railways, and those bulk things are very easily recycled, whereas the tantalum goes into things like capacitors and small materials for computers, smartphones, and medical materials, and they're often interbedded with other commodities that are hard to recycle. And when we think of a smartphone, a major problem becomes evident, because when considering the use of smartphones, which are often simply discarded or left in a drawer after a few years' use, and I'm guilty of this as much as anybody else, the lowest rate for recycling of the metals shown in this color here is really for the technology metals, which have the lowest supply volumes, such as indium, germanium, gallium, and rare earths. And the same as with computers, those metals are typically so well interlaminated or interbedded with other materials that recycling of them is difficult. So as we look forward, are the current rates of production sustainable? Well, my feeling is that they're probably not. But looking at something produced by Gavin Mudd, what he's shown there is in the central row here is what amount of that commodity was produced in 2018, as opposed to what is regarded as the what the resource is in the ground. And he shows that, for example, copper resources in 2015 were 3,034 million tons of copper, compared to a production of 20.1 million tons of copper in 2018. And similarly for lithium, resources in 2010 were 23.6 million tons, yet 2018 production was 95 kilotons. So at constant production rates, and therein lies an issue, he suggests that even without finding any more new resources, we have something like 150 and 250 years remaining, respectively, for these production of these commodities. Now, it's not all bad news. Many sites of mining are protected as special sites of scientific interest in the UK, either for ecological, geological, education, or cultural value, and they provide valuable resources. And sometimes we can use the waste material for other processes to give us a circular economy, or as is happening in the Joburg old mine dumps, which date back to 1886. They're being reprocessed, and although the grade is low at something like 0.5 grams a ton compared to the 5 grams mined from underground, the cost of the mining is not great, added to which the sand from these dumps is removed by high power water jets and carried in streams of water, which are reprocessed at some distance from the city centre. And not only does that produce significant gold, it creates jobs, it releases prime land for redevelopment, and importantly as well, the new dumps outside the city centre are being constructed in line with best environmental practice. So there are some good examples out there of mines investigating in a number of different technologies. There's no market premium for companies that engage in process sustainability actions, which is actually a real limitation of what they can do. And that, as Dave Lowy has explained, is changing. But companies are essentially motivated to engage in pro-sustainability actions, such as energy and water use reduction, or the proactive management of their interactions with local communities and conflict reduction, only if these actions effectively positively impact on their costs, or as is demanded by its investors, or going forward, perhaps its government. We've talked about potentially improving things underground, and I just found this fairly recently when I was researching for this talk about the first entirely automated mine in the world has already been developed, and the Kankberg gold mine in Sweden has produced in 2018 450,000 tons of material grading at 4.4 grams of gold, 10.7 grams of silver, and also significant tellurium. So it can be done, and obviously it is going to be done. One of the things that I wonder is here on the left, you see the sort of thing that we're all familiar with on our fridges in our kitchen. And when you buy a fridge, yeah, this is my last slide, Tanya.
Oh, great, thank you.
Oh, sorry, Sarah.
No problem, thank you.
Sorry, Sarah. When we look at the energy labels on a fridge or a dishwasher or whatever, we can choose what we're going to buy in terms of how energy efficient it is. What I think we need to see for the future is something along a similar lines with recyclability. So maybe we can have an A grading for something that has 90% recyclable commodities, and down to an F grading where there's a very poor recycling possibility. It would certainly give the buyer the option to give more thought to recyclability. And we need, going forward, to think more about that during the design stages of a product. So what I've aimed to show is that the green energy with solar and wind turbines is not as green as many people think, and we certainly need in the mining industry to take that on board and take responsibility for reducing the greenhouse gases emitted by the mining community. So thank you very much for your attention.
Great. Good day,
you.
everyone. Yeah, so I just I got the honor of sharing some of the roles that seismics can play in green mining development. And I suppose the crux of my talk was alluded to by Dave Lowy, who said something along the lines of keeping exploration, or how can we focus at on exploration in a green mining paradigm. And yeah, we've developed a few techniques for doing that, and so I'll be sharing that with you today. I'd also like to share how seismics it's typically thought of as being only part of the exploration phase of mining development, when in fact it can also serve a major role post and during mine development. So I know we have quite a broad audience, or an audience from a broad range of fields here. Sorry, I'm not sure why okay, there we go. And so I thought I would just spend a quick slide just briefly explaining the seismic method. So what we do is we'll take out a seismic source, which is what you can see at the top left there, and we'll smack the ground, and that'll produce a series of waves that will interact with the subsurface. And one of the ways that these waves interact is by reflecting off rock boundaries, as you can see, and then we pick up that signal with receivers, which can be seen at the top right there. And this forms the acquisition part of seismic imaging, which is the first of three major components of the seismic routine. We then take those signals and we process them. And at the end of that processing, we get an image like this, which is an approximate capture of the subsurface. And each of those lines there, those are reflections that were picked up. The processing sequence is actually, it's quite a long and involved process. Once we've processed the data, we then use that result to then infer what the subsurface is doing. So we interpret the data and make inferences of the structural geology of the subsurface. Now, the question that I'm wanting to answer today is, how can we make these two steps greener, or at least assist in making the mining greener with these two steps? And that's something that we've actually recently been looking at the Seismic Research Center at WITS. So before I jump into it, I'd just like to give a quick background of the Seismic Research Center. It was founded in 2015 by Musa Manzi, whom I'm sure everyone here has heard his name. Yeah, it's basically a world-class training facility for students and for consulting. Since its establishment, there have been 30 international papers, peer-reviewed journal papers. There have been more than 10 MSc students and 5 PhD students that have graduated from the research center. And it is composed of 3 academic staff, 3 postdocs, of which I am one, and a whole bunch of master's and PhD students. And we specialize in a bunch of different software processing as well as near surface acquisition. And here are the faces of the Seismic Research Center. You have Musa Manzi at the top left there, the founder, as well as Prof. Ray Durheim at the top right, who's world-renowned seismologist. And then in the center there's Prof. Susan Webb, who's more specialized in potential field theory. And then various students of different degrees of studying. And then some of the research themes that we focus on for the within the research center, it's primarily seismic imaging. And so that's quite an umbrella topic. But we do focus on acquiring data in the near surface, but we also mainly focus on processing and post-processing, so interpretation and data integration. So if there are borehole logs with geophysical parameters, that assists in the modeling of the subsurface and informs the seismic interpretation. And then we also integrate seismics with other geophysical methods such as gravity and magnetics. So going back to the question, how can we make these greener? There are two themes within our research that I'd like to point out. And the first is recycling mining space. And the basic concept behind this is we can exploit a developing mine's structure to better image the target ore body. So if we take equipment down into tunnels and we collect data there, we're much closer to the target, and so we get more precise imaging, and it's much easier to see the target. So we're able to inform the mine if it wants to expand beyond where its current limits, and we're able to, by doing that, we upgrade the geological model, and so there's more efficient mining practices therefrom. The second topic is within the processing, and that is recycling seismic data. This has become quite a hot topic in the seismic literature, where we take legacy data, which mines typically have an abundance of, and we reprocess it. And usually these data were collected, 20 years, up to 20 years ago. And so the updated algorithms make quite a significant difference. And I'll showcase one of those examples later. And then it's a similar outcome. So if we are able to reprocess the data and we update the mine's geological model, then they have a much more accurate idea of what their ore body is doing, beyond the expanses of the current development. And so I want to show you an example of each of these, and I'll focus first on the recycling mining space. So there's a project that we're doing with the Mandela Mining Precinct. It's called the Advanced Ore Body Knowledge Program. You can see on the left there, that's just a snippet from their a clip from their website that details the AOK program. And the basic concept is, how can we look ahead of the mining face or the stope? And we're doing this together with CSIR. The WITS team is responsible for applying seismics to this idea, and CSIR is responsible for applying resistivity tomography to the idea. We also got a little bit of press for this. You can see at the bottom right, there's a clip from phys.org, which is an international and quite reputable online scientific news website, focusing mainly on physics, but also branching out into other fields. And so it was quite an honor to be featured on their website there. And that's what the article there is, the one that is what I'm going to be presenting to you now for this first example. So the mine that we're looking at is Maseve mine. It's located at the western limb of the Bushveld Igneous Complex. So it's obviously a platinum mine. And I'm sure everyone here knows about the Bushveld Complex, and certainly a whole lot more than I do, I'm sure. but for the sake of completeness, I thought I would just quickly brush over it. So it is the largest known igneous layer intrusion, and it does account for 90% of the world's known PGM reserve. It also contains other metals that are listed there, of which most, if not all, are all critical metals. And it's very expansive. It's 65,000 kilometers squared. You can see at the bottom left there, the space it takes up within Southern Africa or South Africa. And the ore bodies that are targeted, and at the mine that we conducted these surveys, Maseve mine, are the Merensky Reef and the UG2. And you can see the stratigraphic column on the bottom right there. There's the Merensky Reef is the MU near the top, and then you can see the UG2 down below it there. And so those are the target ore bodies. So here's just an overview of what we did. So on the left two diagrams are the mine plans, and the right two diagrams are satellite images of the mine. We broke our experiment into two sections. There was the surface surveys and then the tunnel surveys. And the surface surveys, we had 3 sites that you can see there where we were acquiring data. And those sites overlay the location of where we were doing the tunnels surveys, which you can see encircled in the bottom diagram. The bottom right, the Google Earth image, that diagram contains the subsurface structure, or at least a portion of the mine structure, and the tunnels and the incline, which is that main line along there. Okay, so for we used a whole bunch of equipment for these surveys. For the surface surveys, we used these ever increasingly popular RAUs, they're called, remote acquisition units, which is in the top left diagram there. Basically, we have, let me get a pointer up so I can illustrate. We have a peg that we stick into the ground, which detects the waves, and that gets recorded in this box here. And conventionally with seismic surveys, these boxes are usually cabled. So there's usually a cable running from this one to the next one and across the entire length. And these are relatively new in that they're cable-less, so they're remote. And it's very useful to us because we're not constrained in how we set up the survey. We can have a whole complex situation if we need to. We also used Landstreamer, which is in the top right diagram there. And basically, it consists of nodes of these geophones that pick up the seismic waves, but they're not pegs, so we don't stick them into the ground. They're actually just pulled along the surface, and it makes the acquisition a lot simpler, though we do sacrifice a little bit in the data quality, but it makes the acquisition a lot more efficient and just generally easier to carry out. For the seismic sources, we used at the bottom left there, you can see it's a 42 kilogram accelerated weight drop that we mount on the back of a vehicle. And this thing thumps down onto a base plate there and sends the shock waves out that we detect with these various receivers. Additionally, we also had in the bottom right figure, you can see that's a broadband sensor, which those are typically used for earthquake detection. And funnily enough, during this field work, we did pick up an earthquake. I can't remember where it was located, but a colleague was saying that he managed to pick an earthquake, a minor one. But anyway, we decided to deploy these as well to see if we could integrate these with the other conventional seismic receivers. here's the overview of the surface surveys that we had. So those are the 3 sites. Site 1 was a patch, so we did a grid there to get a 3D image. At least it would be a rather small one, but it's something that we could work with. Site 2 at the bottom there was I believe it was 200-kilometer line. Sorry, actually, there is there's a scale here, but it's a bit small to see, but it's 500 meters there. And then we also had site 3, which was another seismic line. And in red, I highlighted all the sources of noise, because seismic noise, because what we wanted to do as well is a relatively new seismic method known as the passive seismic method, where instead of pumping energy into the ground, we also wanted to just collect a whole bunch of the ambient energy and see if we could use that to image the subsurface. Okay, so looking underground now, these were this was the equipment used in the tunnel. We took the conventional geophones, which you can see in the top diagram there, and we had 2 different types that recorded different frequencies. So we wanted to compare the results of those 2. And then at the bottom there, you can see that we managed to secure the land streamer to a pillar, one of the mining pillars, because we wanted to try out some stress tests. And so here are the different lines that we acquired for the underground. You can see they're all annotated in the bottom diagram here. Line 1 ran along this main corridor here, and it was the target there was to image the Merensky Reef and the UG2, and specifically to look at their dip and quantify their dip. Then lines 2, 3, and 4 were all located at that pillar that you saw, which we deemed Michelle's pillar after the coordinator of the project. And you can see the various goals that we wanted to achieve with those different lines. So it's mainly stress analysis on the pillar, and comparing different geophone types. And then we had 3 lines that were end-to-end along the incline of the incline drift. And that was also to target the Merensky and the UG2, and it was our longest line. So that's the most promising one. Now, unfortunately, the data is still being processed, so I can't show any of the results here. But I thought instead of leaving everyone hanging, I would show an example that's very similar to what we did. This was a case study done in Portugal by geophysicists from Uppsala University, with whom we work quite closely. And you can see this is it's Neves Corvo mine in Portugal, and this red, you can see the red ore body there, and the green illustrates the mining structure and the various surveys that they conducted within the tunnels and also on the surface. And some of their results were quite impressive. So the first was this seismic survey that's from that profile 6 on the surface. And you can see that there's this reflection here that definitely is associated with the ore body. And so they concluded that the ore body extends beyond what they originally thought. And another method that they used was a tunnel to surface acquisition method. And basically, so they used a seismic source within the tunnels, the mining tunnels, and picked up the signals in the surface arrays. And they were able to construct what you see there is the velocity model. So those are different velocities at which the seismic waves move through the rocks. And that is extremely useful when processing the surface data. So it's a seismologist's dream to have a velocity model that accurate. And so that gives you an example of what it's like to, or how we've managed to recycle mining space. I'd now like to show you an example of how we recycle mining data, seismic data. And this was a paper that we recently published end of last year. Basically, so there are two seismic profiles that you can see in the two figures there. The top is the surface geology, and the bottom is a magnetic map. This was in the Northern Cape of South Africa. And these seismic lines were originally acquired by Anglo-American they were looking for outliers of the Wits gold reefs, gold-bearing reefs. And the results of that study, from what I can remember, they weren't really conclusive. They didn't really confirm or deny, but you know, it's the likelihood of it is up for debate. But what was very useful is that these data, which were collected in 1994, they lie over, you can see in the magnetic map, this strong anomaly here. And this is caused by hematite-bearing rocks, which are part of the Kuruman Formation in the area. And right next to it, you can see that there's a mine here. This is a Sishen mine in the Northern Cape, and that's an iron mine. And so we decided to reappropriate these data to image the iron-bearing rocks, and to maybe inform both Sishen mine and also just have a model of the subsurface, especially, you know, targeting the iron mineralization. And after processing, this is just a comparison between the legacy and reprocessed data. And you don't really need to be a seismic expert to see, like, the reprocessed data shows some very nice signals in this region here. The red arrows they indicate the reflectors that that are associated with the Kuruman Formation, and the green arrows just show some enhanced reflections throughout the entire section. And so via the reprocessing, we're able to recover a lot of the signal and reduce a lot of the noise. And that's one of the primary objectives of a seismologist. We also, beyond just reprocessing the data, we also integrated the seismic data with various data sets. So there's the magnetotelluric data, which we acquired from, it's called the SAMTEX experiment, where I believe it was MTNet collected a whole bunch of magnetotelluric data. And so we reappraised that and used that to assist our interpretation. We also had two boreholes in the region where we could, we run synthetic seismograms on the boreholes to see what a seismic response would look like in that region, so that we can more critically analyze our results. And then we also used the magnetic data, as you saw, and we combined all of this with a refraction tomogram, which we computed using the seismic data. So basically, with the reprocessed data and the integration of all the other data sets, we're able to make quite I suppose, a significantly comprehensive model of the subsurface along the profile there. You can see it's this big synclinal feature here. This region we tentatively interpreted as an intrusion zone, but after presenting this a few times, I'm getting more and more skeptical about that. So we were very tentative in that interpretation. But you can see the two red layers there. Those are the iron hosting strata, and we concluded from the paper that they had an average depth of 950 meters and an average thickness of 500 meters. So quite informative and useful for any mine developments that might happen there, and it would inform the mine even before they need to do an exploration. This can be very helpful to inform any decisions before acquiring a new seismic team. And so this is one example of how we've reused legacy data. We have quite a few papers showing similar examples. And if anyone is interested, I'm happy to provide links to all of these papers, where in each one of them, the value of legacy data is shown to, you know, we bring out the full potential by re-looking at it. And on top of that, the Seismic Research Center has been given a whole plethora of seismic data from these various mining houses. And this is just a snapshot from within the Wits basin area. You can see all of those 2D seismic lines. We've also got some 3D seismics here, and I believe within there. And then all these random dots out here, these are all boreholes, which can also assist in the interpretation. And so we have quite a wealth of legacy data that we can just, that's waiting to be processed and dug into. So yeah, that's how we found recycling seismic data can actually help with maybe making mining a bit more efficient and a bit more green. And so just a couple of conclusions. The two key things that I wanted to get across is that we can recycle mining space to reacquire data and to further inform the mine. And we can also recycle data to do similar, to update a geological model and to inform the mine. That said, as everyone has pointed out, at the end of the day, the mining still needs to happen. And so it's not like this is the, you know, a revolutionary finding, but maybe it's a couple of steps in the right direction. Before I end, there's two honorable mentions that I feel like I had to put in that we haven't been able to do at the Seismic Research Center, but that has been incorporated in global seismic research. And the first is drone technology. So yeah, drones are playing quite a significant role in having more efficient and more clean acquisition. So this video that you're seeing on the right here, this was taken by some of our colleagues at Uppsala University, where they ran this drone is carrying this, this is a detector, it's a magnetic field detector. And so they're running a mag survey with this drone, and they ran it along a line that was originally acquired using a helicopter. And they compared the data from the two. There are a few data sets here. It wasn't just the helicopter. There was also some fixed wing drones used as well. But what I wanted to point out is the helicopter data is this red, the red data here. And specifically in this region, this is where they had magnetite and hematite rich rocks. And you can see that there's an anomaly associated with it. And the drone got equally good, if not better, resolution seismic data, magnetic data, sorry. And it saved a whole bunch of fuel because drones, you know, they don't use any fuel as opposed to a helicopter. And so they can play quite a significant role in making mining greener. And then the second one I wanted to, right. This is, I thought I'd show this as well. This is something that Total is working on. It's called the METIS program. Basically, they have these drones that deploy these darts that you can see at the bottom here. And the idea of this is that we can conduct seismic surveys in hard to reach areas, you know, like foresty areas or very hilly areas. And the darts are biodegradable. So the idea is that you just send these drones out, they drop these darts into the terrain, and these darts will record seismic data and then send them via wireless signal. And after a couple of years, they would have degraded. And so that's the idea, at least. I'm not sure if this has actually been implemented commercially yet, but you can go and look up the project if you're interested. And then CCS, you know, seismics definitely has a role to play in carbon capture, both before and after the carbon has been pumped into the ground. So before, seismics can definitely be used to survey the target storage rock, and quantify its geometry, and then also see if it would be a good retainer. And then while the CO2 is being pumped into the rock, as well as afterwards, the seismics can be used to monitor the stability of that storage and to see if there are any instabilities. So yeah, I just thought that those two would be worth mentioning. And so with that said, I'd just like to acknowledge the Seismic Research Center has had support from many, many different companies, both in the capacity of funding as well as software. A lot of these companies have allowed us to use their software at a reduced rate, and we're very grateful for that. And so, yeah, thank you for listening to the talk. I'll be happy to take questions, but while questions are being taken, I thought in good South African fashion, I'd show a video of the seismic team doing the Jerusalem dance, which took the world by storm recently. So thank you.
Thanks so much for that, Mike. That was really, really interesting. And actually, I'll say hi to you from Sishen Mine, which is currently where I'm sitting. So thanks for that. So yeah, excuse the trucks in the background if you hear those. But yes, thanks for that, Mike. I'll open the floor to some questions, but I'm going to jump in and start with the first one. Those little dots at the end there you mentioned, you said they take a couple of years to biodegrade. Do you have any idea how many years? Because I know that's a big thing that, you know, when they say things are biodegradable, they actually take, they are, but they take a good few years to actually.
Yeah, that's actually a very good point. I think it's easy to focus on the fact that they are biodegradable and kind of overlook, well, how long does that take? Honestly, I'm not too sure. From my recollection, I believe it is a couple of years. That's the figure that's sticking in my head, but I'd have to look it up to verify that. Yeah.
Okay.
Sorry, I don't have it off the top of my head.
Not a problem. I just thought I'd take a chance there.
No, good point. Good point.
Are there any other questions for Mike while we have him on the line? You can just raise your hand or unmute. I think there's some very interesting stuff going on, and I think it will definitely, you know, we're going towards the future of mining, you know. Willing to help us out and always does have the best and most interesting facts. So hopefully we're in for a treat. When you are ready, Mark, you can take it away.
Thanks, Natalie. Hi, all. It is actually shining for a change in the United Kingdom. Monday we had snow, so much so for, you know, global warming. In the similar way that Paul blamed me for the content of his talk, my talk content is thanks both to Judith and Paul. Like most things, when I started this presentation or doing the research for it, I had a very different idea in mind to what I've ended up with. Some of these slides you're going to have seen already, so I'll just brush through them. But as we all have seen several times, is as technology and human development has advanced, so the requirement for natural resources has increased, specifically minerals and metals. But a lot of the times we tend to forget that our development is based on some very basic and fundamental things that we take for granted every single day of our lives, and we only tend to think about them when they're not there. Now, with all the discussion about the 2 degrees Celsius warming, moving to green energy and economies, being more efficient, circular economies, donut economics, UN development goals, and everything else that happens. If you go through this slide, what is quite interesting is, even though we're looking at these massive increases in metal production in terms of all the critical elements and metals, the last paragraph is actually very interesting, and this is what prompted my discussion. Is nowhere in these requirements have there been any thought, or at least to the research that I did, too much thought given in terms of the fundamental underlying infrastructure that's going to start supporting all of this. And at the same time, you can see things like transmission lines for electricity, sewage lines, roads, railways. None of that information has been discussed or where it's going to be coming from. nor does these massive increases in the amount of metals that we're going to require for the new world economy takes into account the massive physical parts. So as you can see here, the chassis of EV vehicles, that is not taken into account with all these changes that, for example, the World Bank has documented. Sorry, as normal, this slide presentation will be available. All the links and references are down at the bottom, so you can go to any of these, click on it, and it will take you to the relevant documents that I've sourced for this. Now, as Judith pointed out, over time, the world population has increased. In fact, it's referred to as a great explosion ever since the Second World War. And a lot of that is due to advances in technology, specifically medical technology. What most people don't think about is pre-World War II, things like penicillin, medical evacuation, blood transfusions, plasma, were in very, very early stages of technological development. Post-World War II, and the creation of the World Health Organization, there was massive inoculation campaigns. Cities which had been destroyed during the various bombing campaigns and fighting were all rebuilt with new sewage infrastructure, which obviously led to a lower mortality rate. And because cities then started to evolve, obviously people want work, and the place you're going to go and get work is in the city. So as we've seen over time is this massive increase in urbanization, where people move from rural areas where there's limited employment opportunities and start moving into cities. Now, looking at this map, it's quite interesting to see where the large rural or urbanization patterns are occurring. And the majority of them are in what we refer to as the BRICS countries. Now, what should be of interest to most people, especially obviously as it's a South African audience, is that the degree of urbanization in Southern Africa is actually relatively low in comparison to the rest of Africa. I mean, just take a look at West Africa, further up here at Egypt, and then in Central Africa. I mean, no one would expect that places like Rwanda and Uganda have the fastest population growth, or amongst the fastest population growth in Africa, and also by definition, some of the highest urbanization rates. Now, the problem with urbanization, specifically in the African context, is that people move into cities, but there's no infrastructure to accommodate them in cities. Now, this is the latest information that I could source, so it's a bit dated, so it only goes up to about 2015 from the Brookings Institute. But you can see the massive urbanization in Central Africa and West Africa, not so much in Southern Africa. But probably what is more important is if you start looking at this graph below. And what that's trying to imply is the degree of development within those cities or urban areas, i.e. infrastructure. So when we start looking or starting to compare the degree of urbanization, or what's referred to as agglomeration in Africa, with major cities in the rest of the world, there's some quite interesting facts that start popping out. So if you have a look, and unfortunately these slides aren't too clear, they are the best I could get at the time. If you start looking at similar European cities, and the magnitude of population by no means is the same as what you're seeing in places like Addis Ababa, Dar es Salaam, Lagos, but it's the infrastructural development. So if you look at somewhere like Barcelona, so the white line is the CBD, so the Central Business District, and then looking at the development of the city as it goes away from the Central Business District. Now, in general, African cities, I mean, think of Johannesburg as an example. The original city center is effectively being abandoned by most businesses, and businesses have now started to move out to places like Sandton, Rosebank, Fourways, okay, which tends not to happen in a lot of Western cities. Why? Well, part of it is due to the fact that there is a lot of infrastructure in those cities. So if you look at this, for example, Barcelona, Central Business District, and this whitish area is the level of tarred roads. So it's seen as a function of the amount of infrastructure, so to get people to and from work. So again, getting back to the South African context, Soweto, due to apartheid government laws and regulations, is outside of Johannesburg. There is very limited access to Johannesburg from Soweto. It was done on purpose. But in similar type of African cities, like Johannesburg, if you look at things like Dar es Salaam or Addis Ababa or even Nairobi, as you move out from the center of the city, the amount of infrastructure to support the working force getting into the city drops off astronomically. And if you start using tarred roads as a proxy for infrastructure, so things, again, most people take as granted, so water, sewage, electricity, public transport, you just don't have that. So what tends to happen in the African environment is while there's a high degree of urbanization, what you then tend to get is a high degree of slums. So as we all know from South Africa, you start seeing shacks or shanty towns. But to drive all of this type of stuff, one of the fundamental things for our green economy is going to be electricity. And this is also a rather frightening graph, depending on which way you want to look at it. In Southern Africa, which is generally considered as being the most highly developed portions of the African continent, with South Africa in general being considered to be the most developed in the African continent, less than 50% of the population is connected to electricity. As you start moving further north, this drops off. So if we start thinking about, well, how are we going to drive this new green economy with taking away reliance on fossil fuels for energy or even electricity, there's going to have to be massive infrastructural development. And massive infrastructure development comes with a whole load of things, which, again, most of the time we don't even think about. So when you're starting to look at a roadway system, I mean, there's a whole load of material that goes into a roadway system, not just the capital that is spent on it, but all the raw materials which are used to build and maintain a roadway system. The same thing goes with railway lines. Again, railways tend to be the most cost-effective way of transporting mass amounts of material over long distances. And theoretically, they have a lower carbon footprint than transporting things by trucks. What tends to happen, or has happened in the past, is with mismanagement of a railway system, tends to force companies and businesses who are transporting to move on to roadways. So given the fact that all vehicles are either diesel or petrol driven at this stage, you then start moving your problem from one area to the next area. By moving your transportation problem onto a roadway system, you, as has been seen in Johannesburg, you then end up with blockages and choke points, and the system becomes more and more ineffective. I mean, the classic case of the traffic in Dar es Salaam or the traffic in Lagos or Nairobi or anywhere else where the road infrastructure has not been maintained, neither has the railway infrastructure. Similar thing starts happening when you start looking at basic infrastructure requirements such as water supply and sewage systems. Again, all of those depend on a backbone of infrastructure, which if it's not maintained or if it's not developed, tends to collapse, and the capital involved in redeveloping that becomes higher and higher. Now, I'm sure the point most of you are wondering is, well, you know, why is Mark rabbiting on about this when we're actually talking about geology? Well, it starts getting into the fundamentals of what's required. Something as simple as water and sand. I mean, the example from here is an American example, so they tend to have different standards in building roads and railways and hospitals, but these are sort of indicative. So if you're seeing massive population influxes into cities and you want to bring your general population, as a good government should, up to a general reasonable wellness standard, you would anticipate that there will be houses built, that there will be roads to get people to decent jobs, and that you're going to have hospitals and schools to go and cater for people. Now, lack of infrastructure development actually isn't a South African problem. I was doing work in Ukraine recently, and one of the biggest issues that is happening in Kiev at the moment is, again, a massive influx of people from the surrounding countryside into Kiev for work, but there has been no money put into the infrastructure in Kiev. So you're now getting people moving in, massive amounts of building in terms of businesses and flats, but there's no hospitals or schools to go and service the families of the people moving into the city. What is also critical is, and this talk doesn't discuss it in any detail, is the concept of water. Water is becoming more and more critical, regardless of any arguable climate change the stress on water is increasing just due to the amount of people that we're getting on the planet and the amount of things that we're building. There's some interesting stats I came across, and again, I couldn't validate them, but there are theoretically more man-made built objects on the planet at the moment than there are living beings on the planet, taking into account all animal species as well. So when we start looking at these type of things, well, where is all this stuff going to? Who is consuming all these products, and where's it all occurring? So if we switch over to just look at cement manufacturing, which is generally tracked as an indicator by things like the World Bank and the OECD, as an indication of how prosperous your economy is and how you're developing, you can see China is by far the biggest producer of cement in the world. The next biggest one is India, and if you look at the graph, I mean, it's just nowhere in comparison to what China is actually doing. And then moving down the line, obviously, Vietnam, United States. Now, if you were to take all of these in total, every other country in the world up in terms of the cement manufacturing, they actually do not reach the same amount of manufacturing capability that China is currently exhibiting. So when we start looking at what components then go into cement manufacturing, and again, it's just something, you think you go down to the hardware shop, the builder's warehouse, and you buy a bag of cement, but what goes into cement, and it actually starts becoming a lot more interesting, not just this bag of gray stuff that you go and pick up to build a wall. This is the type of things that go into a standard Portland cement. Now, I'm going to get to why it's called Portland cement and the history in a few slides, but there are large amounts of industrial minerals that go into this. And as you would no doubt rightly say, but most of those are bulk commodities, so we need large holes in the ground to get them. They tend not to have a high value, so we're not in the same space as looking at things like platinum or palladium or gold or silver or even copper. I mean, these are the things that, side of the road, there's a piece of rock, okay, and we can start using it. Probably what is interesting when you start looking at these in a little bit more detail is the last two on the list, bauxite and iron ore. Most countries tend not to have huge amounts of bauxite or iron ore. So that material will then be imported from external sources into the country. So above and beyond, as Judith pointed out, the carbon footprints that comes in from manufacturing Portland cement, you are then going to get the additional carbon footprint of moving these materials from where they are, like in Guinea or Australia, to your country so you can go and process it. And these are just the primaries. When we start looking at what's referred to as the secondary raw materials, which are needed in cement, we start getting into some very, very interesting territory. If you start thinking about, well, where does slag come from? Where does fly ash come from? And where does FGD gypsum come from? Now, all of these, or at least the first three, are all related to industries which use coal as a primary heat source in the production. So if you think about making steel, metallurgical slag coming from coking coal. So if you want to move away into a lower carbon environment, you're no longer going to have the same amounts of slag being produced if the hydrogen technology currently being tested out is actually successful. So first of all, we're going to wipe out slag. Fly ash, again, a primary component in different types of Portland cement, is a byproduct from coal burning in coal-fired power stations. So once we start taking coal offline or coal-fired power stations offline, then you suddenly start running into an issue of where are we going to acquire a fly ash? Interestingly enough, the FGD gypsum is a byproduct from another environmental process. So those of you of a certain age can remember when acid rain was the topic of choice, moving industries into reducing the amount of sulfur dioxide getting pumped into the environment. And part of that was doing this process. So any sulfur dioxide getting pumped out by coal stations or smelting facilities then goes through a desulfurization process. And by doing that, you create gypsum, which is then used in the building industry. So again, if we start going into a carbon neutral economy and focusing on things like wind turbines, geothermal energy, pardon me, or solar panels, we then suddenly lose our source of gypsum, which again is critical for our building industry and building infrastructure. Then the final point is recycle building materials. Now, again, that all sounds very well and good when we're talking about it in the theoretical sense. But when you start looking at it from a purely economic point of view, one of the problems that starts coming in with recycling of waste deposits or building materials is the size. Even though the material is there, the size of a block is trivial in comparison to mining the material from an open pit. So your cost per unit will start going up when you start looking at recycling some of these things. The second thing starts getting into the environmental aspect. A lot of older buildings would contain things, nasty things like leads or asbestos. And by definition, with new building and building standards and health standards, that material cannot be used and recycled. It has to be disposed of and buried. So you're not always necessarily going to get this ongoing recycling of buildings. The other thing that you start encountering is, well, how often can you start recycling buildings? This assumes a constant churn of building and destroying and building and destroying. Now, at which point are you then going to get to the point, well, is it ecologically friendly to start recycling buildings? We just created our nice green building, and in 5 years' time, we're going to knock it down again because we need the raw materials for our next building cycle. So, but to move on, where does this all come from in talking about cement? But as a historical aside, it has a rather dubious legacy. This is William Aspdin, pretty much lost to the history pages, but he was branded in his own time, as you can see here, an incorrigible liar and swindler. So much so that in Victorian times, well known for, you know, pillars of the community like our own Cecil John Rhodes, he was pretty much vilified. The quote that you see next to him, that was written by his father after he asked William to leave the business because William was deceitful and fraudulent. So, but getting back, why is it referred to as Portland cement? Well, that was a bit of a Victorian sleight of hand. In Britain, Portland stone is a well-known building stone. It has a grayish color, and with the earlier forms of cement, it looked very, very similar to Portland stone. So Portland cement was originally intended as being a substitute to Portland stone, so a cheap and effective substitute. And when we start looking at Portland stone in a little bit more detail, Portland cement, you can see it's just not cement. Cement is just not one bag of stuff you get. There are 7 different major classes of Portland cement. And within those, each one of those have subclasses. And these are just the standards. We're not actually looking at specialty cements at this moment. But if you start casting your eye across the information that's contained in here, the logic or the repercussions of going fully green and getting rid of a lot of the secondary sources of raw materials, you start wiping out large portions of the types of cement which are critical to building infrastructure. So just flipping it back a bit, depending on the type of infrastructure you're building, you would select, or the civil engineer would select a specific type of cement designed for resistivity, or its resistance to, say, erosion, resistance to salt water, curing time, hardness over time. So you can see that, for example, as soon as you take out fly ash, then suddenly you can't produce fly ash cement, which is incredibly hard, or alternatively, the cost of those cement products are going to increase significantly and potentially make any building a lot more expensive than what it currently is. Okay, so just an example of fly ash. And again, just when you thought ash was ash, and it's just the stuff you get out of the back end of a boiler in a coal-fired power station, well, turned out not so much. This is the American classification. America classifies fly ash as C and F. And as you can see here, they have different characteristics, different particle sizes and different particle shapes. Depending on the country that you're in, the cement manufacturing industry will then have a series of specifications which will lay out in terms of, well, what type of fly ash and what's the quality of the fly ash can they absorb within the cement manufacturing industry. Now, the German building organization has been the first one to start raising these concerns. based on a study that they did back in, I think 2017, if I'm not mistaken, where they started pointing out to the German government and saying, well, look, guys, it's all very well and good for you to have said that you're going to start phasing out coal-fired power stations in Germany, but you do realize that if you do this, we are no longer going to have a source of fly ash in the country, which is going to be relatively cheap and theoretically with a lower carbon footprint. Now we're going to have to start importing fly ash from surrounding countries, which may not have the same type of regulations. So fly ash from Poland or Czechoslovakia, sorry, I should say the Czech Republic, or Romania or Ukraine is now going to have to be sourced out of the country and moved into Germany by theoretically rail. But again, the implications of some of these things have not necessarily always been thought through to the logical conclusion. The other critical component that we start looking at in terms of cement or concrete is things like sand and gravel. Now, if you're like me, I've never really paid too much attention to this. I mean, sand is sand, gravel's gravel. It's at the side of the road. You dig it up, you do stuff with it, and you can build. Turns out it's not. The other really interesting thing, which I was not aware of, is that in terms of raw materials extraction, aggregates in some countries and some economies actually have more economic value or have a high economic value than mining of metals. So if you start looking at the US, for example, the second largest contributor to the US GDP in terms of the extractive industry is the sand and aggregates industry. Surprisingly not the metals as most people would assume. And oil and gas comes very, very close to those, and it depends on the stats you're looking at and where they're sourced from and which year you're looking at. But overall, aggregates, sand and gravel are massive industries. And because they're massive industries, you start getting corruption. And this is also going to be something I'm going to be touching on later on. There's a massive illegal trade in sand in the world at the moment because specific sands is in short supply. But getting back to this, if we don't have sand and the right type of sand, you cannot build infrastructure. Okay, you're not going to have concrete, you're not going to have tarred roads, and you're definitely never going to have any glass. Again, glasses, which I didn't get into. Again, just when you think glass is glass is glass, well, not so much. To make glass, you need very, very specific qualities of this raw silica that you're going to be melting to make glass. When we start looking at aggregates, again, it becomes quite interesting. We start looking at primary stuff, which is quarries and borrow pits, which we're all pretty much familiar with. But then we start looking at things like recycling. And I've already touched on this. It's all very easy to say we're going to recycle stuff, but you start looking at the economic side of things, and very quickly, some of the recycling ideas actually don't make economic sense. So when we're talking about things like Crisco reporting standards, if we assume that we're now going to start seeing a building as a source of material or a natural resource, as has been punted in a number of academic journals, we then get into the whole argument, well, what is the criteria for eventual economic extraction of those materials? Because if you're not going to get your unit costs down, these things are going to become too expensive, and it's actually going to be cheaper, like in the case of wind turbine blades, to just bury the damn things because it costs too much to reprocess them and to recycle. So when we start looking further on, well, who are, again, getting back to the biggest consumers, this is also a very interesting slide to have a look at. This is based on a report done by the UN, where they started looking at sand, because interestingly enough, as I said, sand is actually really critical, and there's the whole illegal trade going on in sand at the moment. So if you start looking at the usage of sand and production of sand, it's quite interesting. Again, this graph is a little bit dated. It's the most recent data that is available, but you can see the massive impact of the great slowdown in 2009. Now, the rest of the world in general didn't show a major tailing off in building and construction. China did. And because China sneezed, the entire world economy showed that downturn. So this is just looking at the Chinese consumption of sand and cement over time. And you can see in terms of relative figures, if something goes wrong in the Chinese economy, the implications are massive. So everybody still worries about the US dollar and what's going on. But I think from 2008 offhand, the Chinese economy is the biggest driver. And if you start doing a little bit more research, it's actually quite well known that the world economy is based on the Chinese economy and Chinese consumption at the moment. And this is just, again, to give you an indication of how much sand is actually consumed in the world at the moment. Currently, we're looking at about 25 billion tons of material, maybe a little bit more than that, being used in manufacturing and building. If current population growth trends are to be, or are to stay on track in terms of what the UN is currently estimating, which is about 9 billion people between 2050 and 2060, not only are our metals consumption, not only is our metals consumption in the world going to increase, the amount of sand and crushed gravel is disproportionately higher than any requirement we actually have from any other source of raw material. And again, this actually starts becoming a bit of an issue, because if you think about it, where you want to go and live is generally not somewhere where you want a big pit to be built to go and extract gravel or sand next to you. And this is just an indication of the size of these in world economic terms, okay? Now, you may think this jibes a bit with the previous slide in terms of consumption, which is quite true. A lot of these countries make the money by exporting sand to various other places in the world. And sometimes this whole supply chain gets rather bizarre, as we're going to be seeing in the next few slides. Now, one of the things that happened in the past is, as countries or governments realize implications of these massive extraction programs are having on the natural resources, i.e. river systems or beach systems, they then tend to clamp down on legal export of sand. So, and you can see with all of these countries, which is again quite interesting, is in some ways, while it's not as dramatic as the Norwegian or the Dutch disease, where countries then get used to having a source of revenue coming in with no little or no, pardon me, not a lot of hard work, and that money gets squandered. These emerging economies are now exporting something which is irreplaceable. You're never going to replace this. The rate of replenishment of sand in riverine and marine systems is much, much slower than what we're currently taking it out at. But it's the only thing, apart from labor, that countries like Vietnam or Cambodia actually have. They tend not to have massive amounts of other commodities. I mean, Vietnam and Cambodia do have some gold deposits. The Philippines is the world's second largest supplier of nickel laterite ore at the moment to China. But overall, in general, these are the type of things that countries can then start exporting. The problem is, not only are they destroying their own natural habitats, a lot of that money actually isn't going back to where it should be going to. And this is where things start getting rather bizarre. This resource trade website is actually really fascinating. I just pulled the sand trade routes out, but it goes through lots of other commodities. You can look at agricultural trade routes, gold, silver, platinum, oil and gas, everything else. But what we start having a look at here, and this is where it starts getting rather bizarre, is you've got countries like Australia exporting sand to China, or countries like Bangladesh exporting sand to countries which you'd assume have more sand than what they actually need. Massive trade in between Mexico, Canada, and the US. But as we start developing, it's like, there is this massive trade route in sand. And again, getting back to it, if we're talking about carbon neutral, carbon free economies, you're taking low value bulk commodities, dumping them into a ship, transporting them across the ocean, unloading them, and either dumping them into trucks or a railway system and transporting them across the country. So it is a rather bizarre situation that this is a type of thing happening. But the logic is, but why does this happen? And it turns out, and I'm sure some of you are going to say, but Mark, this is obvious. It wasn't necessarily obvious to me when I started doing this. Sand is not just sand. Not only do you need the right particle type of sand, the particle size of sand. So if you don't have the right particle size or winnowing, then your sand is of little use and you need to go and crush it. Obviously, as soon as you crush it, you add new costs. No one's going to be happy about that. The other thing is, not all sands work. So that's why sand from the Sahara or the Gobi is out. You can't use it. Why? Because it's well-rounded. In order for cement or concrete to work, it needs to be angular. And the only places that you start getting angular sand is in riverine environments, estuarine environments, or marine environments. But that comes with a cost. Probably the classic case is in China at the moment, Poyang Lake, where what originally happened was, with the infrastructure developments in China, there was massive sand dredging in the riverine system. Led to a whole lot of environmental issues, and then what's happened is the sand is now getting dredged out of the lake itself. Now, the problem with these type of things is this. This is what happened to Poyang Lake in 2012. Now, there's two reasons for this. Yes, there's actually three. Yes, there was a lower in general rainfall that happened, but two other things that happened at the same time which caused this calamity. First of all was the sand dredging in the riverine system downstream from the lake, which led to higher outflows than normally would have happened in nature because the river's now been opened up. The second thing was the building of the Three Gorges Dam system upstream from the lake. So the natural amount of water, natural supply of water was then getting limited by damming. So a lot of implications for this, but it's not just occurring in places like China. This is an example from India, and there's actually hundreds and hundreds of these you can go through. If you go to this website below, the graphics Reuters one, there is a whole load of examples of the implications of sand mining on ecosystems, and it's not just happening in China and India. It's actually really scary what's happening in especially West Africa, places like Liberia and Sierra Leone, Nigeria, where sand is just getting stripped from beaches and used in building of sub-quality material. Now, just as an aside, when you're taking sand from a marine environment, it contains salt. Salt and cement don't like each other too much. So one of the things that you should be doing with any material or any sand derived from the marine environment is giving it a good wash with fresh water, which then promptly takes us back to this whole thing about, well, water is getting tight with more people, and we're now using water to go and wash sand. That water then becomes contaminated with salt, and it's no longer of any use for irrigation or drinking. So again, there's massive implications in terms of when we start thinking about some of these things, or when you start applying your mind. Other big thing in India specifically is this what's referred to as the sand mafia, where there's massive cartels involved in illegal mining in India. Really worthwhile doing some research onto that. Some of the figures, if they are to be believed, are totally astonishing. Now, what also happens is richer countries, as I've shown beforehand, poor countries, just flicking back, like Vietnam and Cambodia, taking the natural resources to go somewhere else. Well, where does that money go? Or where does those resources go to? Well, it goes to the rich countries, like Singapore. Singapore, originally part of the British Empire, when it was first established, was a trade post in what was referred to as a malarious mosquito-inhabited swamp. Now, as you can see over time, Singapore, which has no natural resources of its own, it's a financial hub, has imported massive amounts of sand from other countries. Now, the only one that's a bit misleading is 1973. No, this is not the green they're referring to. It's these green portions sitting offshore here, and this large area, and these large areas over here. But over time, Malaysia, by importing other countries' sand, has built itself up. The other country which is notorious for doing this is the Netherlands. They dredge massive amounts of offshore sand and use that to build dikes to expand the Netherlands themselves. But other things are vanity building projects. So if we move on to Dubai, tons of sand. The highest or the tallest building in the world, Burj Khalifa, 828 meters high, as you can see there, Every single thing was imported from outside Dubai to build this, okay? All the glass was imported, all the concrete was imported, all the steel was imported, and probably, again, something which really just freaked me out a bit, to be quite honest, was the sand was imported from Australia. You know, and again, if you think about this, not only have you got this massive building, which was everything was imported, but your sand is coming from as far away as Australia because it was the right quality, what was needed for the high tensile concretes which were used in the building. Now, getting back to this whole Chinese thing, you know, casting your mind back, there was this massive usage of cement in China, but there was very limited or no export because it's all used locally. Okay, this is the Pearl River Delta. And just have a look at those numbers. Now, if you start thinking about it, within this really relatively small area, you have the equivalent population of all the capital cities or major cities of Britain, Italy, America, Ireland, all grouped together in one small area. Now, of course, those people all need houses or at least apartment blocks to live in. And that's where all the cement and sand goes to in China. And this is just one small portion of China. What's even more interesting is when you start looking at the actual figures in terms of Chinese consumption. Okay, the last one is absolutely mind-boggling. Okay, China basically in, was it 2-year period, has used more concrete than America did in 100 years. And we're talking about, when you start looking at America, we're talking about building things like the Dwight Eisenhower interstate highway system, which is all built of concrete. We're talking about things like the Hoover Dam, the rocket pads for launching missile silos, and China has just outstripped that. One of the other statistics I came across is that if you were to take that amount of concrete, you could cover the entire China in a layer of concrete approximately 2 meters thick. Another really interesting visual graphic, which I didn't put into this presentation, is if you go to the Reuters graphic website, one I referred to earlier on, they use the Great Pyramid of Giza and scale Chinese and American cement consumption relative to the Great Pyramid of Giza. And again, it's just absolutely mind-blowing. But moving on from that, I mean, I've probably beaten sand and cement a bit to death now and implications of some of this. But the other primary thing that we need in our life is tar, or what's referred to more correctly as asphalt or bitumen. Like Witwatersrand carbon, they actually come with slightly different meanings, basically due to sourcing. But the main thing that these are all used in is making roads. Now, there's only currently 2 ways of making a road. You either make, well, apart from dirt roads, you either make it out of cement or you make it out of tar with aggregate. Now, what tends to happen is because asphalt is so expensive, tar in most other countries, not so much in South Africa, but tar in most countries then gets ripped up and recycled. The problem with recycling of tar is the fact that because it is an organic carbon, over time it gets dried out and you still need to replace a certain amount of asphalt in the recycling process. Now, there's a lot of discussion both in the cement and the tarring industry or the road building industry to start using recycled plastics into a lot of tar and also as a substitute for things like fly ash and cement. The problem tends to be, first of all, you need the right type of plastic. A lot of the older plastics contain nasty elements in it, so you can't really recycle them too well. And the other thing is they tend not to have the same strength component as the traditional things like fly ash or aggregates that go into, cement buildings or into tar. And in the same way that just when you think cement is cement, and in this case, I thought, well, you know, tar is tar. Turns out tar is not quite just tar. There are a whole variety of different types of tars with different viscosities, different flash points, and you use them for different types of road surfacing. So again, as you can see here, this is an American standard. And you can see depending on the load that you're going to be putting onto it, so the type of corridor. So if you're looking at a light duty, so normal cars on the road, you use what's referred to as the PG6422 binder. Okay, tends not to be as strong and you don't use as much additive. As soon as you start looking at roads where there's big trucks driving on them, then you go up to something which is significantly more expensive. This all has implications again in the raw material, because depending on the type of vehicle that you're going to move over the material, it depends on the type of size of the aggregate you're going to use, the abrasiveness of the aggregate, the weathering characteristics of the aggregate, and how much aggregate you're going to be using to make the ballast in the roadway. Okay, so again, when you start going into some of these things, they tend not to be as simplistic as what you might first think. So something we all know about, this is what it looks like. And the correct terminology, as I again discovered, it is not tar macadam or tar. The correct terminology to use in these cases is asphalt cement, with the bitumen being the binder. Now, most of these come as a byproduct from the oil and petroleum industry. So again, if we start looking at going towards carbon neutral and starting to phase out oil and petroleum, these things are going to become a lot more expensive to manufacture. So the cost per meter, the cost per kilometers of roadways will, by definition, start increasing. So bringing in some geology, because I'm sure everybody wants to see some geology by this stage, I'm almost finished, is the Canadian Athabasca tar sands deposits. So these are massive, in fact, the world's largest tar sands deposits, hosted in the Murray Formation up in Canada. And this is where most of the mining occurs from these type of things. It employs several 100,000 people in jobs, and it's always been a bone of contention between the mining companies, or rather the petroleum companies in this case, and environmentalist lobbies. The reason why? Well, it's quite simple. Effectively, the Athabasca tar sand deposits are what you would refer to as ultra heavy sour deposits. So what that means is that they are very complicated carbon chains, so you need to crack them. And at the same time, the sour means it contains a lot of sulfur. So if you ever go and do some research or go and glance through, for example, this Green Life, a Green Web website, you will see photographs near the processing facilities of these massive piles of sulfur. And again, it's relatively crude or poor quality sulfur, and there's nothing you can do with it. So these things just stand there and leach themselves into the environment. Now, when we start looking in the general context, the broader context of things like cement and sand and building of things, we start running into potentially some ethical conundrums, given the UN Sustainable Development Goals, of which there are 17, tied in very tightly to trying to make the world a more equitable place. So part of the World Economic Forum's Great Reset program is that you no longer, or theoretically will no longer, see the massive disparities between Western societies and emerging economies. So the whole concept is that everybody will have a decent place of work, everybody will have fresh water, everybody will be able to live in a house, and it will all be sustainable. But as we've seen, these things are going to start coming at a cost. As soon as you start cutting out one aspect of it, it will have implications and ramifications. The other thing that you'll start coming across when you start delving into this a little bit more is this concept of donut economics. Now, it's currently punted as an economic theory. It tends not to be, it's more of a philosophy, where again, it's trying to determine in which areas are we using too many of the natural resources and the impact. So you can see here, we are impacting, well, climate change. We're impacting in terms of nitrogen, phosphorus. Okay, and just an aside, the reason why we're seeing that is because the more people you have, the more food you need. The only way that you can get more food is then by applying fertilizers or rock fertilizers to ground. They are either nitrogen-based or phosphate-based. What then tends to happen is, because there's too much put onto the soil can't absorb it, and that gets flushed off either through irrigation or through natural rain processes. And again, that causes a whole lot of other issues, such as algal plumes. As soon as you have algal plumes, then you start killing off the local life in rivers, and you end up with abiotic environments. Conversion of land. Again, why? Well, more population needs more housing space, but also with the drive to go to biofuels, for example, what tended to happen is land that would have been used for agricultural purposes then gets converted because it, you get more revenue coming out of growing soybeans than you do for growing wheat. So people or farmers started moving from food farming to producing, pardon me, vegetation, which would then go into biofuels, which then started causing pressure on things like the Amazon rainforest. So it's not just illegal mining and forest and felling in the Amazon rainforest. A lot of that type of thing was driven because of this drive towards biofuels. And then that obviously will impact on animal loss. So if we start moving into the future, well, what are the type of things that we can see? Well, first of all, we need new technology. There is no currently known substitutes for cement and concrete. There's a lot of speculation in the market. There's a lot of research going on, but it runs into two things. First of all, the unproven technologies, and second of all, it runs into economics. Okay, you're building a building, you need insurance. Most insurance companies will not be prepared to insure you if you're using material which has got no proven history. I mean, concrete has been used by the Romans. We're going back several thousand years of proven technology. It's got a track record. You could look at things like using natural products like kaolin, so what's referred to as metakaolin, so kaolin with additives and stuff. The problem is it's just not as strong enough as cement. Using fiber reinforced concretes, again, is something familiar to those that work in ultra deep level mines. Again, the tensile strength is just nowhere near the same as what you're seeing. And then we start looking at the whole plastics issue, because now you're bringing plastic into the equation, which comes from the petrochemical industry. Interesting thing when you start looking at some of the recycling aspects of stuff is when you start recycling things, they don't always come back at the same quality product as the primary material you put into it. So, for example, if you start researching recycling of cars, the steel that comes from a car and recycling tends to get contaminated with copper and molybdenum and other stuff, and it can't actually be repurposed for the same thing. So it tends to be, that material then tends to go into something which is not of the same standard of quality. So in general, recycled steel from cars tends to be turned into rebars to be used in the manufacturing industry, or sorry, in the building industry. When we start reprocessing those old buildings, it no longer is economically viable to take them out. So again, it tends to be used as landfill in a lot of cases. And I said, this is all unproven technologies. There's been some concerns raised, for example, about the use of plastics in things like cement and in asphalt roadways. There's been technology in America which has been tried to start using the solid waste from sewage factories to be used in terms of some sort of slag. But again, all of these things are pretty much unproven at the moment.
Sorry, Mark, to interrupt you. We're going to have to wrap you up.
Okay. Oh, okay. Anyway, last slide is farewell. This is the bungee, the Yellow River dolphin, declared extinct in 2006 due to human activities. And one of the reasons cited is mining of sand out of the Yangtze River. And that concludes my talk.
So I'd like to thank the speakers that have gone before me, particularly those this morning who made some of the case for me on whole systems perspectives, to which I have a project that responded, which will allow me to go very quickly through some leading principles behind the research. And the first is this, that the requirements for the infrastructure of low carbon energy require a large diversity of materials. They require a diversity of materials that are produced in large concentrations, the bulk metals, and a diversity of materials that are technology metals with specific properties that cannot easily be substituted for other materials, which are used in smaller quantities. And so we need to think about what they're used for in what quantities they're used. And I've got these 3 bullet points up here, which is essentially the way that the UK government has absorbed the need for different metals, in that it has an energy white paper in which raw materials are actually considered in terms of their application. And the breakdown that's used in that document is the materials for industry and power, the materials for building, the materials for transport. It's quite a simplistic way to consider what we need, but it does very nicely emphasize the diversity of materials. It also nicely, if we think about the diversity of materials and how long they've been used for, as some people have said, it highlights how recycling and circular economy initiatives can only, for the technology metals, be put in place as we're really starting to use them. And so they're not going to, in any way, replace or limit the demand that's going to be placed on primary raw materials production. So my talk is quite EU-centric because the Commission funded this research. And Judith showed different criticality metrics. This is the most recent EU depiction of the critical risk list, which is the 4th iteration. And the important point that I want to make is in each iteration of the Commission's investigation of what's critical, a wider number of commodities was considered each time. And the wider that net is cast, the more materials are considered to be critical. And the other point that I want to make with this graph is the EU, yes, it thinks about supply risk on the one hand, it thinks about economic importance on the other, and the materials that are critical can move across these boundaries from one time to the next. The important thing is the bulk materials are down here. While they're not currently considered critical, they are of very high economic importance. And of those metals, of these materials, I'm not in this talk considering biotic materials like these over here, or natural rubber, which is on the critical list. I'm thinking about metals. And yes, we have the byproduct commodities, which are tied to those bulk metals. We have alternative sources, and the lithium brines are one of those. And then we have the more traditional primary mined commodities, which is what I'm really going to focus on today. And one of the things that links the bulk and technology metals is that the amount of reserve we have is a function of grade and tonnage. And it doesn't really matter whether you're looking at bulk metals or you're looking at technological metals. The general rule of thumb is the metals are geologically available, and they can be available in a variety of different ore deposit types. So this graph is for rare earth elements. And the important thing about this graph for the rare earth is only Bayonobo is over here in a giant sized ore deposit. And so we have a sliding scale of types of ore deposit, and some will be higher grade and lower tonnage, some are higher tonnage, lower grade. And we have a situation where the current mining paradigm is focused on these higher tonnage, increasingly low grade ore deposits. So we need to think a little bit about why that is. If we put it in a supply chain context, then essentially we have an increase in value as we go from the raw materials to the end products of the supply chain. And essentially, what we need to think about is what makes a deposit economic depends on the value increase in the supply chain. So as we follow the manufacturing chain from feedstock supply to intermediate product manufacturing and to end product manufacturing, this embodied incremental increase in value as materials are traded many times, that requires that feedstocks are relatively inexpensive. So while the manufacturers and raw materials producers are inextricably linked by supply and demand, the impact of price fluctuations on business is proportionally greater for raw materials producers than for manufacturers, since it relates to a larger proportion of the means that risk of price fluctuation is higher for raw materials producers than it is for end manufacturers. It also requires that we think about the efficiencies of scale. In order to keep costs low, we need to think about how lowering the unit cost of production of the raw materials. So how do we lower the unit cost of production? It's by continuous operation with a consistent feedstock, and by maximizing throughput to make sure that that feedstock remains consistent. This is what favors development of giant or world-class ore deposits with proven reserves that ensure an adequate and extended life of mine, an extended or adequate return on investment. So the impact of that is that for the technology metals that are required in small quantities, we can potentially satisfy global demand with just one or two giant ore deposits. And as Judith and other people have demonstrated, that is what results in supply concentration and therefore impacts the criticality metrics. So when we think about that centralization of global production, particularly for technology metals, we have to think in terms of extractivism, this relationship between consumers and producers, where essentially production is concentrated and we have a material flow with increase in value to those centers of consumption. So extractivism is not just about the transfer of material, it's an economic model in which the raw materials are traded outside of the raw material producing nation to more wealthy countries where the value is added to the commodity by manufacturing. And the term has negative connotations, having arisen from colonial traditions of taking wealth from the global south to enrich the global north, and being positioned at the interface between economy and negative environmental impacts. So it constitutes an environmental risk in a very immediate sense for the producing regions, and an economic and industrial risk for close to market manufacturing and consuming regions such as Europe. We also see that there is a very strong link to other aspects of international trade and relations, and the rare earths again provide a very neat historical model for this, in which initially, the rare earths were coupled to the arms race, and then it became part of the manufacturing for household items, and now it's key to the critical energy transition. And so the EU, for example, and other regions, of course, has this whole suite of actions to try and secure access to resources, not just the rare earths. So that whole suite of actions includes reducing demand through reduction and substitution. And we do see that, and in response to some of the talks, there are now regulations that are moving towards the right to repair as opposed to replacing items in a disposable consumption society. So that's very interesting. There's also the UK Fires report, which thinks about all of those transportation, building supplies for a low carbon economy. And the Use Less research group in Cambridge, for example, thinking about how they just design for reduced mass in construction and engineering, which is very exciting. And then there's alternative resources. And this last one down here, which I'm highlighting for diversifying mining strategies. And why do we need to do that? So when we talk to operators who are engaged in large-scale mining, there is a very, very clear need to consider extending production from existing mines, because we know that we need the bulk materials. We know that the bulk materials are produced by the efficiencies of scale. And we know that it can take mining a very long time to respond to demand by setting up new mines. It frequently takes decades from initial discovery of an ore deposit through evidencing success to investors and to full-scale production. To prove the economic viability of a deposit is a complex, expensive, and protracted process. It's another protracted process to gain licensing in a favourable economic, legislative, and societal climate. The overall scale of mining operations and the established reporting and finance system mean that the raw materials sector does respond to demand, albeit slowly, for the bulk metals required for infrastructural development and transport. And so the operators of large-scale mines suggest we just need to ramp up production from increasing mines. And that can help respond to changes in demand while the exploration and proving of viability is ongoing for new mines. We need to think about whether that's sustainable in the long run. And we also need to think about how that works for the technology metals, where it's more challenging to prove that there would be an adequate return on investment. And that's particularly the case for large-scale mine operators that have very large overheads. Would a smaller scale technology metal mine ever provide an adequate return on investment when a company has very large overheads? So when we put all of that together, we have to think about whether we rethink the scale of mining. Can large-scale mining work in the long run for the diversity of materials we're going to have to be able to access? So a project was designed around whether we can rapidly respond to very short-term changes in demand for technology metals as a consequence of design and innovation at the end user consumption, end manufacturing part of the supply chain, how do we increase the rate of response of mining by looking at small scale operations? So essentially, we ask the questions whether the global trade, regulatory, and finance models are suitable, because the large, low-grade, energy-hungry, and waste-generating mines that have a significant ecological footprint will really work in the future. So essentially, we need to think about reducing the amount of investment needed. We need to rethink our approach to CapEx for startup and OpEx for operating. We need to think about whether this can ever be economically competitive with the current mining paradigm that exists. And if we do start diversifying mining strategies and adding more small-scale mining to the mix, what is the cumulative impact and how do we offset that? So we decided that what we needed to do was put together a project which did get funding from the European Commission to think about the technologies that we could use for selective low-impact mining of small high-grade deposits and place that in a whole systems perspective. Although we were centered around technological innovation, we know that that can't happen in isolation, because we need to think about the supply network, the logistics of transportation, how it will interface with ore deposits, how it will interface with the environment and with society and with the economic situation. So in a 4-year turnaround, we had to design, build, implement, transport, and test the technologies for a small-scale, not gold mining operation. And we decided to do this by taking one example of a bulk metal. We used lead because we had an opportunity to test that. And we chose one example of a technology metal, antimony, famously known as a fire retardant, but also used for antimony selenide solar cells. So we wanted to see if our small-scale mining approaches could be adaptable to different commodities and whether it could therefore be translated from one ore deposit to another, particularly in response to changing price fluctuations, which obviously change the economic viability of different ore deposits. And so essentially, what we had to do in the very first instance is differentiate between small deposit mining and small scale mining. So small deposits are necessarily described in the geological and metallurgical terms that are needed to engineer mining and processing solutions. And scale of mining operation describes the infrastructure that you put on site and its impacts on the surrounding socio-environmental, economic context, micro-political context, essentially. And we had a problem in that the existing definitions of small-scale mining really didn't translate to what we were trying to do in a European and Balkans context, because although the Balkans mine sites we used were outside of Europe, they do feed into European manufacturing. And so essentially, we needed to start with just thinking about those concepts of small deposit and small scale. And so one of the things we did was look at a range of different commodity types, and BRGM built a query function tool within an open access platform with the link depicted there on the slide to actually work out what is the potential for small scale mining to be used on small deposits. And essentially, as you can see, there is a huge density of symbols on that map of Europe there, basically saying that there's an awful lot of small ore deposits that have sufficiently high grade that they might be feasibly economic. And in this platform, we can query whether there's infrastructural access to those mines to make startup easier. And so the fact that we can cross-reference means that there can be an initial investigation of potential. We didn't stop geologically with this classification of what constitutes a small deposit, because the other problem we've got is that we have to think about, if we're going to use a small high-grade deposit, we're going to have generally some mineralogical complexity, particularly if we're looking at vein deposits. So we started to think about what are going to be the problems with accessing small deposits where we have relatively high geological uncertainty and relatively high metallurgical variability. So I've just put in one slide of a large number of research approaches we took to think about geological uncertainty and metallurgical variability. And so just to explain these figures a little bit, at the top of each of these figures, we have an antimony deposit from a place called Podgorica, which is near Gorazde in Bosnia. And on the bottom, we have antimony deposits from Zajaca, which is in Serbia, just over the border. As I said, we deployed on an Olivo mine site which had lead, where we had a mining operation and processing operation on mine site. And in the second instance, we used a satellite mining model to look at different antimony ore deposits and how they can feed through. And what we found is that when we look at it through a geometallurgy lens, we need to accelerate the amount of geological information that is generated by early reporting. We found that instead of just a simple petrographic survey, we needed to do some QuemScan modeling of the association of antimony minerals, whether they're sulfides or oxides, with other materials that could be problematic for processing. And so we start out with our QuemScan analysis of rocks, but then a very simple hand grind and subsequent QuemScan analysis to give us some initial ideas on liberation and the subsequent association of the antimony minerals of merit with other materials can actually give us a little head start on thinking about the processing options and challenges that we would use. And then the metallurgical test work went a lot further to enable us to design processing flow sheets and start to actually design the construction approaches for material. It helped us to think in a geometallurgical context about not just geological information and flow sheets, about material handling and storage solutions, about mine planning for selective removal of material and backfill to minimize waste production. So we'll come to those technological solutions in a minute, but then we had to think about differentiating the mining sectors, and the definitions that are presented there are published in Resources Policy. And essentially what it was is that the social scientists on the team realized that the existing definitions of small-scale mining didn't conform to the framework of funding, the technological innovation for environmental regulation in Europe. And so essentially, the important thing, I think, is that small deposits are amenable to small-scale operations, but small-scale operations can theoretically be used for project staging purposes on large-scale mines in order to reduce capital startup costs, to high-grade early production, and create finance for subsequent mine development. Nevertheless, the cost of startup may be unrealistic for artisanal mining, and this is yet to be determined. Importantly, small-scale mining is not limited to small ore deposits and can be responsive to changes in demand. So what were our technological innovations for the small-scale mining? The first thing is that a selective mining tool, which is much smaller than those commercially available, was designed, built, and deployed and tested, where the cutting head and power pack were designed to enable changing orientation of picks, changing speed, and by doing that, not only can you access within a vein and mine quite vertically and remove far less material, and thereby reduce transportation, haulage, and crushing, reduce energy consumption, but also by changing the pick design and speed, you can change the particle side that's taken off the rock face and reduce the amount of primary crushing that's required. You can't quite replace a primary crushing requirement overall. Then taking that material from underground, putting it through a reduced scale containerized ore sorter, you can reduce material further, reduce the amount that goes through comminution, which is particularly energy hungry. But by downsizing throughput, you create technical challenges that we needed to resolve. And so those were very practical, logistical challenges, and I don't think we're quite there yet on that. Importantly then, once we'd got that material through and sorted, in the first photograph I showed the physical reality of this equipment deployed on a mine site. So this is a 4-container physical separation unit we use that can be deployed in different configurations depending on the footprint available at a mine site. And then there's a processing design that was created for treatment of industrial water. And so essentially these were thinking about how do we, when it's on a mine site, change the way we think around these, and very importantly, because we have all these different units being deployed on a mine site together with a new selective mining tool, with a new screening facility, with a containerized ore sorter through the comminution unit to the facility deployed on site. Having all of these different units together at once enables us to gather data about the manpower required, about the water draws, about the energy draws. And the other important thing, and just because I've revisited this figure at the bottom here, the selective mining tool and the comminution circuit were installed and hot commissioned on site, each within half a day. The minerals processing test facility had craneage demands, some concrete demands, and this was installed and hot commissioned within 3 days. And we can compare that to the main Olivo processing site, which is there in the background, which was constructed over a period of months. So certainly construction off-site and deployment was a very rapid response. But the contribution of this kind of mining to local employment is really small. And we were able to calculate that relative to the overall employment rate in the local regions. So there was a very big social sustainability and health and safety emphasis on this project, and that's being worked through into publications at the moment. But it does require a new conversation between the mining industry and society. We also need a new conversation between the mining industry and energy, obviously, and this is what's particularly important for this meeting, I feel, is that yes, we need all these minerals for the energy infrastructure, but we are going to fail to achieve a low carbon result if we do not think about the energy for mining. And, you know, I've used the metric, the little piece of information before that mining consumed 11% of the world's total energy consumption in 2017. To think that it will be over 25% in just a few years' time is a very, very sobering thought. So in our project, we thought about whether or not the approach could be very nicely supplied by renewable energy. And so a paper is pending acceptance. It's been reviewed and resubmitted now to Resources Conservation and Society about renewable energy systems for mining. Now, it's important to notice that renewable energy systems are available on the market, and as we've heard already today, Anglo American aims to be 100% renewable in South America. So renewable energy systems are being used on large-scale mining sites. However, conventional diesel generation is still preferred for off-grid small-scale mining operations because of their mobility, because of their modularity, and because you have a consistent energy supply, which is needed to maintain energy provision to keep a processing operation running continuously. You can't have fluctuations in energy. And so a survey was done of MMC-RES, mobile and modular containerized renewable energy systems that are currently available on the market. And very importantly, it's not just about the rate of renewable power output, it's also about the horizontal dimension of the renewable energy systems for a small footprint, small-scale mining operation. And essentially, a set of simulations was carried out using HomerPro software to work out what are all the possible designs of operation that you can have to actually change your energy draw. And we were able to do this kind of experiment with the equipment we had. So for different peak energy demands and loads, it was found that there is a particular architecture which combines solar PV with biomass gasification generators and lithium ion batteries for storage. The balance of solar PV and biomass changed depending on where in Europe was investigated. And that means that, for example, in the sort of Mediterranean countries, solar PV would make a larger contribution. For the Balkans, where there's adequate forestry, biomass would make a greater contribution and would have a bigger CO2 output. So the site in Europe corresponded with the balance of renewable energy and the implication in terms of CO2 generation. We modeled that CO2 generation as the dominant metric in the climate change impact in life cycle analysis of environmental impact. We've also done social life cycle analysis, which I'm not showing today. But a very large number of metrics were used to think about the environmental impacts. And yes, CO2 and the energy production really is the critical one overall. But very importantly, the impacts of different processes in a more small-scale mining operation have different impacts in terms of other ecotoxicity events. So there is space for improvement. Obviously, this was only a pilot to really tease out all the challenges. The important thing is in using the renewable energy investigations and the life cycle analysis investigations, we get to change the design of the mining operation for maximum beneficial operation. And this was really important because we had to operate in a very adaptable way. And we really did have to respond in the same way that nimble and adaptable mining would, for the simple reason that our first deployment was on a mine site that was fully licensed and ready to start operation. And the environmental license that existed for that first operation is stated that there could not be any use of flotation chemicals. So our processing plant was based on gravity methods. On our second site, we were trying to get environmental licensing in real time. And essentially, there was not enough knowledge on the flotation reagents that would be needed in order for us to get environmental licensing. So we had to use that satellite model. We had to have our mining located at one mine site, and we had to have the equipment located on a fully licensed processing site 20 kilometers away. And so the way in which we think around environmental licensing has to think about maybe changing the mining model and the deployment of mining facilities, where we maybe think more about upgrading on site and isolating environmental contaminants from small-scale operations by transportation and satellite operations. But all of those exist in former mining paradigms. So it's very much something that can be done and designed once we have adequate knowledge. So one of the things that we come out at the end is, what is the knowledge we need? When do we have adequate knowledge? And how do we design the whole system for maximum environmental, social, and economic benefit to both the mining company and the community? And so we also, at the end of it, have to think about technology adoption. What we find is that if we think about technology development and innovation in isolation, it's very difficult to think about equipment providers being able to commercialize that if the development costs are high relative to the market opportunities. And the market opportunities stay low unless we have that long-term testing to prove to mining operators that it is a viable working option, because the mine operators are subject to greater economic risk relative to the value chain. So early adoption by mining operators is impeded by the economic risk with which they're faced. So those are my concluding comments. There's an awful lot to unpack, but I hope that that is of interest. And my final acknowledgements, yes, we had funding from the European community. You can see all the partners there. But actually, the communities in both Bosnia and Serbia who welcomed us to mine and processing sites also participated in our social surveys, which was very, very important. And so a very great thanks to them for hosting us as well. And I will stop sharing.
Thanks so much for that, Kate. That was a very interesting talk. And I'm sure everyone agrees. We have time for a quick question if there is one. Otherwise, hopefully you'll stay until the end and then we can have some discussion.
Yeah, that would be great.
Great.
Okay, critical materials, the last 10 years, the good, bad, and the really annoying. No, there we go. And it actually comes out of a suggestion that Mark gave, that I could give an update on the presentation I gave at the IGC in 2016. And my first thoughts were, what on earth did I say back in 2016? And then I thought, well, it's probably, if it's going to be an update, that could be a bit boring. So I'm just going to talk about what's changed, what's new, and perhaps reflect back. So in fact, that probably is the same as an update. So to give it some context, what was happening sort of 2007, 2009, before we really started to see sort of critical raw materials hit the spotlight or really come into the media in any way, shape or form. And from 2007 to 2009, it was really all about uranium. There were two GSSA events, one in 2007, one in 2009, focused purely on uranium exploration and uranium deposits, principally in Africa. Nuclear power was regarded as clean and green, and the uranium price was rising and peaked at $140 US a pound in late 2007. And there's a chart there, and you can see the very nice peak in the uranium price. It's actually going back up again now in sort of 2021, and people are quite bullish about uranium and uranium exploration again. 2010 was the probably next major significant event, the Senkaku boat collision incident, which you might remember regarding the rare earth elements and the questionable constraints on rare earth element exports from China to Japan or the rest of the world, but it certainly drew our attention to rare earth elements and critical metals. Perhaps it wasn't quite a coincidence that the 6th International Rare Earths Conference occurred in November in Hong Kong of the same year. In 2011, the Fukushima Daiichi nuclear incident caused by the earthquake and tsunami, uranium then certainly became not a topical commodity, and rare earths got even more focus. And I think that sort of perhaps is now being slightly forgotten as uranium comes back into favor again. And we can see the chart there showing from 1994 to 2017, global production of total rare earth oxides in black, price of monazite concentrate in red, and dashed red line the Mish metal average. And the sort of prices really peaked in about 2010, 2011. And so that's just a sort of summary of various talks that I gave on the subject of critical raw materials from about 2011 to 2019 in various places, mainly in South Africa, but also in the UK and in Japan. But it's actually quite interesting to see the changes in the topics of the talks. I was trying to obviously make them relevant and make them interesting. And so starting off in 2011, it was sort of pegmatites and rare earth elements, none of which were really targets then and probably still aren't now. Then sort of other elements started creeping into the talks: niobium, tantalum, antimony, tin, tungsten. Antimony was then something from sort of up till about 2014 that was quite a topic of interest. And 2014, we start to see lithium coming in. And lithium and cobalt have really been of major interest probably since 2018 onwards. And then in about 2018, 2019, the hype cycle was something that I sort of tried to concentrate on, and we'll see more about that in a minute. And it's probably not really a surprise that the commodity focus changed with time. If we look at the price charts of top right, we see REEs peaking in about 2011, and antimony peak in 2011 as well. And really the antimony price has dropped considerably since then. Lithium peak in 2015, 2017. Again, dropped off until about the early part of this year, but again, climbing up. So I guess that shows that academics can react to prices of commodities as well, and we try and make our talks topical. Perhaps it also helps us get funding for research. They also illustrate the theme of the hype cycle, which was developed back in 1995 for looking at emerging technologies. It's somewhat Zen-like in its terminology, with an innovation trigger, a peak of inflated expectations, a trough of disillusionment, a slope of enlightenment, and a plateau of productivity. It's not really a cycle and doesn't predict what's going to happen to the emerging technology or the commodity of interest. There's only one outcome, the plateau of productivity. But I think it can be amended to either sort of have a subsequent hype cycle, or actually sort of disappear and not be interesting anymore. Probably better envisaged as a feedback loop rather than a cycle. And it's certainly been applied. It's sort of 2010. We can see that a BRGM presentation showed where lithium and rare earths were on the left-hand side, climbing up towards hype, and that tantalum was really on the right-hand side in its plateau of productivity. It was very routine to know that tantalum was being used in cell phones and in capacitors. In 2012, it made it into mineralium depositor, the hype cycle, and by then, rare earth elements, particularly in wind turbines, had actually overtaken lithium in car batteries. And so you can see sort of commodities moving up and down depending on the technology that they're involved with. So it's reasonably simple to apply this in a, I suppose, a non-quantitative way, really very qualitative. And so now coming to the sort of good, bad, or annoying since about 2010. And what's happened to antimony? According to Roskill, the overall demand for antimony has actually been increasing for flame retardants, lead-acid batteries. However, the amount used in any individual item that's been manufactured has been decreasing. The increasing price, the increasing costs of antimony resulted essentially in increased substitution, and there was further increase in health and environmental legislation, which reduced the use of antimony. And that really has led to the decrease in price of antimony. And so what effect will that have on deposits such as Stibium Mapani in the Murchison belt? Are we likely to see antimony continue to decline? At the moment, because of the ease of substitution, that is a distinct possibility. It will be interesting to see what effect EVs will have on antimony demand. Obviously, less lead-acid batteries as a whole. What about fuel cells? Rare earth elements, the sort of kickstart to the whole critical raw materials environment, I think is sort of going to be probably good eventually. And after the initial rare earth element exploration stimulus and reinvestigation of many projects worldwide, it's worth noting that there are no new rare earth element mines operating in Africa yet. And according to some work in 2017, the defined mineral resources of rare earth elements outside of China doubled between 2011 and 2015 from 40 million tons to 98 million tons. It wasn't actually that difficult to find rare earth elements, albeit from projects that were known about and perhaps really didn't need too much discovery. And so from that, the map on the right is something Jock Harmer and myself put together in 2016, showing African rare earth element projects, which were then at a resource stage or at an exploration stage. And I think now there are 4 or possibly 5 projects in Africa which still show signs of life, particularly with a longer term perspective. Some of the others may well indeed come to life as well, depending on the prevailing environments. But we'll just have a quick look at Lofdal, Steenkampskraal, Longonjo, Namaqua Hill, and Phalaborwa. They're interesting in that they show 3 very different styles of projects, if you like. And this is the table from 2015, which shows the added rare earth oxides to the resource inventories between 2010 and 2016. Kankankundi, Steenkampskraal, and Sandkopsdrift were relatively well known, but the others really were new resources, although reasonably well-known deposits. Lofdal has the highest grade in terms of percent heavy rare earth element oxides in Africa at 20.5, although it's quite a low tonnage, about 6 million tons. The mining license application is currently in review. A preliminary economic assessment was completed in 2014, and in 2021, Namibia Rare Earths announced a JV with JOGMEC. So the project is progressing. Steenkampskraal in South Africa, the highest grade total rare earth oxide deposit worldwide at 14%, although a rather low tonnage at 0.6 million tons. It's a vein type monazite bearing deposit, contains 2.14% thorium, historically mined. It was awarded a water use license in 2020 and had a mining right license awarded in 2010. So potentially that could well be one of the first new rare earth element mines in Africa. Longonjo in Angola, which was one that didn't have a resource and wasn't really undergoing active exploration back in 2016. But since then, Pansana PLC have been doing exploration in Angola. It's a carbonatite hosted principally neodymium-praseodymium project, and they intend building a rare earth element magnet manufacturing facility in Humberside, Yorkshire, UK, which would be designed to process rare earth sulfates from Longonjo. Namaqua Hill in Tanzania is a similar sort of story. Peak Resources completed a BFS in 2017, a carbonatite hosted basanite dominant deposit. The mining license is currently under consideration by the authorities in Tanzania. And the intention is to establish a rare earth element refinery from concentrate to oxide in the UK, in this time near Middlesbrough in the Tees Valley, which will use material from Namaqua Hill as a feedstock. Phalaborwa, this was a relatively recent announcement of November last year and doesn't refer to the sort of main carbonatite itself in the center part of Phalaborwa, but really from the phosphates for processing the waste gypsum dumps, which have been left after phosphate mining. And there's a low-grade rare earth element deposit there. I guess one of the good parts of this is the vertical integration that we're seeing at Longonjo and Namaqua Hill projects, and probably something that we'll see more of in the exploitation of a lot of critical raw materials, especially where we have small scale or small deposits. It makes it easier for supply chain management, blockchain technologies, and the overall chain of custody for goods and services and of the ore deposit itself. There have also been suggestions that companies like Tesla and Apple would like to move into the mining sector to ensure the security of supply of CRM for their manufactured goods. Again, more vertical integration. The two smaller deposits, Steenkampskraal and Lofdal, have potentially very specific products, but are very limited in size. So it's quite difficult to actually envisage individual processing plants being justified for those two deposits, and they may have to find somewhere that will take the offtake for the mines. Vertical integration for minor metals and commodities isn't new. The two main fluorite deposits in southern Africa, Okurusu in Namibia, now shut down, and Vergenhoek in South Africa, were or are owned by European chemical companies. One of the things that we see in terms of price of commodities, share prices, this hype cycle that I've referred to, and critical raw materials are, I think, particularly vulnerable to speculation and volatility. It's quite annoying, really. They reflect short-term fluctuations based on the perception of shortages. It's not necessarily real shortages, and often optimistic forecasts of demand, panic buying, and or optimistic expectations of price increases. We now have a fire alarm going off here. If it's not annoying for everyone, I'm going to continue. Is that all right?
Not an actual fire, right?
I hope not. This is the third time it's gone off this afternoon, so I'm fairly optimistic that unless someone comes and knocks on the door, we'll be okay. It's gone off again. Critical raw materials are typically low volume commodities, and when one mine sneezes, the rest of the world gets flu. They're much more susceptible to price fluctuations. Medium to long-term trends are much more reliable and provide better indicators of growth. And volatility is not new at all if we consider tantalum, and when that really became a critical raw material back in the late 1970s, early 1980s, principally produced from pegmatites such as Tanko in Canada, Wodgina Greenbushes in Australia, or now from Central Africa, Rwanda, and DRC. 1978, 1980, the first computers, the electronics industry said, oh, we need lots and lots of tantalum. There was panic buying, there was stockpiling, and then the price crashed. Stockpiles depleted, increased demand. Late 1990s, early 2000, our first cell phones. I can remember buying the first cell phone in about 2001 in South Africa. And then 2 years later, almost everyone I knew had a cell phone. Again, rumors of shortages, panic buying, and a price crash. Then one of the main owners of one of the mines, Sons of Gwalia, who were operating and owning Greenbushes and Wodgina in Australia, went bankrupt, and there was significant volatility in the market then, and another price crash after that. This really explains all that in a little bit more detail. The blue line is the overlying trend, and I think this is the sort of important thing to look at whenever we see a price spike in a critical raw material commodity, because that is really much more indicative of the overall trend in that commodity. One particularly good recent paper that I really enjoyed reading was an evaluation on the drivers of volatility in metal markets and exposure of producing countries, focusing on critical raw materials. And they reckoned that essentially for minor metals with few and specific high-tech applications, the demand and therefore the price was actually controlled by complex interactions of all the drivers that they had considered: technological change, speculation, government interference, substitution. And I was amused by mere perception. I think mere perception is perhaps understating the importance of perception, because perception essentially drives investment and drives consumers. The conclusion that they came to was that the complexity of this interaction makes it impossible to forecast which drivers, which raw materials will play a dominant role and which will fall back into a niche state. I don't think that is an excuse to do nothing or an excuse to try not to predict what's going to happen, but I think it should make us aware that really a forecast is just that, a forecast, what we think might happen. And if anyone's tried to predict the gold price in the last 20 years, I think if they've made it a success, that's really very impressive, but I certainly wouldn't want to try it myself. Shortages is another sort of perhaps aspect that is frequently touted. And it's really the perception of potential or perceived shortages which contributes to the market volatility. One of the problems is that the figures that are used by non-geologists to calculate global resources, non-stock exchange compliant resources, are typically based only on company reports of reserves and resources. They take no account of unknown, undiscovered, or minimally evaluated deposits, what can be referred to as the geopotential of a particular commodity. And so they are always going to underestimate the amount of material available in the ground. And the pessimistic viewpoint always seems to get more publicity. There's a very nice diagram from 1949 from the US, where mercury was going to run out in about 1952, lead in the late 1950s, copper and zinc before 1970, and coal was going to run out by 1980. I don't quite think that this happened. And obviously there's the limits to growth in 1972. And again, there's quite a lot of discussion about, did they get it right? Did they get it wrong? Certainly in terms of predictions of when something was going to run out, they would be quite happy to admit they didn't get it right. But I think also it's important that they weren't there to make predictions on when a particular commodity would run out, but really to highlight the difficulty in understanding the sustainability of an industry that is actually exploiting and in the longest possible term is not sustainable. But again, we've heard from Michael this morning on lithium. It's interesting that with the sort of lithium exploration boom that happened in Southern Africa or Africa in about 2017 to 2018, in approximately 3 years, 3 million tons of hard rock resources were defined in compliant resources, and those are the ones in red. Global production at the time was in the region of 80,000 tons per annum. So it wasn't actually difficult to go and find more lithium. Okay, again, quite a lot of those were known pegmatites, known hard rock resources, and it really just required evaluation as opposed to exploration. Battery metals, lithium, cobalt, nickel, vanadium, and who knows? I think it's most definitely in a state of flux. Lithium being covered by Michael, and we're going to hear about vanadium in the next talk. We don't know what the batteries of the future will be. We do know that there will be price volatility. it's likely that the chosen technology is not necessarily going to be determined by the best technology. There will be commercial factors which potentially will have a greater effect. For those of you of a certain age who can remember the VHS Betamax sort of debate, VHS format came to dominate the market of videotapes, while Betamax was regarded as the better technology. Not necessarily 100% true, but it was perceived as the better technology. Betamax, in fact, couldn't record as long a time on a tape as VHS could. But the cost to consumer and the convenience was much more important than the perceived quality of the product. And the same, to some extent, is happening in terms of Android versus the Apple operating system, iOS. What will become the sort of dominant technology, or if there will indeed become a dominant technology, is open to question. I think in terms of battery metals, it may be that there will not be a single technology that will dominate the markets and dominate the products for a system. We may have to have multiple technologies and multiple critical raw materials, which I think is only to an advantage. And that leads on to the sort of EVs versus fuel cells sort of controversy. And certainly everyone was very, very positive, and I think still are, about lithium-ion batteries. Price increases, attendant hype, exploration booms. But I think now there is a greater realization that fuel cells may also have their place. And certainly successful use of fuel cells is happening and is on the increase. And intrinsically, a kilogram of hydrogen has 236 times more energy than a kilogram of a lithium-ion battery. And there are still question marks over the future of large trucks or lorries and aircraft, particularly given weight restrictions. Hydrogen or biofuel in those cases seems to be more appealing than lithium-ion batteries. Which is greener and cleaner? I think one could probably listen to a whole days of talks or presentations on the advantages and disadvantages of lithium-ion versus fuel cells. The sort of take-home message that I've got in the last week was that if hydrogen is produced by reverse electrolysis from water using renewable energy rather than from refining natural gas, the reverse electrolysis and renewable energy is more environmentally friendly. Refining natural gas emits CO2 and carbon monoxide. Having said that, the environmentally friendly process of the reverse electrolysis is currently only 75% efficiency in terms of energy. So there are always going to be technological developments which are going to be important, which need to occur. I think one of the key things is that if you look at the whole critical raw materials sort of systems, energy, usage, and products, nothing stands still. Everything is subject to change. Surf and turf is a lovely example of where hydrogen, to use a BBC headline, is transforming these tiny Scottish islands. Surf and turf is always good in my opinion. The Orkney Islands are offshore Scotland, of the far northeast of Scotland, and they have abundant wind and water renewable energy. And they have too much energy. In fact, they have surplus energy from wind and water, and it's used to generate hydrogen by splitting water. They've got quite a lot of that as well. The hydrogen is then stored as compressed gas, used to power fuel cells in vehicles and buildings as required. And in fact, the municipal vehicles on the Orkneys are all fuel cell powered. Given the use of PGEs in fuel cell technology, this is obviously good for the South African platinum industry. However, the role of EVs has been and will continue to be easier and faster than fuel cells. There is already an electricity grid network in most countries. Changing perhaps petrol stations to hydrogen stations is not going to be an easy thing. But refueling a hydrogen-powered vehicle takes about the same time as refueling an internal combustion engine vehicle. Electronic vehicles are even in Africa. The two photos below of the e-Golf are taken in Kigali in 2019, where VW and Siemens rolled out the e-Golf. It's interesting, and it's a 2009 sort of statement. For any vehicle range greater than 160 kilometers, fuel cells are superior to batteries in terms of mass, volume, cost, initial greenhouse gas reductions, refueling time, well-to-wheels efficiency, using natural gas or biomass as the source, and life cycle costs. Now, I suspect that the calculations have probably changed since then. Whether it's 100 kilometers or 200 kilometers now, I have no idea. But certainly at that time, the fuel cells were potentially superior over that greater distance. And so again, I suspect it's another illustration of change with time. And so decisions we make at any point are going to be based on the information we have at that time, and are not necessarily going to be the right decisions for 20, 30, 50 years down the line. But I think we have to stay flexible because of that. Solar energy, PV cells, good. In South Africa, we're now seeing more solar farms than before. We now have 384 megawatts operational from Globe LEQ. I drove by a farm on the honours field trip late last year, which was under construction. That's the Google Earth image in the top centre. That's just south of Polokwane. There is a 31 megawatt Southpan solar power project just north of Vivo in Limpopo province. But according to the Solar Capital website, the largest solar farm in the southern hemisphere is near Daar, although that is a 2016 statement, and there may be bigger now. And so solar seems to be taking off in South Africa with perhaps a boost from load shedding by Eskom. But there are also some other interesting things about photovoltaic cells. And you might not be aware that the recent research has showed that adding capsaicin, which comes from chili peppers, to perovskite solar cells increased the efficiency and increased the amount of energy produced by the solar cell. In February this year, it was reported that researchers from the Royal Melbourne Institute of Technology have developed solar paint that generates energy from water vapor. There are actually two other methodologies of using solar paint to generate energy. And there's a fascinating article at that website link. If solar paint works, perhaps solar panels aren't going to be required at all. And I think that is the key. Technology is changing rapidly, and the requirements for raw materials will change as a consequence. If and when solar paint becomes a commercial reality, what raw materials will it use? And is their mining, extraction, and processing more clean and green than the alternatives? It's such a rapidly changing field. It's very difficult for us all to keep up, I think. Just 2 slides left now. Because of that, I bought this book at our local bookshop about a month ago, The Rare Metals War, The Dark Side of Clean Energy and Digital Technologies. And this prompted the sort of title for the book, for this talk. Because the book, I'm only halfway through it at the moment. It's good, it's bad, and in places it's really annoying. The inaccuracies, the emotive language it uses are perhaps something I'm not used to. But then again, I think it brings things into the discussion. It brings the discussion into the public domain, which can only be a good thing. I think the more society, the more the public, the more politicians actually read and find out about critical raw materials, the better. And in contrast, we have the probably well-known Critical Metals Handbook that I'm sure most of us have seen, that came out quite a while ago, but also Raw Materials for Future Energy Supply. I think that's 2018 by Friedrich Wellmer and co-authors. Most definitely excellent books, but probably not really in the public domain. We need more dissemination of knowledge, more discussion. We almost need a sort of David Attenborough of critical raw materials, which perhaps will try and take over from showing animals or plants or insects or whatever in the environment, but to find out more and inform the general public about what they use on a day-to-day basis. Thank you very much indeed.
Thanks so much for that, Paul. And I'm glad to see that you haven't been smoked out or fired out there. There's a question or a comment in the chat box here from Xavier. It says, perhaps, but do we have actual data for that regarding the scale of artisanal mining and the true environmental impact they have? Or is the real impact rather the illegal mining is taking place in areas or shafts that were never properly closed or rehabilitated?
Oh, is that pertaining to a particular commodity or a particular area?
Xavier, would you like to unmute yourself and have a chat to Paul? If you can. I'm not sure. Yeah, I'm not sure what it's particularly asking about, Paul.
Okay. In terms of, I mean, I think there are a lot of individual studies on perhaps artisanal small-scale mining. It's something that's often said to be environmentally a problem. I think that is justifiable in some cases, but also probably totally unjustifiable in others. And I think it's probably very, very difficult to get a global or continent-wide perspective on small-scale artisanal illegal mining anywhere. I think there's certainly figures from the gold mining industry which suggest how much gold is mined illegally on the planet over a year, and I seem to remember that it was about sort of 10 to 15%. I could be wrong. Mark may well be able to get a better figure there than I can, but it was certainly significant. I don't think critical raw materials generally come into the same category because of the difficulty of processing most of them. Certainly, I don't think there is going to be an illegal rare earth element processing lab anywhere on the planet. On the other hand, things like sort of processing cassiterite or pyrochlore for tin and niobium tantalum are sort of not that, it is a very different kettle of fish altogether. So I think it probably needs quite a lot more work, and certainly when it comes to looking at it on a global basis.
Great, thank you. Thank you very much, Natalie, for that introduction. Yes, not only am I joining remotely, really remotely, I also just had a baby, so that's actually why I'm out of the country at the moment. So this is also my paternity leave, but I feel this is an exciting enough topic to talk about and share. And look, the topic is vanadium real electrolyte batteries, but I promise that the next 40 minutes or so will not be that technical. And hopefully it'll actually be broad enough where it'll be interesting to all the participants. Just a little bit about me. I run Bushveld Energy. I founded that business. It's part of a larger group, Bushveld Minerals, and I also wear, which is an integrated vanadium company, but also wear a number of other hats. I chair the South Africa Energy Storage Association, and I work a lot on global topics as well. I'm not a geologist, so I'm hoping that will not be held against me over the next few minutes. Bushveld itself is as I mentioned, a vertically integrated vanadium company. Some people might think of us as a mining company, And certainly we do a lot of mining. We actually started as an exploration company and a multi-mineral platform at some point where we had coal, tin, vanadium, platinum, but really started to focus on vanadium because it was an exciting commodity. It's used primarily in steel, but we also saw this emerging opportunity in the energy space, which is transforming quite a bit, which I'll talk about later. And so we set up the energy business, which is what I run, in about 2015. And we do a few things there. We do component manufacturing, the part, the electrolyte, the part that stores the batteries. We've actually made some investments into battery companies, and we also have a project development team as well. So that's what we call an integration. But I do want to stress that our geology is core to the company. It's what the roots of the company were based on. Our mining assets, you can see on this map, we've got a mine in Brits and a processing facility there. We've got a processing facility in Vanchem. And then we've got a greenfield project, a mining project in Mokopane. That was actually our first project that convinced us that the vanadium is a commodity that we wanted to be in. And we've grown quite a bit. We probably had about 6 to 8 people in 2015 when I joined. We've now got over 700 people, all of them in South Africa. And 2 of our founders or co-founders are some of the most foremost geologists in South Africa, the Wilhelm brothers, and great people, and a lot of insight on the Bushveld complex, as well as a lot of other geological formations. So while my talk will not be technical on that side, I do just want to stress how the origins of our company are really based on geology and the unique geology that is found in the Bushveld complex, which is where the name of the business comes from. So and I think that there's maybe 4 objectives that I would like to cover today. So one is to introduce energy storage and highlight its significance in the global energy transition. Some of you may have heard of this as the energy transition to clean energy or to sustainable energy. And needless to say, that's very much aligned with this clean and green topic of today. The second part is I want to emphasize why specifically this is important for a mineral-oriented economy like South Africa, and thus the mineral-oriented industries in South Africa as well. I'll focus a lot more on vanadium, and specifically the vanadium redox flow battery technology. I promise this will not be a technical talk, but I will talk about the technology nonetheless. So a few technical details will be there. I'll talk about what its role in the power system, and how advanced the adoption of the technology is. Needless to say that the demand for the mineral and the use of the mineral in a product are very closely linked. So to talk about one without talking about the other would be inappropriate. And then finally, I want to talk about some of the characteristics of the technology itself that really makes it clean and green, and thus a good fit to today's topic. So I'm hoping that energy storage is something that you have seen in the media quite a bit, whether it is from foreign media or local media. It's a topic that is very hot, part of the clean technology craze to some degree, but I think it's a craze that is not independent of where the world is going. But it is a big topic, and hopefully today you'll get some insight into it. Really, where does it all start? And it all starts with the fact that electricity itself is actually, in my opinion, the core part of what is called the energy transition. It's not the fact that we're seeing the electrification of everything is just critical to this story. In 1980, about 10% of all energy went through electricity. Today, it's about 20%, and you can see that on this graph. The electricity is this dark blue part. Yes, there's a bit of a dip in 2020. You can see the kind of impact COVID has. I always like these charts. They really tell you what pandemics do. But you can see how it's getting larger, whereas everything else is basically getting smaller, or in the case of gas, remaining constant. We know that this is at the expense of coal, and we know that this is at the expense of oil. Oil is used for mobility a lot, and you can see electricity displacing that. Coal is obviously used more for industry and for electricity, and you can see that is being displaced to some degree as well. So that's a key thing. By the middle of this century, it'll be well over 40% of all energy going through electricity, and the trend will continue before. So if you're doing anything with electricity, the next 100 years are great. And I think one of the challenges that electricity presents as an energy carrier is that it's much more difficult to store. Something like coal, you can store for millennia, and it's actually energy is there. With electricity, it's a lot more difficult, and so the ways to store it, whether they're batteries or other types of storage, are a lot more important because this energy carrier is becoming a lot more important. The other part of the energy transition is the fact that this energy, this electrical energy, is being created by renewable sources. And we've always had some element of renewable sources, which is this blue part, and it's hydro. But what we're seeing a lot more of is solar, different types of solar, especially solar photovoltaics, PV, and then wind, onshore and offshore wind. But really that's what's driving most of the electricity that's going to be generated, again, at the expense of coal, and to a lesser degree of oil, with gas, I think, more of a question mark, and nuclear being quite constant. But that's really what's driving it, as is renewable energy. And there are some additional challenges that renewable energy, especially solar and wind, produce, which is the fact that they're only available when the wind blows and when the sun shines. So again, the need to align supply and demand of electricity becomes greater. Now, in a power system, there's always an imbalance between when electricity is produced and when consumers actually use it. But when you have renewable energy, that imbalance becomes even greater. And so the need to store energy to time shift to support the power system increases, and hence more need for energy storage. But I want to stress that while renewables are a big driver for the need for energy storage, they're actually not the underlying one. The underlying driver is the increase in electricity. So if you think about how electricity is consumed, there's kind of three categories. There's consumer electronics, which is one that all of us are familiar with. Our mobile phones, our laptops, calculators, for those of us who are a little bit older, flashlights and things like that. The one that you're probably hearing the most about are electric vehicles. Still very, very nascent in terms of how much electricity is consumed by electric vehicles, but growing quite a bit. But really the biggest part is our buildings, whether they're buildings that have manufacturing or buildings that house people or offices. And this is where you have stationary storage. Basically, this piece here is where you would use stationary storage. This is where you would use mobility storage, and this is where you would use kind of consumer electronics, basically batteries. There's really no other kind of storage that's used there at the moment. So you can see how these three types of storage are allocated in the current marketplace. So we're somewhere here around 2020. Most of energy storage demand is, not surprising, electric vehicles, because of just how important the battery is to a car. The one that is very stable is this green, consumer electronics. It is not expected to change very much, maybe slight growth, but basically this supports kind of your information aspect of electricity. The piece that is growing the most, and maybe that you would have expected to be the largest, is the kind of grid-related storage, but it's actually not the largest at the moment. It's the one that is growing the fastest, but the reason why it's the smallest is because to date, that need for storage has been covered by other technologies, such as coal. Coal, again, is a way to store energy. Gas is a way to store energy. But as we're moving away from those fuels and moving more to sustainable fuels like solar and wind, we actually need a lot more of grid-tied storage, or even off-grid, but basically this stationary storage. So again, while I think the insight I wanted to take away is that while electric vehicles are the ones that get a lot more press coverage, and for good reason, because right now they're the ones that are actually driving how much storage is used, the growth point, especially if we extrapolate this to 2030, 2040, and 2050, is around stationary storage. So we're starting at a very low base, but we're seeing massive growth. And this chart would look very different if we looked at it in 2050 than it does in 2027. And even in South Africa, we're actually seeing quite a bit of movement on the stationary storage side. For those who track what's going on in the power sector, the IRP, which is the Integrated Resource Plan, the most recent one we had was in 2019. And for the first time, it listed not only technologies that generate electricity, such as coal, nuclear, hydro, wind, etc., gas and diesel, but it also included storage. And it's interesting because storage doesn't actually produce electricity. It takes electricity and then it feeds it back into the power system at another time. But it's that important to the power system now that it's actually got its own separate category and its own separate allocation. And we're seeing quite a bit of procurement already starting up. Eskom has got a very large battery program that they're running. For those who have seen the results of the risk mitigation round, which was around getting more electricity onto the grid as soon as possible to help with reducing load shedding. There were about 4 projects that included batteries out of the 8 that were awarded. The ones I think that get the most coverage are the gas ones, these power ships, but actually, and they do combine for most of the energy that actually has been awarded. But 4 out of those 8 projects, smaller projects, they have renewable energy and they have batteries, and that's quite exciting. And on top of that, the DMRE has also said that they will come out with their own program for another 500 plus megawatts of storage. So it's quite exciting to be in South Africa and in the energy storage space. So what is storage used for? Well, actually quite a few things. I'm not going to go through all of these, but basically they're all about kind of matching this mismatch between when electricity is needed and when it's produced. And I sometimes like to equate that storage is kind of the time equivalent of wires. So transmission in electricity, if you're familiar with it, is basically matching the gap between where electricity is produced and where it is consumed. And storage is the same thing, only from a time between when it is produced and when it is consumed. So transmission is the where and storage is the when. And that is important because there's all of these things that are needed to support a power system that storage can provide. And frankly, it can even support you if you're not connected to a power system. And you've probably heard about people going off grid because they don't believe they don't rely on the grid, they don't want to rely on it, or it's becoming too expensive. And if you want to use solar, the only way to really have a 24-hour system is by putting in storage as well, unless you have other types of generation technologies. So about half of these are tied to renewable energy, which are the ones in gray, but a lot of the other ones are not tied to renewable energy. So storage is not just about renewables. I just want to make sure that that's understood. It's something that enables renewables and the transition to clean energy, but it's actually needed by a power system, even independently of those. The most important maybe thing to think about storage is that it is a time-based factor. So if you think about electricity, it's usually measured in watts, which you have here on the y-axis. But it's important for storage to think about duration. For how long do you actually need that electricity? And I always give an example of a car where you have an engine that tells you how fast the car can go, how much torque it can generate, a truck can generate if it wants to pull something. But it's the gas tank that determines how far you can actually get on that. And so storage needs both of these, the engine and the gas tank is this discharge duration. And sometimes you need storage that lasts for just a few seconds, maybe a few minutes, maybe an hour, maybe a few hours a day. And in some cases, you actually might need something that lasts an entire season because there could be seasonality mismatches in when electricity is produced and when it is consumed. So that's just an important thing to remember, is it's both about power, watts, and also duration, which I call energy, which is watt hours. And needless to say that the technologies that support these different use cases also differ. So you might have technologies that are great for a very short duration and others that are great for a long duration or even seasonal. So hydrogen, you've probably heard about. It's not something that would be efficient to use on a daily basis, even once the technology matures, but it is a great solution possibly for seasonal storage. Pumped hydro, which is actually most of the storage in South Africa, we've got about 3 gigawatts on the grid already. It's quite flexible, but the geography makes it a bit challenging to deploy pumped hydro wherever you want. You need to build a lot of dams if given our water issues, that's not as easy as one would think. Batteries, as you can see, are really flexible. They can give you that minute, and they can give you that day as well. So that's why batteries get a lot of attention nowadays, and it's really that around that flexibility. But there are different types of technologies. I'm not going to go into the details of them. I will go into the detail about the flow battery, but they have differences in how large they can get, their duration, where they become kind of cost competitive, what is their efficiencies, and how long they last. You know, can you use it 500 times? If you think about the lead acid batteries that we have in our cars, those do not last forever. Usually you'll replace those a few times in the lifetime of a car. Think about our phones. How long does a lithium ion battery last here? It's usually great for the first year, and then so-so after about a year, and then second year, and then after the third year, you're like, I need to get a new phone. Not because I don't like the phone, but because the battery just doesn't last. And those are just differences between the different types of technologies. And some are emerging, and some are kind of out there in the market already. Pumped hydro is what's basically been deployed historically as the most kind of commercially successful type of storage. But because of issues around environmental capabilities and just a lot of the good topography that is used for pumped hydro has been already used, it's actually they're not going to be that successful going forward. Lithium batteries are the batteries that are used the most right now, in part because the kind of the electric vehicle sector has created a lot of supply chain and cost reductions. Most of the news is around lithium ion. I'm going to focus on flow batteries, specifically on vanadium flow batteries, because that's an emerging technology. It's still kind of in early stages of deployment, but already out in the market. But certainly in the latter half of this decade and going forward, it's something that is extremely attractive and thus an exciting field for me to be in, and hopefully for others as well. So let's then talk about the second part. Why is this important for South Africa? Why is the energy transition important? Well, one is it can actually create solutions to some of the challenges that we have around employment, around economic growth, and around ensuring that the energy transition isn't just one of transitioning to cleaner fuels, but also one that remains a just transition. And one way that can happen is a revitalization of the mining sector, specifically on moving from thermal types of extraction industries like coal to energy metals, as I call them. And the beauty that South Africa has is it's got quite a lot of metals, and I'm sure everyone here understands that quite well, is that the geology is so good that we're blessed with high deposits, high quality deposits of quite a few different types of minerals. And here I've listed basically the ones where South Africa is either number 1 or number 2 in the world. There are others where it's not number 1 or number 2, but it still has fairly good deposits. And examples of that are iron and nickel. But what South Africa can do is take advantage of these, and not only to mine them, but also to beneficiate them and use a competitive advantage of just being close to those minerals and having expertise in them from a metallurgical point of view, from a geological point of view, from a chemical point of view, to build downstream industries based upon these minerals. And so the question then is, well, which minerals are going to be important in the energy transition? So this is a chart from the World Bank, and this talks about which minerals are going to be important for electricity generation. As I've mentioned, electricity is a key part of this transition. So anything to do with electricity is great. And I've put little South Africa smiley faces on the ones where there's a lot of resources available in the country. So titanium, manganese, nickel, chrome, iron, and aluminum. Now that's just generation. Let's talk about storage. Right, so storage needs a different set of minerals. This is also same data from the World Bank Group. They're looking at how much more will be needed of which commodity, and you can see that vanadium and nickel are the two that we have quite a bit that are expected to grow a lot. So and nickel is basically used as a kind of the most important, let's say the heaviest part of a lithium battery, and then vanadium used in the flow battery technology. So it's quite encouraging, I think, for South Africa that these are the things that are needed. And if you're working in these industries, this is also a good opportunity, hopefully, to see a lot more exploration, a lot more development, and a lot more mining, and thus kind of enabling this transition that the rest of the world is undergoing. So now let's get into a bit more detail specifically on vanadium, and I'll start by just giving a little bit of an overview of the technology itself and how it's different from others. So it is a flow battery, and really what that means, as the name suggests, is it's got a liquid. It's got a liquid electrolyte, which is the piece that actually stores energy. And most other batteries, whether they're alkaline batteries or lithium batteries, they're kind of solid batteries, where the anode and cathode electrode are sometimes physically intertwined, whether it's in a little pack or in those little circular cells that you've probably seen. If you remember, if you go to the store, you still have those AA batteries, AAA batteries. I mean, those are physical batteries. They're not liquid. Those are solid or sometimes gels. But in a flow battery, it's a liquid. It's primarily water with vanadium and some sort of a chemical stabilizer, usually sulfuric acid. And the technology has been around for about 40 years. The vanadium one is a little bit newer, developed in the mid 80s. And really the whole principle is you've got 4 different states of oxidation that vanadium exists in, and you have these 2 tanks, and you have basically an inverse reaction. And in one case, the electron is kind of removed from the vanadium molecule, and then on the opposite side, that electron is added, kind of creating the ability of the electron to go back. And when it moves across the membrane, you have an ion exchange, and that's when electricity is either kind of, the electron is moved in or out of the battery, and thus it's either charging or discharging at that point. So it's kind of a fairly simple design from that point of view. I like to think of it as there's kind of four things that you need: a plus and a minus and a charge and discharge. And so the ability of vanadium to have these different oxidation states and also to be water soluble is what makes it so successful in this technology. There are other flow batteries, but they tend to use multiple minerals to make this work. So it's a much simpler battery if it uses vanadium. There's a lot of benefits. I'll come back to some of the clean ones later on, but it's a battery that doesn't degrade from use because the reaction is reversible. There's no pathways that are created. It's a completely reversible reaction, and so that's quite important. You can use the full battery, and for long duration applications, it gets very cheap because you can scale the energy part separately from the power part. In most batteries, that engine in the car and the gas tank, you have to increase them together. So you can't control for the fact that I want to go further. But in a flow battery, you can. You don't have to increase the engine, you only increase the gas tank. And that's quite valuable because that means your 8-hour system is cheaper per hour than your 4-hour system. And so when we need long duration, flow batteries become very, very competitive. When we need short duration, they're not as competitive. And that's just something that's important to note. And there are other benefits like safety, there's no fire risk, and sustainability, which is something I'll actually come back to in the last part of the presentation. Usually the technology that vanadium is compared to is lithium ion. And by the way, even with the lithium ion, you actually have different chemistries, whether they're based upon iron, so a lithium ferrophosphate, for example, or manganese, nickel manganese cobalt oxide, or sometimes there's actually also cobalt nickel base that doesn't include manganese at all. So there are different chemistries of lithium, but the overall theory or the design of the battery is quite similar among those. So they do tend to be compared. But as you can see, there are pros and cons to each one. So vanadium, better for long duration, lithium, better for short duration, slightly better efficiency. It is not as safe, and recyclability is an issue, but vanadium is much safer, and I'll talk about the recyclability. That's actually a major advantage of the technology as well. The cost, this is where lithium has an advantage because of the supply chain spillover from electric vehicles. But vanadium is now actually seeing a bit of that economies of scale, finally the development of the supply chain, and that is making it more competitive. And the fact that vanadium is such a big cost driver, I actually see that as both a plus and a minus. Certainly, if you're making and mining vanadium, that's a major plus. And all of these things feed into market acceptance, where lithium is kind of more dominant, especially in the US. In North American markets, vanadium has a lot more traction in China and Japan. So there's some regional differences as well. And part of that is actually by the use cases. What is the storage used for? So this is just another way to visualize this. You saw this chart that I put out there in terms of how to think about storage of power versus energy. And you can see that vanadium batteries are kind of on the longer duration part of where batteries would play, and then lithium is on the shorter duration part of where batteries would play, but they do overlap. So that you could have scenarios where you would actually compete. Nothing stops you from putting together 8 different lithium batteries. And if vanadium is 4 or 8 times as expensive, you might actually opt for the lithium technology, even though it's inferior technically, because it's going to end up being cheaper. So there is an overlap where they do compete head to head, but there's also a clear distinction as to where one is more effective versus the other. So here are just some examples. On the left here, you can see how a lithium battery performs over time. Basically, what was called the capacity fade. So each time you use a lithium battery, it is slightly worse off than it was before. And this worse off differs by company. You can see here Tesla, LG Chem, Samsung, Sony, and it also differs over time. And by the way, there's research so that all of this can be improved. This is data from 2018 from Australia. And after about 2 years, 3 years, whether you're at 700 cycles or 1100 cycles, you're actually looking at something that's 80%, maybe 70% of what you had to start off. So that's a challenge, because it means that you have to augment or replace the battery to get the same amount after a few years, whether that's 5 years or 10 years. So you won't have someone give you a warranty for 20 years for a lithium battery. With vanadium, and here's data from a very large installation in Japan from 2015, they had basically 13 strings of batteries. And you can see that these different shapes are what it performed in the first year, second year, and third year. Very small change. And actually, in some cases, it's a little bit higher from year to year. And so that actually just shows you that the degradation is minimal. If you did 2 or 3 years here, you can actually already see a 10 to 20% decrease, which you don't see with a vanadium battery. So this is not just theory, it's actual practice. The other big benefit is that vanadium batteries are water-based, so they don't have thermal runaway risk. And there's been a lot of news, thankfully not yet in South Africa, but with more deployment of storage, we might see those fires as well. But certainly there was a whole set of fires in South Korea, about 30 different fires between 2017 and 2020. About half of the storage facilities were shut down, and all of those were provided by LG or Samsung. There was a large fire in Europe in 2017. There was another one actually just last year in the UK, and also a massive one in the US that actually threw a firefighter 20 feet from the explosion. It's, again, people don't know exactly what to do. It's a lot of times before the fire, there's a lot of gas that builds up. So there are major risks. And so there are some rules around how to install lithium batteries that are not really relevant or an issue for flow batteries. And in some cities, you're actually not allowed to put in lithium batteries because of this fire risk. This is just the kind of an old chart I've used to talk about this cost competitiveness. And really it just shows how over longer durations, a vanadium battery becomes cheaper, whereas a lithium battery kind of becomes constant. And I've talked about this, so I'm not going to spend a lot of time on it, but this is just a visualization. It's a very old chart, actually, so the prices are a fraction of what they are here. But the point is that a vanadium battery becomes cheaper as you need more hours, whereas a lithium battery does not. So again, if you want to have a short duration battery, you're actually fine with using lithium. If you want a long duration battery, you're much better off in using vanadium. This is how storage is compared on costs through using levelized costs. And I just kind of brought an example from Lazard. It's an investment bank, and you can see the technology is competitive with lithium. Lithium is in the gray, and I've used vanadium in the orange and the light orange. It is driven by applications, but still not very cheap. These costs have come down in the past 2 years, but these are in US dollars per kilowatt hour. Certainly none of us want to pay this much for electricity, especially when you convert it into rands. But these costs are coming down quite a bit, and we'll likely see prices of sub a rand per kilowatt hour for stored energy in the very near future. In fact, the tender from that used batteries, the cheapest one was solar and storage, and it came in at about R1.48 per kilowatt hour. It's not very cheap, but it's also not very expensive, and those numbers will continue to decrease as the technology matures. As I mentioned, there's a lot of deployment going on in China. That's where we're seeing most of the activities. It's a bit kind of in certain provinces, but at the moment there's between 1.5 and 2 gigawatt hours of vanadium industrial battery deployments in China alone. It is the largest market for that. In Japan, I've mentioned this is the photograph of that large battery from 2015 by Sumitomo in the northern island of Japan. You can see what it is like inside, a whole bunch of tanks with electrolyte, quite cool. I haven't been inside, but I'd love to. And just this one battery alone is basically using 330 tons of vanadium, and that's quite impressive. And they got a repeat order, so clearly it is something that customers want. A lot of news flow around vanadium batteries in 2020 and even recently in 2021. So it is a sector that is gaining a lot of that economies of scale that is needed to drive costs further down. Lithium does have a little bit of a head start, but over the last year and a half, a lot more news, a lot more companies involved, a lot more money flowing into the sector as well. So let's use the remaining few minutes to talk about the last part, which is specifically what are some of the innovations that are specific to vanadium electrical batteries that kind of make it especially clean and green as a technology. And that's in addition to the fact that it is an enabler of the energy transition. Without storage, we cannot have more electricity. We cannot have more renewable energy that generates electricity. So that in itself is already a massive benefit to sustainability and decarbonization. But on top of that, the technology itself has a number of benefits. So as I mentioned, it is a massive enabler. And an example that I use is, we have developed certain projects that are off-grid. And until maybe a few years ago, before the advent of cheap solar, the only way to kind of really support yourself as an off-grid installation was to use diesel or some sort of version of heavy fuel oil, jet fuel oil, which obviously emits a lot of carbon. So if you were to add to that a solar system, that's great, but you can only use it when the sun is shining. So just adding a solar system maybe displaces around 20 to 30% of that diesel. But if you add batteries, then now all of a sudden you can put in more solar and migrate some of that solar energy that you've produced into the night. And now you can displace not 20 or 30%, but 70, possibly even 90% of that thermal energy, which is great because it's a massive reduction in carbon output and also possibly a reduction in costs as well. That's just an example of how long duration storage really enables the energy transition. If you just had renewable energy on its own, you're only talking about a fraction of decarbonization and sustainability that you can do by adding storage to it. And the other piece is the ability to actually connect a whole lot of people who would otherwise have to wait for the grid to get there. Now, because these distributed solutions are cheaper, and that's solar and batteries, you can actually connect villages that otherwise would have had to be connected by a transmission line. And a lot of times it's really not economical to build a transmission line to connect remote communities. And there are certain parts of Africa, especially East Africa, that are the most rural in the world. And it would have been extremely expensive to build transmission lines the way that the US has, or Europe has, or China has. So now you don't have to do that and yet still provide access, reliable, round-the-clock access of electrical energy to populations that live there without having to install a whole bunch of polluting generators. And that's quite exciting, and it's a big benefit that the continent has. I see that as kind of another way to leapfrog, similar to how the continent leapfrogged in telecommunications by not having to build phone lines. The second part, over too many pages here. The second part is around the fact that the vanadium battery itself is less carbon intensive than a lithium ion. Thinking about those two options, you can actually see how much savings. This is data that was done by Texas A&M, and they basically said that per megawatt hour, a vanadium battery offers somewhere between 17 and 33 kilograms of savings per CO2. Now that's not a lot, but that's only per megawatt hour. You know, you saw a previous chart that I had where we would have needed hundreds, eventually, gigawatt hours of storage. So when you multiply that out, it's actually pretty impactful that you have this this additional savings. And it's not only on from Texas A&M. The Technical University of Munich did similar studies. They compared a vanadium battery from one company to two different types of lithium batteries, and similar savings, about 27 to 37% in reduction emissions if you deploy the vanadium technology versus lithium. So those are really good things. So and the other part that I want to talk about, the last one, is the sustainability of the vanadium itself. And this is a piece that Bushveld has been driving. It's a bit of a passion of mine, to bring the circular economy to vanadium. And the traditional economy is what's considered a waste economy, where we create something, we use it, we dispose it, we throw it out. The idea of a circular economy is that when we create something, we actually are already thinking that we will reuse it at some point, whether that's recycling, but it's embedded into the initial business case that it's not a once-off, we're going to use it multiple times. And you can do that with vanadium because the battery doesn't degrade, the chemical doesn't degrade. So the chemical, which is water and vanadium and sulfuric acid, is as good in 10 years and 20 years as it is in day one. The other components of the battery degrade, but not the chemistry. And so you can either reuse the electrolyte, or you can extract the vanadium fairly cheaply from the electrolyte and then use it in other applications of vanadium, like steel. And so for us, that's a really exciting piece that is unique to the technology because of how cheaply you can do this. And the water solubility is a big part here, but also the fact that you don't need new recycling technology. We can actually take the material at the end of the battery's life, which is kind of the step 5, and either put it back into the battery or put it back into our existing processing infrastructure, into our metallurgical flow sheet, and basically precipitate the vanadium out. And so we obviously don't need to do new mining. So there is a step that is lost, but a lot of that infrastructure can be reused in this cycle and really create sustainability around it. And I call it like bringing the circular economy to vanadium, making it almost like a circular commodity to kind of combine some key terms. And there are reasons why this works very well with vanadium specifically. I think at some point this could actually be done with other products and other commodities as well. But I start with what I know. And the beauty of this is that not only can we do this technically, we can actually create a financial incentive for this to happen by creating a model where we sell the battery, but we don't sell the electrolyte, and we rent the electrolyte because we know we can reuse it and we know it has a lot of value. And we take advantage of that value by not selling it to the customer. The customer has a massive advantage because they don't have to buy it. So that means there's less cash they have to pay up front, which makes the battery more competitive. And instead the customer pays a rental fee. So it's almost like, when do you buy a house or do you rent an apartment? So you give a customer the option to rent rather than to buy. They can still buy it if they so choose, but if they don't have the money or they don't want to spend it, they have the option to rent. And so we can combine a financial product. This isn't anything technical. The technical was on the previous page. This is the financial product, is we just create a different financial structure with a different funding model to allow for this to happen. But the great thing is it makes the technology even more sustainable. It incentivizes the reusability. It basically guarantees it, because if you didn't do this, then you'd lose a lot of money. So you basically make a promise that you will actually reuse that electrolyte and that vanadium after the battery's lifetime has ended. And this is part of some of the innovation that we are doing. And again, I think that this can be done for other products and other commodities and other minerals. but we're starting with vanadium, and to me this is probably one of the coolest and most sustainable benefits that it offers. And I think that is the end of my my presentation. I think we have a few more minutes. We can I can answer some questions as well.
Hi, Mikhail.
Hi, Paul.
Hi. Sorry, man. I just wanted to ask, what would you sort of consider to be the best scale for these particular batteries in terms of do you foresee them being used in a utility scale type of environment, or more sort of here in South Africa in particular, a lot of individual businesses and so on like it are installing photovoltaic PV installations together with battery arrays, or on larger residential sort of developments. What sort of scale would you just see these types of batteries being best used in?
Yeah. Look, and so I didn't talk through all the details of the advantages and disadvantages of the technology. Probably the biggest disadvantage of the flow battery is it takes up more space. So it's about 2 to 2.5 times the volume of a lithium ion battery. And that's why you don't see them in phones and you don't see them in cars. So the question becomes, can you fit one into an apartment? Or can you fit one into a house? Well, you probably would put it outside. So that's part of the hesitancy that I've always had about would residential consumers use vanadium batteries rather than lithium batteries. There's a safety benefit, but there's a space issue. And there are a couple of vanadium battery companies that are selling specifically to the residential market. One in Germany, because there's a very large battery market in Germany, and then one in Denmark. But those are the only two, whereas there's about a dozen who are catering to utilities and commercial and industrial customers. The other thing to consider is that in terms of who's going to deploy the most storage, it is the front of the meter or your utilities. And by the way, utilities could be independent power producers that sell to utilities. So your solar plant that has a large battery attached to it. So that's the largest market. So if you just think about it, there's probably going to be more use cases there from a quantity because it's the largest market. It doesn't mean that it won't be useful in other applications, but that's just a pure volume play. And my hesitancy in the residential side was around the fact that space is a bit more at a premium. But certainly there's nothing stopping mines, and we're building a solar and vanadium battery mini grid at one of our operations in Brits. There's more than enough space there, because if you're building solar, you need a lot more space for the solar panels. The battery's footprint is no longer really an issue. It's, do I have enough space for all the solar panels?
Well, that's where I was going, because I mean, there's been a lot of talk about Goldfields, getting permission to build their power plants recently, and what sort of type of array system would they be setting up? And on a mine, generally 24 operations. I mean, that's exactly where the benefit would be seen. Thanks.
Yeah. No, I agree, and I think that the challenge that we still have is that, in part because these developments take a couple of years to even get. I mean, Goldfields actually went out to a tender for this. Initially for the PV back in 2015 or 2016, so it took them a while to get a license. I'm still a bit frustrated that mines aren't thinking about storage. That they're just thinking, well, I'm just going to put in solar, and I'm not going to care what happens when the sun goes down. I've got the grid for that. That's actually very bad for the grid, and you're actually already seeing Eskom respond to it by increasing their capacity charges. And pretty soon, I guarantee you, we're going to have really cheap energy that we can buy during the day, and the nighttime energy is going to be more expensive, because that's happened in other places where a lot of solar has been deployed. So a lot of those companies are going to switch and start to use storage when the tariff structure changes. But in the meantime, they're actually just thinking, I'm just going to put in solar panels because it's going to make it look that I'm more sustainable, and because it's just easier to put in one thing rather than two different things.
Oh, cool. Thanks very much for the great talk.
My pleasure.
Greg, I think you're on mute, or you're not on mute, but you're talking, but there's no sound coming. Still
no,
not.
I can't.
Yeah, sorry. There was another question from Nick in the comments there, Mikhail. Does the vanadium battery have an end of life if the vanadium doesn't degrade?
Yes, so it does have an end of life. It's not only the vanadium, it's the electrolyte that doesn't degrade, but there are other components. There's the casing, the tanks that store it, and those are made of plastic, and then usually there's metal outside. There are membranes, which basically function as the electrode. There are pumps. So all of these things do wear out either due to time or due to use. So it's a little bit like a power station or a car. You know, you have a car, and what's the use of the car? Maybe 10 years or 20 years. But you do need to repair and replace certain things like the tires much more frequently. So at what point does the lifetime come into play? And in this case, it's when replacing all of the components becomes more expensive than buying a new battery. And so that's usually when the engine goes, which are the cell stacks, or the second most expensive component. So usually companies will give you about a 20-year timeline for that. Some of them will go to 25 years, and they're basically doing that because they're trying to align with the timelines of how long solar and wind technologies last. So it's a little bit of an arbitrary time because yes, you could actually say it lasts for 100 years. You just need to maintain everything except for the electrolyte. And in a way, if you think about our rental product, that's exactly what we're doing, right? We're actually saying that this thing is going to be there for 100 years, but you have to change all the other stuff. So that stuff you have to buy because we can't rent it out because it's gonna degrade. But the stuff that doesn't, we're happy to rent out and keep it around for decades rather than just for a certain timeline. So hopefully that answers your question. Usually they'll put in about 20 years, but it's the other stuff that has to be maintained, and you will need to replace some of those other components on a regular basis. Filters, probably once a year. Expensive stuff, probably after 10 years. Most expensive stuff, probably after 20 years.
Craig, we still can't hear you. I'm not sure what the story is there, but there's another comment in the comments from Tony. He says, "Excellent talk, Mikhail. The financing model is very interesting in terms of incentivizing recycling. Probably an example of ESG best practice from the financing perspective."
Yeah, so there's there's kind of two parts to how investors can kind of drive the sustainability agenda. One is by telling companies that they've put money into, saying, if you don't clean up your act, literally by decarbonizing, by making sure that your water practices are sustainable, your labor practices are not only law-abiding, but probably even some cases beyond that. So investors and funders can motivate companies to change behavior, and we're seeing a lot of that in ESG right now. And as a mining company, we're definitely not immune to that. The other way that they can do it is by making investments that are in themselves kind of an ESG investment. And so from our point of view, we're the way that we're going to fund this structure is through a commodity fund. And you have some commodity funds that are just there to give you a commodity return. Here, on top of that, it's giving you a return because yes, vanadium can become more expensive or cheaper, but it also enables more sustainability. So we like this model not only because of what it does to vanadium and the vanadium battery, but we actually think there's going to be a lot of appetite to support it because of what it does. And it is really around tapping into what do investors want. Yes, there's a piece of me that is kind of an idealist and I want to make the world a better place. But if I'm trying to create a product, whether it's a technical product or a commercial or a financial product, I need to have people who are willing to put money into it. And right now is a very good time to develop financial products that are attractive to investors with an ESG mindset, either because they need that for marketing, but I actually think innately people want to see two types of returns now. They want to see their money not losing money and earning something, but they also want to see it making the planet a better place in 10 years or in 30 years, and not kind of making the same, not mistakes, but compromises that the previous generations have made. And it makes sense to try to cater to their needs. And in this case, what we're doing on the rental absolutely does.
Cool. Thanks very much for that, and thanks for the questions. Craig, do we have you back yet? I can see you, but we can't hear you. I'm not sure what the issue is. Anyway, are there any more questions then for Mikhail? You can just raise your hand or unmute yourself and go for it. Anyone?
Well, I mean, someone asked for a little bit more detail in how the electrolyte is recycled, and I kind of showed it in the chart there. But physically, let's assume that you can't reuse the electrolyte. So the simplest way is we take electrolyte from one battery, and that battery has, that project has ended after 10 years or 20 years, and we pump it out, and then we deliver it to the next site where that electrolyte is reused. That's the simplest way. Let's assume that in 20 years, nobody needs storage anymore, or nobody needs vanadium storage anymore. I think those are unlikely, but sometimes you have to be risk averse. So in that case, we take that electrolyte and we ship it to either back to South Africa if it was produced here, but actually to any vanadium processing facility, whether it's in the US or in China or in Brazil or in South Africa or in Russia. And there's a couple of smaller ones. And you can actually then feed that electrolyte into the process flow. So in our case, at our Vametco mine, we have 13 steps. And I think it's somewhere before the leaching mill that we would actually feed in. We've actually done this. You'd feed in the electrolyte. And we already use sulfuric acid in our metallurgical flow, so we're actually not introducing anything new, just a little bit more water, but that will evaporate out. But we're actually putting in something that is about 15% vanadium, 10 to 15% V content. Whereas in a typical mining process, we'll start with something that is 0.5% V, if even that. So actually, it's actually in some ways even more economical to do it that way. So we are incurring some additional transportation costs, but we don't need any new infrastructure. So we're actually feeding it into an existing infrastructure that exists, and we're having less byproduct. If you think about how much earth has to be moved in mining, we're not moving any earth. How much additional stuff needs to be put into dams? None of that here. So it's actually a cleaner way to get vanadium back as well. But the key thing for me is the value of the vanadium is quite high compared to the cost of reprocessing it, and we don't need any new R&D. The R&D that we have done is just proving that we can do this at our facilities, and in fact, other companies are doing this as well to see if they can actually physically reprocess, previous electrolyte, and it doesn't have to be just one location. I think South Africa will definitely gain from this process, but you can do it anywhere you have a vanadium metallurgical plant.
Maybe I'll start with, and we'll end the session with this one as well, but directed at Mikhail. The idea of new business models. Has there been a lot of thought into new business models to drive faster uptake of these technologies? Is that one of the reasons that you're looking at lease agreements for components of your systems as opposed to just simple sales?
Look, from our point of view, absolutely. I think that's one part of it. I think the other is the world is changing, and it's probably changing at a faster rate. So I kind of always talk about that second derivative, the acceleration of the rate of change. And so you need to think about changing in almost like 3 different dimensions. So you can think about if I'm, let's say, a mining company, I can change how I mine. But maybe I need to do more, so that's actually where some of that creativity comes from. I think the companies that tend to drive that are the smaller, maybe junior miners who sometimes do it out of necessity because they can't get as much attention unless you're doing something creative. But I also think because entrepreneurs tend to go into those kind of companies rather than in the more established companies. And so that's why you do find some creativity that comes out of those spaces. I mean, I used to tell people that what makes Bushveld different is that we have very few miners. Our chairman is a miner, but almost everybody else in the company was either a geologist, an accountant, a management consultant, a banker, not really a lot of miners. So and that means that if those people build a mining company, they're going to have different ways of looking at things than if it was miners building a mining company. And so that's I think that's in some ways where these things come from. But we are seeing other companies do things like that as well. Sometimes it's driven from other businesses. A lot of like the deployment of renewables might be driven out of the ESG parts of the businesses, out of their ESG budgets. We're seeing something like a lot of more creative partnerships where a company like Volkswagen will sign offtake for a certain commodity. Usually you would have a trader do that. You wouldn't have the actual user. So at what point does a Volkswagen or a Tesla become a mining company? And at what point does this distinction between who's a miner and who is somebody else go away? So I've talked about our business model as integration. You're actually seeing that from a lot of bigger players. It's just not talked about in the same way. But signing a 10-year offtake is the equivalent of basically funding a mine or owning a mine. You're just kind of legally managing that risk a little bit differently, managing the balance sheet a little bit differently. So you are seeing innovation, and I think it's sometimes because of the creativity of the people there, and at other times it's a necessity thing because this rate of change is accelerating.
Yeah, thank you for that. I mean, we are definitely living in a world of change right now, and it's where we're going to be in 20, 30 years is anybody's guess. Would anybody else like to comment?
Where we are in 5 years.
Yeah.